Right. A warm welcome to everybody. So, welcome to the marathon session on electrical machines. Am I audible to everyone? Am I clear? Just let me know in the chat box. Am I clear to everybody? Right. A warm welcome to everybody. So, welcome to the marathon session on electrical machines. Hope it is fine. From my end, it was very clear. Okay. So, very good morning. Very good morning. Yeah. All right. So, yeah, coming to this marathon session that we are conducting from past few days, various subjects have been already completed, like electrical, power systems, mathematics, okay, control systems, digital electronics, EMF. Some of the subjects have been already completed. Now we are coming to electrical machines. Okay, so if you are new here, I am Surendra Reddy. I teach electrical machines at Om Institute. Right. So coming to machines is a vast subject. All of you know that. Okay. And if you look at the weightage for this particular subject, okay, just a moment. Yes. So electrical machines. So as far as GATE exam is concerned, this particular subject will carry around 10 to 11 marks. This is general weightage. Sometimes you may get 9 marks, 10 marks, 8 marks, 12 marks. Okay, on an average, 10 to 11 marks you can expect from electrical machines subject. Also, it is one of the core subjects for electrical engineering students. Okay, and this will be useful not only for GATE examination. If you are preparing for engineering services exam or state services exam, so even if you go to interviews also, electrical machines is going to be one of the key subject for electrical engineering students. Okay, and there will be 4 parts, as you all know that. So I'll be discussing about DC machines first, okay, in this marathon session. Next I will go through induction machines, okay, and then I'll take up transformers, and then I'll go through synchronous machines. Okay, so any doubts if you have throughout this particular marathon session, keep posting in the chat box. Okay, whenever I gave you a short break, I will go through your messages and I'll try to give you the reply. Okay, all right. So now I would like to take around 2 hours to 2.5 hours for each machine's part, so that we can complete the all machines in a single day. That's my plan, but let's see how it goes on. Okay, so what my plan is for this marathon session. Generally, in regular classroom course, I used to take approximately 40 hours for each and every machine. So overall, I used to teach 160 hours. Okay, that is for regular classroom session where we discuss from the scratch till the depth of the subject. Okay, that is normal regular classroom course. But in this marathon session, I am trying to finish this entire course in 10 hours. Okay, so that means you can understand a 160 hours course we are trying to finish in 10 hours means this will be little crisp in nature. So I will only discuss about the summary points and important formula. Okay, and we will also practice questions related to each and every topic. So I am picking approximately around 20 questions for each machine's part, so that we will try to solve approximately 80 questions in this marathon session. And every topic I tried to select 1 or 2 questions, so that will brush up all your previous learnings. Or if you already learned this subject, it will definitely brush up all your basics, also formulas and in-depth concepts. Okay, if you are very new to electrical machines subject, some of the concepts you may not be able to understand because it's a just a last minute revision type. Okay, if you are very new to electrical machines, just understand whatever formula I gave you, just believe me, the formula is correct. Okay, you don't try to question how sir wrote this formula. That is what we use to learn in regular classroom course. So in this marathon session, whatever I gave you the points, you believe me, all those points are going to be correct. Understand? Okay, and if you already know about this subject, of course, whatever formulas and whatever summary points I'm going to give you, you already know all those things, and you just try to brush up all your basics. Okay, right. Now Let's start with DC machines first. That is going to be the first topic today. Okay. See, DC machines is relatively easier compared to other electrical machines. At the same time, if you make any small mistakes, you will end up with wrong answers. Okay, any small mistake. Okay, so generally, if the multiple choice questions are given from DC machines subject, any small mistake, you will end up with a wrong option, which will always be available in the 4 options given. Okay, so therefore, you need to be very careful. Okay, even though subject is very easy, you need to be very careful about every step that you are approaching in the problem solving. Okay, and there are number of topics available in DC machines. So let us see what are the important topics that we are going to discuss. So first we will discuss about EMF equation of a DC generator. Okay, and then we will see equivalent circuit of a DC generator. Then what are the different types of DC generators that we have? Okay, different types of DC generators and characteristics of these DC generators. Characteristics of DC generators. Okay, and then we will see what are the different types of DC motors. Okay, and then characteristics of DC motors. Characteristics of DC motors. Then we will see speed control of DC motors. Speed control of DC motors. Okay, once we are done with speed control methods, then we will look at starting methods. Okay, starters. Then finally, losses and efficiency calculations. Okay, losses and efficiency calculations. So these are the topics I am going to cover in this marathon session. 2 topics I am not going to cover here, that is armature reaction and commutation process, which is a vast theory part. Okay, and there are very less number of questions about armature reaction and commutation process in the earlier GATE exams. That's why I'm not picking up that. I'm taking the important topics where you can definitely expect questions in GATE examination. Okay. So without wasting our time, let's move through the basics first, and then we will figure out the EMF equation of a DC generator. Every topic I will try to solve numerical questions, okay, so that it will be easy for you in your final examination. Okay, right. So hope there were no issues in the live streaming. Just let me check. No issues in the live streaming. Okay, I think everything is clear, right? Okay, so all right, so let's start with the basics of DC generator. Okay, so you need to understand one thing: DC generator and a synchronous generator will work on the same principle, that is Faraday's law of electromagnetic induction. Generally, what a generator will do, generator is a machine which converts mechanical form of energy into electrical form of energy, right or not? Okay, so you will give mechanical power from a prime mover, and that mechanical power will interact with magnetic field inside the machine, so that electrical power will be generated. And both DC generator and synchronous generator will work on the same principle. Okay, what is the principle? Faraday's law of electromagnetic induction. Okay, Faraday's law. Now see, according to this Faraday's law, whenever a conductor is moving in a time invariant magnetic field, it will experience changes in flux linkages, so that an EMF will be induced inside the machine. Okay, the point is we need time invariant magnetic field. Time invariant magnetic field. So what is mean by time invariant magnetic field? Time invariant means it is constant with respect to time. Okay, so that means if you take the flux on y-axis and the time on x-axis, then the magnetic field is going to be constant with respect to time. Such type of magnetic fields are known as time invariant magnetic field. Okay, and you can get this time invariant field by exciting the field system with DC current. because what is the relation between flux and current? We know flux formula. Okay, flux is always equal to mmf divided by reluctance of the magnetic medium, correct? And what is mmf? Mmf is equal to number of turns into current divided by reluctance. Now, according to this formula, the field flux is directly proportional to current carried by the conductor. Therefore, I can write flux is directly proportional to current. And what type of flux we need? Time invariant field, that is a DC flux. And I know DC flux can be created by exciting the magnetic system using DC current. Okay, if the current is DC, automatically the flux is also going to be DC. That is a time invariant magnetic field. That is why in a DC generator and synchronous generator, the field winding is always excited using DC current only. Understand? Okay. Now, what Faraday's law states that in this time invariant magnetic field, you move a conductor, then definitely EMF will be induced across the conductor. Okay, that means what I need to do, you take a conductor of length L and you move the conductor with a velocity V in a magnetic field of density B. If all these three conditions are satisfied, then an EMF will be induced across that conductor, and the magnitude of that induced EMF is BLV sine theta. Got it? Okay, you might have learned about this equation many a times. And here theta is nothing but the angle between flux lines and conductor movement. Okay, suppose if the angle is 90 degrees, then maximum EMF will be induced. If it is 0 degrees or 180 degrees, there won't be any induced EMF. This is the operating principle of both DC generator and synchronous generator. Okay, very simple. You take a magnetic field which is a time invariant and you move a conductor in that time invariant field, automatically EMF will be induced. Okay, and this particular induced EMF is known as dynamically induced EMF. We call it as dynamically induced EMF. So there are two types of induced EMFs, dynamically induced EMF and statically induced EMF. Dynamically induced EMF means the EMF induced across a conductor using a time invariant magnetic field, just that what we discussed right now. Okay, but statically induced EMF means it is the EMF induced using a time varying field that we will study in transformers and induction machine. Dynamically induced EMF we will mostly see in DC generator and synchronous generator. All right. Okay. And now point is, how do you understand the principle of this dynamically induced EMF? Okay. So important thing is magnetic field is required and movement of conductor is required. Okay. So let us select a simple magnetic field. I am selecting a north pole here and a south pole here. Got it? And flux will always flow from which pole to which pole? North pole to south pole. Let's say there are number of flux lines available like this. Okay, so I am assuming some finite number of lines. Let us say there are 5 flux lines. Okay, now in this magnetic field we have to move a conductor. Okay, just assume that we take a conductor here. Imagine the conductor is right now on the 3rd flux line. You have to move the conductor with the help of mechanical energy. Okay, so let us assume that a conductor was moving in upward direction. If a conductor was moving in upward direction, right now the conductor is linking which flux line? 5-3. Next time the conductor is moving in upward direction and it will link 5-4. Next time it will link 5-5. Therefore, you see the conductor was linking same flux line every time or changing its changing, yes or not? Initially it is linking 5-3, next 5-4, next 5-5. Therefore, there is a change in flux. That change in flux is responsible for the production of EMF. Because what Faraday's law states is that induced EMF is dependent upon change in flux. And that change in flux will create the magnetic field. Sorry, the induced EMF. And you understand the similar type of induced EMF we can also produce in one more way. See that? Okay, let us once again consider we have 2 magnets, a north pole here and a south pole here. Flux will always flow from north pole to south pole like this. And the number of flux lines are there, 5-1, 5-2, 5-3, 5-4 and 5-5. And just now assume that there was a conductor again on the 3rd flux line. Okay, but this time what I am doing is I am not going to move the conductor, guys. I will keep the conductor stationary. Instead of moving the conductor, what I am doing is I am moving these poles in downward direction with a velocity v. Tell me, guys, if the poles are moving in a downward direction, along with poles, can I say flux lines are also moving in a downward direction? Therefore, which flux line is right now linking the conductor? Phi 3 was linking right now. And next time, the flux lines are going in downward direction. So next time, phi 4 will come down and link the conductor. Next phi 5 will come down and link the conductor. Therefore, can I say there is a change in flux once again? So initially phi 3, next phi 4, next phi 5. So same type of EMF will induce in the second case as well. Okay. So but what is the only difference you are observing in both cases? You see, in the first case, magnetic field is stationary, conductor was moving, right? But in the second case, conductor was stationary, magnetic field is moving. So this is the difference between a DC generator and synchronous generator. Both machines will work on the same principle, Faraday's law. Both machines require same type of magnetic field, time invariant field. But in DC machine, the conductor was moving, field is stationary. But in synchronous machine, conductor is stationary, field is moving. That is the only difference. Therefore, what is a stator part? That is a stationary part in DC machine. What is the rotor part? That is moving part. Yes, the stationary part is magnetic field, and the moving part is armature conductor. Armature conductor. Whereas in case of a synchronous machine, the stator part, the stationary part will be armature conductor, and the moving part is magnetic field. That is what we call it as rotating magnetic field in synchronous machine. Okay. So this is the only difference between DC generator and synchronous generator. Otherwise, both machines will work on the same principle. Okay. Now, which is difficult process here? DC generator process is difficult. Why? Because armature winding is on the rotor part. When the winding is rotating in nature, collecting the current from the winding is very, very difficult. Arcing phenomena will take place. Okay, so in case of a synchronous machine, there is no chance for arcing. Why? Because armature winding is on the stator part. When the winding is on the stator part, while you try to collect the current from that winding, arcing does not create because it is stationary winding. But in DC machine, arcing will definitely come into picture because the winding is rotating in nature. Now, even though arcing is created, why we are still using this rotating armature winding in a DC machine? Yes, the only reason is to satisfy commutator and brush system action. Okay, there is a special device in DC machine known as commutator and brush system, and that commutator action is possible only when armature winding is on the rotor part of the machine. Got it? Yes. So this is the basic difference between DC generator and synchronous generator. Okay, right. Now, let us move to the next concept here. Working of DC generator. Okay. So I'm moving little quickly because we can't spend so much time on each and every concept. Okay. It's not like a regular classroom course. It's a quick session. Okay. So I hope you are following, right? Let's move to the next concept. EMF in DC generator. Okay, so once again, I will be considering a 2-pole DC generator. You can take 4-pole, 6-pole, any number of poles, right? Magnetic field is always moving from north pole to south pole, right? Okay. Now, in this magnetic field, I have to move a conductor with the help of mechanical prime mover. So when I said a prime mover is rotating the conductor, there are two chances. You can rotate the conductor either in clockwise direction or in anti-clockwise direction. So I am assuming the conductor is rotating in clockwise direction. Imagine the conductor was driven in clockwise direction. So let us say the conductor started its movement at this position. Let us say position number 1. After 90 degrees, the conductor will come to position number 2. After 90 more degrees, conductor will come to position number 3. 90 more degrees, conductor will come to position number 4. 90 more degrees, conductor will come to position number 5. Now, in all these 5 positions, we have to find out the magnitude of induced EMF. And what is the formula for induced EMF? I told you already, BLV sine theta. Can I say the magnitude of induced EMF will depend upon this angle theta? And that angle theta is the angle between conductor movement and flux lines. It is the angle between flux lines and conductor movement, right? So if you find out the polarity, magnitude of induced EMF at every position, you will get 0 EMF at position 1 as well as at position 3. Why? Because at position 1, you can see the flux lines are moving from north pole to south pole, guys. Flux will always go from north pole to south pole. Conductor was also moving in the same direction, clockwise direction. Okay, therefore the angle is 0. That's why induced EMF is 0. But at position 2, you see conductor was vertically moving in a downward direction. Magnetic field is from north pole to south pole. The angle is 90 degrees. So maximum EMF will be induced. Again at position 3, 0 EMF. Position 4, maximum EMF. Okay. So position 1 and 3, no EMF. Position 2 and 4, maximum EMF. And once I told you position 2 and 4 are having a maximum EMF, let us try to find out the polarity of that maximum EMF. How to identify the polarity of induced EMF? Fleming's right hand rule. By using Fleming's right hand rule, you can find out the polarity of induced EMF. And according to Fleming's right hand rule, you see the first 3 fingers of the right hand must be placed in a mutual perpendicular direction. This is thumb, this is point finger, this is the central finger of the right hand. Thumb will always indicate the direction of a conductor movement. Point finger will always indicate the direction of magnetic field. And the central finger will always indicate the polarity of induced EMF. And remember guys, this rule is valid in all rotating electrical machines, not only DC machine. So let us figure out the polarity of induced EMF at position 2 and 4, because 1 and 3 anyway don't have any EMF. So if I look at position 2, can I say the conductor was moving in a downward direction? Just a moment, guys. Okay, so at position 2, the conductor was moving in a downward direction. Magnetic field is from north pole to south pole. Therefore, what my central finger was showing out of the plane, right? So therefore, this is a dot polarity. At position 4, conductor was moving in upward direction. Magnetic field is north pole to south pole. Now my central finger was showing into the plane. This is cross polarity. Therefore, you tell me position 2 and position 4 are offering 2 opposite polarities or 2 same polarities, 2 opposite polarities. Okay. And how do you represent 2 opposite polarities mathematically? Plus and minus only. Therefore, if you assume this cross is a positive polarity, this dot will become negative polarity. Or you assume this cross is a negative polarity, then this dot is going to be positive polarity. So keeping these points in mind, if I draw the waveform by taking the position of the conductor on x-axis and the induced EMF on y-axis. Okay, and you see one complete revolution, we have 5 positions. 1, 2, 3, 4 and 5. Understand? And you tell me at position 1 and 3 anyway the EMF is 0. But at position 2 we have dot. I am assuming cross is positive, therefore dot is negative. Therefore at position 2 we have a negative maximum. At position 4 we have a positive maximum. And if you combine all these points, you are going to get a, yes, it looks like AC voltage or DC voltage. Definitely it looks like AC voltage. See, our machine is a DC generator, but what type of voltage is induced? AC voltage is induced. Now, there is a necessity here to convert that AC voltage to DC voltage. That is what is going to be done by commutator. By using the help of a commutator and brush system, this AC induced voltage can be converted to DC voltage. Therefore, the summary point is, even though our machine is a DC generator, what type of voltage will be induced inside armature? AC voltage will be induced. And the frequency of this AC voltage will be equal to P into N divided by 120 Hertz. Is it the same frequency at which voltage is induced in synchronous generator? Yes. and the same frequency is valid even in DC generator as well. Got it? And where P is number of poles, N is the speed at which the machine was rotating. Understand? Okay. That's it. This is about the procedure of EMF induction in case of DC generator. And you see two important axes I am going to discuss in this particular diagram. One is the axis which is passing through position number 1 and position number 3. This is known as magnetically neutral axis or interpolar axis. Can I say whenever conductor is along this axis, how much EMF is induced? Zero EMF. Got it? Okay. Next, let us say one more axis which is passing through position number 2 and position number 4. We call it as direct axis of the machine or polar axis of the machine. And you tell me whenever conductor was rotating, and when the conductor was along this particular axis, how much EMF is induced? Maximum EMF is induced. That is known as direct axis or polar axis of the machine. Okay, so whenever conductor is along the interpolar axis, EMF is equal to 0. Whenever conductor is along a polar axis, the EMF is going to be maximum. Got it? So this is about EMF induction in a DC generator. Summary is, even though machine is a DC generator, whenever conductor was rotating, AC voltage will be induced inside armature winding, and to convert that AC voltage to DC voltage, we will use the help of commutator. Okay, fine. Now the point is, what is the magnitude of this induced EMF? Okay, that is what we are talking at, known as EMF equation. EMF equation in DC generator. Let's say it is EG. Okay. So now remember, a DC generator will have many number of conductors inside armature, and I told you armature is a rotating part. Okay. Magnetic field is stationary. Remember, in case of DC generator, the stator part is magnetic field. Okay. And the rotor part is armature winding. Armature winding. And remember, this armature winding will have a number of conductors. There are many conductors available, and when these conductors are rotating inside the magnetic field, EMF will be induced across every conductor. Okay, and the magnitude of EMF across each conductor. Okay, first let us find out EMF per each conductor. I am not going to do any derivations, guys. We don't have that time. Okay, I will directly write down the formulas. So EMF per each conductor. Okay, EMF per each conductor. Let us say small e is the word I am using. Yes, the EMF per each conductor in a DC generator is P phi omega by 2 pi. Okay, this is voltage per conductor. Okay, so remember, this is the formula for induced EMF across each and every conductor inside armature. Okay, I said voltage per conductor. And what P represents here? P obviously represents number of poles. Okay, and phi represents the field flux per pole. Field flux per pole. And omega is rotor speed in radian per second. Rotor speed in radian per second. Got it? And you can also write this formula when the speed is expressed in RPM. We will see that. Okay. Remember, this is the EMF only per one conductor. But I wanted to know what is the EMF of the entire machine, the total generated EMF. In order to understand the total generated EMF, let me take a small example. Okay. See the example. Consider I have a DC generator with total, let us say 10 conductors are there. Okay, practical machine may have 1000 conductors also. Okay, remember 10 conductors, and these 10 conductors are connected in two parallel paths, let us say. So when I said 10 conductors in two parallel paths, we will see on what factors the parallel paths are dependent on. So when I connect 10 conductors in two parallel paths, can I say each parallel path will have 5 conductors? Yes. Therefore, let us say this is a conductor number 1 with an induced EMF E. Next, this is connected in series with conductor number 2, conductor number 3, conductor number 4, conductor number 5. Okay. Similarly, can I say second parallel path will have 5 more conductors? Yes. Isn't it? 5 more conductors. And both are connected in parallel. Okay. Parallel means what? This positive polarity connected to each other. This negative polarity connected to each other. This is the final output generated EMF. This is the answer I need to know. This is the negative. What is this voltage? This is the total generated EMF out of this machine in this example. Okay. You tell me, first parallel path has how many conductors? 5 conductors in series. Therefore, what is the total voltage of the first parallel path? It will be 5 into E. Okay. Then what is the total voltage of the second parallel path? That is also 5 into E. And can I say that 5E, this 5E both are in parallel to each other? Then what is the final output voltage? The final output voltage will be 5 into E only. Yes or not? You may have any number of parallel paths. The overall output voltage will be same as each parallel path voltage. And here, what is this 5 is representing? Yes, I hope you can understand that 5 is representing total number of conductors or conductors in each parallel path. Conductors in each parallel path. Okay. Conductors in each parallel path. Okay. So, how can I write conductors in each parallel path? There are overall 10 conductors and there are 2 parallel paths. So, therefore, it is 10 by 2. Correct or not? So, what this 10 is representing? Total number of conductors. 2 is representing number of parallel paths. Okay. And in DC generators, total number of conductors are represented with the letter Z. Z is the letter we will use to represent total number of armature conductors. And the number of parallel paths are represented with the letter A. What A is representing? Number of parallel paths. And what is this small e? We already derived. Small e is nothing but voltage per each conductor. Voltage per each conductor. This is the total generated EMF equation of a DC generator. So let me write down in the next page. So Eg is equal to Z by A into, yes, what is small e? Voltage per each conductor. What is the voltage per each conductor? P phi omega by 2 pi. P phi omega by 2 pi. Now this is volt. This is the total generated EMF of a DC generator. Don't mix this formula like P phi omega Z by 2 pi A. Don't mix like that because every factor has a significance. What is this P phi omega by 2 pi is representing? This is the voltage per each conductor. And what is this Z by A? That Z by A is representing number of conductors in each parallel path. Okay, I can write number of conductors per each parallel path. Okay, number of conductors per each parallel path. So this is the total generated EMF equation of a DC generator. Okay, so what Z is representing? Total number of armature conductors. Armature conductors. And A is representing number of parallel paths. Okay, number of parallel paths. Now you please try to understand in this particular formula, omega represents the speed in radian per second. But sometimes in the exam, the speed may also be given in RPM. Of course, most of the times the speed will be expressed in RPM only. Yes, we have a relation between radian per second and RPM, right? What is the relation? Omega is equal to 2 pi n by 60. We know omega radian per second is equal to 2 pi n by 60, where n is RPM. And if you replace that omega in this formula will change again. Okay, so the formula will become Eg is equal to Z by A into P phi n by 60. This is one more formula. This is the formula we will use if the speed is expressed in RPM. This is the formula we will use when the speed is expressed in radian per second. When the speed is expressed in radian per second. Got it? All right. So this is about generated EMF equation of a DC generator. Now the crucial point we have to understand here is what this A is representing. Very important. That A represents number of parallel paths in armature winding. Why we are connecting conductors in number of parallel paths? Why don't we connect conductors in single parallel path? Why we need multiple parallel paths? What is the requirement? Why? Yes, the need is commutator action. I told you commutator is a sensitive element, guys. Okay, and when you are using a commutator, there is a chance of arcing. Okay, arcing is a serious issue. And if the arc is too high, there is a chance that the motor or generator may completely damage, and even the person who is operating that machine may get affected. Therefore, we wanted to minimize the arcing procedure, and that means without arcing, commutator has to work. And remember, in order to operate commutator without arcing, there are two types of armature winding designs proposed. One is lap connected armature winding design, another one is wave connected armature winding design. So you may have a doubt, sir, why we are using only these two designs? Why we are not using some other design? Means if you try to use some other design, arcing may create at the commutator surface. So to avoid arcing, only two designs are proposed. One is lap connection design, another one is wave connection design. Let's see the difference between the two. So let us first discuss about lap winding. Lap winding means number of parallel paths are equal to number of poles. That means if the machine has two poles, number of parallel paths are 2. If the machine has 4 poles, number of parallel paths are 4. Therefore, number of parallel paths are equal to number of poles. Okay. And if you are talking about wave winding, the other type of winding I told you, in case of wave winding, the number of parallel paths are always 2 and they are independent of poles. Whether the number of poles are 2 or 4 or 6 or whatever may be the number of poles, the number of parallel paths are only 2. That is wave winding. Got it? And again, this lap winding and wave winding are subdivided into different classifications. You see, we can have simplex lap winding. Simplex lap winding means number of parallel paths are just equal to poles only. We can also have duplex lap winding. Duplex lap winding means the number of parallel paths are equal to 2 times of poles. We can have triplex lap winding. Triplex lap winding means number of parallel paths are equal to 3 times of poles. We can also have a quadruplex lap winding. Quadruplex lap winding, the number of parallel paths are 4 times of poles, and the order will continue like that. Okay, so you can use simplex, duplex, triplex. It depends upon size of the machine. Suppose in the particular question given in the exam, if there is no information about plex number, they simply said lap winding, there is no information about plex number, then by default it is simplex only by default. Okay, right. Similarly, in the wave connection also, we can have different types of connections. We can have simplex wave winding. Number of parallel paths are just equal to 2. We can have duplex wave winding. Number of parallel paths are equal to 2 into 2. We can have a triplex wave winding. Number of parallel paths are 3 into 2, and the order will continue like that. Quadruplex means 4 into 2. And if there is no information about plex number, by default it is simplex wave winding only. Got it? Okay. So these are the 2 types of armature winding designs that we will use in DC generators. Okay. An important thing, this is the EMF equation of DC generator when the speed is in RPM. Okay. Hope there are no issues in the streaming. Fine. So now let us see the next observation. Next observation is armature winding resistance. Okay. Before discussing about armature winding resistance, let us understand generated current as well. Generated current, we also call it as armature current. Generated current or armature current. So let us take a simple example. Consider we have a 4-pole lap connected machine having, let us say, 8 conductors. Okay, you can take 800 conductors also, no problem, right? So when I said lap connection, how many parallel paths will be there? Number of parallel paths are equal to number of poles. 4 poles, 4 parallel paths, and overall 8 conductors. Therefore, can I say each parallel path will have 2 conductors? Yes. This is the first parallel path having 2 conductors. Second parallel path having 2 conductors. Third parallel path having 2 conductors. Fourth parallel path having 2 conductors. All are connected in parallel. This is how the machine is generating the EMF. Okay. Now the point is, the machine is generating the EMF fine, but will it generate the current? No. Why? Because it looks like open circuit. If the machine was not connected to any load, the current cannot be generated. The machine will be able to generate the current only when the load is connected. So imagine a load was connected here. So the moment when the load was connected, automatically the current will be generated, and that current is what we call it as armature current of the machine. So armature current means it is the total current generated by the machine only when the load was connected. Got it? And you tell me this armature current was coming from one parallel path or 4 parallel paths together? 4 parallel paths together. Assume the current passing through each parallel path is small I. So could you tell me what is the KCL equation? So the total armature current is equal to 4 into small I. From this, small I is equal to Ia by 4. Correct? And what is that 4 is representing right now? Number of parallel paths. Therefore, the generalized equation is Ia by A. So what is that small I is representing here? The small I is nothing but current passing through each parallel path. Ia is the total current generated by the machine. Got it? And you tell me again, in each parallel path we have only one conductor or number of conductors in series. You see here 2 conductors are in series. When I say the entire parallel path current is a small I, what is the current passing through each conductor also? Small I only. So current passing through each parallel path or current passing through each conductor, both are absolutely same. Got it? And this is small I, Ia by A. Correct? Okay. So now you have idea about total generated EMF and the total generated current. Therefore, what is the total generated power? Yes, the total generated power is equal to generated EMF multiplied by generated current. This is the power that is generated by the machine. Simple. Okay, this is about generated current. Now, one more point I would like to discuss here. Okay, let me go to the next page. Yes, armature winding resistance. This is a simple topic. Armature winding resistance, RA. Generally, you tell me, in order to design the machine with higher efficiency, we will always use low resistance winding or high resistance winding. Yes, we always use low resistance winding. Okay, generally copper, aluminum windings we will use. And here you tell me, when I said armature, number of conductors are there and only one conductor will offer resistance, or every conductor will offer some resistance. Every conductor will offer some resistance. Then how to find out the resistance of the overall armature winding is the next question. So I will take the same example again. A 4-pole lap connected machine, let us say 8 conductors are there. Therefore, each parallel path will have how many conductors? 2 conductors. This is the first parallel path, second parallel path, third parallel path, fourth parallel path. So every conductor will have every parallel path has 2 conductors. Let us say resistance of each conductor is small r. Small r is the resistance of each conductor. Now what is the overall armature resistance is the question. What is the overall armature resistance? Is it looking like every parallel path resistance is 2R because R and R in series? Therefore, what is the resistance of first parallel path? 2R, 2R, 2R and 2R. Isn't it looking like 4 2R resistors connected in parallel? When I said 4 2R resistors connected in parallel, what is the overall armature resistance? 2R divided by 4, correct? And what that 2 is representing? Can I say the 2 is representing number of conductors in each parallel path? That is nothing but Z by A. Isn't it? What Z by A is representing? Number of conductors per each parallel path. What is that small r? Resistance of each conductor divided by, what is that 4? Isn't it 4 nothing but number of parallel paths A? It is A. Therefore, what is the final answer? Numerator Z into R divided by A into A, it is A square. This is the formula for armature resistance in a DC generator. So from this formula you can understand armature resistance is inversely proportional to parallel paths or inversely proportional to square of the parallel path, inversely proportional to square of the parallel path. Understand? Clear? Right. Now, that's all. These are the 3 formulas we developed so far. Generated EMF, generated current, generated power, and this is armature resistance. Okay. Now we will try to answer some simple questions related to the EMF equation of a DC generator. Okay. Just to look at the formula once again, we will solve numerical questions. Sajin, you asked it out. What is the difference between right hand rule and left hand rule difference? See, Fleming's right hand rule is used to identify the polarity of EMF, and Fleming's left hand rule is used to identify the direction of force. Force, experienced by a conductor. Lorentz force equation. According to Lorentz force equation, whenever a current carrying conductor is placed inside a magnetic field, it will experience a force. And the direction of force we can identify using Fleming's left hand rule. Okay, right. Fine, guys. So without wasting time, let's solve some questions related to the EMF equation of DC generator. Okay. Fine. Okay, so here we go. The first question. Just read the problem. A 6-pole 1200 conductor DC generator rotating at 1000 RPM, operating at a flux per pole of 20 milliweber. It is feeding a load of 50 kilowatt. Determine, first question, total generated EMF. Yes, first question, total generated EMF. Second question, total generated current. Third question, current through each conductor. And please, you need to answer this question for both lap connection and for wave connection separately, so that we will understand the difference between both windings easily, right? Okay. So first let us note down the data. Number of poles are 6. Overall conductors are 1200. Poles are 6. Number of conductors are 1200. Okay. And 1000 RPM speed. N is equal to 1000 RPM. Okay. And flux per pole was given. Flux per pole was 20 milliweber. 20 milliweber. And it is feeding a load of 50 kilowatt. So the power information is also given. The power is equal to 50 kilowatt. Actually, that is the load power. There are no information about losses, so neglect losses. Therefore, load power or generated power remains the same. Now you have to calculate generated EMF, generated current, and current through each conductor. And I need to answer this question for lap connection as well as wave connection. So let me divide the page into 2 parts. So this side I will consider lap connection, and this side I will answer that question for wave connection. Lap connection means how many parallel paths? Number of parallel paths are equal to number of poles. In the question I gave you 6 poles, therefore 6 parallel paths. So let us find out generated EMF first. Yes, what is the formula for generated EMF? Z by A into P phi N by 60. And how many conductors are given? 1200 conductors are given. 1200. Can I say number of parallel paths, number of poles will cancel because both are same only. Therefore, the denominator is 1. And flux per pole, 20 milliweber, that is 20 into 10 power minus 3. and speed is 1000 rpm, 1000 by 60. Okay, you can use calculator. Even without calculator also you can answer. This is easy question. 1000 10 power minus 3 will cancel. 20 will cancel 3 times here. 3 will cancel 400 times. Therefore, the answer will be 400 volt. So this is the generated EMF if the machine is which connected? Lap connected. Now answer the same question if the machine is wave connected. Right side. Okay, wave connected. Same formula. Eg is equal to Z by A into P phi N by 60. See, the only thing that will change here is number of parallel paths. In wave connection, how many parallel paths? 2 parallel paths. Therefore, number of conductors are 1200. Parallel paths are only 2. Poles are 6. Flux per pole is 20 milliweber. Speed is 1000 rpm by 60. Okay. So take your calculator and solve it. You will get generated EMF for wave connection as well. Okay. So if I try to simplify, 1000 and 10 power minus 3 will cancel. 20 will cancel 3 times here. 3 into 2, 6. 6 will cancel. Overall answer will be 1200. So therefore, the generated EMF with wave connection is 1200. So what is the conclusion from this problem? You can see when it is lap connection, voltage was 400, but when it is wave connection, voltage was 1200. Therefore, can I say lap winding is used for low voltage applications, wave winding is used for high voltage applications? Yes. Now let us try to answer the second question. What is the second question? Total generated current we have to calculate, that is IA. To calculate IA, I will use this power information. Okay, yes. What is the formula for generated power? I discussed. Generated power is equal to Eg into IA, right? From that, IA is equal to generated power, 50 kilowatt the machine has to generate. I am neglecting losses right now. By generated voltage was 400. You will get the answer here. Okay, take the calculator and solve it. And similarly in this case also, same formula, generated power is equal to generated voltage into generated current. But this time the voltage was 1200 volt. Take the calculator and calculate what is the current value. So you will get armature current in both cases. Whenever you got answer, you try to reply in the chat box so that others also can see your answers and you can check easily, okay, whether your answer is correct or not, right? Yes, I got few responses. In case of lap connection, 125 ampere. Right? So that is 50,000 by 400. Yes, 125 ampere. In case of wave connection, you'll get a different answer. 50,000 by 1200. So 41.66. Therefore, what is your observation from the second problem? From the second problem, you can understand lap connection means higher current value, wave connection means lower current value. Therefore, final observation is lap winding is used for low voltage and high current applications. Wave winding is used for high voltage and low current applications. Got it? Yes. But we have one more question to answer, that is current through each conductor. I just told you current through each conductor or each parallel path both are same. Small I is equal to IA by A. So let us answer the last question also. Small I is equal to IA by A. What is IA? In case of lap connection, the total armature current was 125. 125 and there are 6 parallel paths, right? So what is 125 by 6? 20.83. Got it? This is the current passing through each conductor in a lap connection. Similarly, you try to find the same answer in wave connection. But in wave connection, what is the total armature current? 41.66. 41.66. And only 2 parallel paths will be there. So you will get the same answer, 20.83 ampere. Therefore, what is your conclusion from the last question? From the last question, we can conclude that even though total generated currents are different in both machines, but current passing through each conductor is always the same, right? current passing through each conductor is same whether it is lap connection or wave connection. Am I correct? Yes. So summary, lap connection is used for low voltage high current applications. Wave connection is used for high voltage and low current applications. And whether it is lap or wave, current passing through each conductor is always same. Current passing through each conductor is always same. Got it? Okay. So let's take one more problem. All right, go through this problem, guys. A 4-pole lap wound DC generator has 300 coils with 4 turns per each coil. The voltage per each conductor was 2 volt. Then what is the total generated EMF is the question. They said very clearly 4-pole lap connection. So number of poles are 4. Lap connection, that means the number of parallel paths are also 4. Overall 300 coils are there. This time rather than giving conductors information, coils information was given. Total coils are 300. Okay. And every coil has 4 turns. Every coil has 4. First of all, what is mean by one turn? One turn means it looks like this. This is what is mean by one turn. Okay. That means you tell me, just a moment. So you try to understand one turn means how many conductors are there. This is one conductor. This is another conductor. Therefore, one turn means 2 conductors are there. But our question is 4 turns in each coil. When I said 4 turns are there in each coil, see, this is one turn. This is the second turn. This is the third turn. This is the fourth turn. This is one coil, guys. One coil. Okay, this is one turn, this is one coil. Therefore, you tell me, according to the given question, 4 turns are there in every coil. 4 turns means, will you tell me how many conductors are there? You can easily understand 8 conductors are there. Okay, because one turn means 2 conductors, 4 turns means 8 conductors. Like that, overall 300 coils are there. Therefore, could you tell me overall how many conductors are there? There are 300 coils. Every coil has 4 turns and every turn will have 2 conductors. Therefore, I can say 2400 conductors are there in the machine. Correct? 4 to 8, 8 into 300. It was 2400 conductors are there in the machine. Okay? The moment you know the number of conductors, you can easily find out generated EMF because voltage for each conductor was already given. What is the generated EMF formula? Generated EMF is equal to Z by A into P phi N by 60. I told you already this P phi N by 60 is nothing but voltage per each conductor. Am I correct? And overall, how many conductors are there? 2400 divided by how many parallel paths? 4 parallel paths because it is a lap connection, right? Into voltage per each conductor was 2 volt, right? Voltage per each conductor was 2 volt. Isn't it? So therefore, 1200 volt is the answer. 1200 volt is the answer. Remember guys, this is important. One turn means 2 conductors will be available. Like that, 4 turns means 8 conductors will be available. In each coil, 8 conductors will be available. Got it? Clear? 8 conductors will be available. Fine. This is about the generated EMF of the given question. Clear? It's a 1 mark type model. Okay. Right. Now let us figure out one more question. Yes, read the problem. A 6-pole lap wound DC generator has 240 coils of 2 turns each. Resistance of each turn is 0.03. Armature is 50 centimeter long and 40 centimeter diameter. Air gap flux density was 0.6 Tesla under each pole. Pole shoes are covering 2/3 of pole pitch. And for armature speed of 1200 rpm, find what is the generated EMF, first question. What is the armature resistance, that is the second question. This is a 2 marks model, guys. It is a 2 marks model. Okay, important. First understand the data. It was a 6-pole machine, lap connected, that means the number of parallel paths are also 6. Overall 240 coils are there. Every coil has 2 turns, and again every turn will have 2 conductors. So first to find out overall how many conductors are there. There are 240 coils. Every coil has 2 turns. Every turn has 2 conductors. Am I correct? Therefore, number of conductors are simply 240 into 2 into 2. Okay. So let us see. Use calculator wherever it is required. So 240 into 2 into 2. So 960 conductors. 960 conductors overall. Okay. Next, resistance of each turn is given. Each turn, we know one turn means 2 conductors. Okay. Let us say resistance of this conductor was R, this conductor was R. So the 2R value was given for you, 0.03 ohm. Therefore, what is the resistance of each conductor? 0.015 ohm. Correct? Next, armature length is given 50 centimeters. Diameter was also given, because our machines are, circular cross section and cylindrical structured machines, right? This is how the machine shape will be. Got it? And this diameter was given. What is the diameter of the armature? The diameter of the armature was 50 centimeters. Okay, and the axial length was axial length is 50, diameter was 40. Okay, so this diameter was actually 40 and this length is 50, so that you can calculate the area of this entire machine. Okay, and flux density was 0.6 Tesla. Okay, and pole shoes are covering 2/3 of pole pitch. You know that if you go through the construction part of the machine, imagine this is the rotor part of the machine, and suppose if the machine has, let us say, 2 poles or 4 pole or 6 pole. Okay, generally poles structure will be like this. Imagine if it is a 2 pole machine. This is how the poles looks like in DC machine, and this is what we call it as pole shoe length. And if you draw a line which is like this, this is known as interpolar axis line. Now, if I ask you a question, what is the length from interpolar axis to interpolar axis? This is known as 1 pole pitch. 1 pole pitch. Out of that 1 pole pitch, a pole shoe is covering only 2/3 of the pole pitch. That was given in the problem. Okay, pole shoe covers only 2/3 of the pole pitch. That means if you assume the entire area of the machine is A, what is the area covered by pole pitch? Only 2/3 of this area is covered by pole pitch. If the total area of the machine is A, pole shoes are covering only 2/3 of the total area. That is the effective area covered by pole pitch or pole shoes. Got it? So now the important thing is the flux density was given in the problem. Using this flux density, you have to find out what is the flux offered by every pole. Then only you can find out generated EMF, because what is generated EMF formula? Z by A into P phi N by 60. In that phi is flux per pole. Therefore, using this density, you try to find out flux per pole. From that, you can find out what is the EMF equation. Okay, so let us see what is the relation between flux density and flux. We know flux density is equal to total flux per area of the machine. Total flux per area, right? That is flux density. Suppose if there are P poles in the machine, every pole is creating a flux phi, then what is the total flux? P phi. Remember here, phi is flux per pole, P phi is flux for the entire machine. Okay, right? By area. For a circular cross section and cylindrical structure machine, what is the formula for area? Area will be equal to 2 pi RL, right? Where is R is the radius of this circular cross section, L is the length of the core. They said very clearly diameter was 40 centimeter, so area is 20 centimeter, sorry, radius is 20 centimeter, length is 50 centimeters, so substitute the area 2 pi r l. Okay, but remember this is the total area and I have to multiply this total area with 2 by 3. Why? Because I told you pole shoes are not covering the entire area of the machine, they are only covering 2/3 of the area. Okay, 2/3 of each pole pitch. Suppose if that information was not given in the problem, then you assume that pole shoes are covering the entire pole pitch, then you need not to multiply with the 2 by 3, you just multiply with 1. Okay, so this is the total area, multiply with 2 by 3 means effective area. So let us substitute everything. So the given question, 6 poles are there. I don't know what is the flux per pole, by 2 pi into what is the radius, 20 centimeter, that is 20 into 10 power minus 2. Length is 50 centimeter, 50 into 10 power minus 2, multiplying with 2 by 3. This is equal to density, and in the given question density was 0.6. So if you solve it, you will get flux per pole in Webers. The moment you got flux per pole, I think calculating generated EMF is not a big task, right? So solve it and find out what is a flux per pole first. Yes, find out what is a flux per pole. 0.6 into 2 pi, okay, 20 into 50 into 2 by 3 into 10 power minus 4. I am also solving just like you. If I made any calculation mistakes, please let me know, okay, in the chat box. So this is the flux per pole I am getting, 0.0418 Webers. Okay, the moment I got flux per pole, I can find out generated EMF now. What is the formula for generated EMF? Let me go to the next page. Generated EMF is equal to simply Z by A into P phi N by 60. Okay, how many conductors are there? We already found the number of conductors are equal to 960 by, I think it is lap connection or wave connection. Lap connection means A and P will cancel because A is equal to P only, and we just found flux per pole value 0.0418. And what is the speed of the machine? Is the speed given? It must be given. Yes, 1200 rpm, right? 1200 rpm. So 1200 divided by 60. So let us do it. I am getting approximately 804 volt. Am I correct? Okay. So if I calculate flux per pole correctly, then my final answer is also correct. Okay. I'm not too good at calculator. I hope you can help me, right? You solve it, this you will get flux per pole. Yes, this is correct. And I am getting 804 volt, right? Yes, 804. This is correct. Fine. This is the first question, guys. What is one more question in the problem? Calculate armature resistance. I hope you can easily calculate armature resistance because each conductor resistance was already available, right? So then what is the formula for armature resistance? Armature resistance formula Z into R by A square. Okay, so Z value 960, each conductor resistance 0.015 and 6 parallel paths are there. Okay, so 960 into 0.015 by 36. So I am getting 0.4 ohm. That is the resistance of entire armature circuit. So this is a 2 marks model. Okay, so the only point is instead of giving a flux per pole directly, they gave you flux density in the problem. Okay, and using that flux density, we have to find out flux per pole. Okay, we have to find out flux per pole. And remember, pole shoes are not covering the entire machine, they are covering 2/3 of the pole pitch. That's why the total area must be multiplied with 2 by 3. Okay, that's all. So this is about EMF equation of a DC generator. Okay, now let's move to the next topic, electromagnetic torque equation. Electromagnetic torque equation. So I would like to develop this electromagnetic torque equation in a simple terms by using power information, right? First of all, there are two types of torques in any rotating electrical machines, guys. One is mechanical torque, another one is electrical torque. Okay, as you know, what generator was doing? Generator was converting mechanical form of energy. We will give mechanical power as the input, and it will convert to electrical energy, which is output. Therefore, this mechanical power will create one torque. We call it as prime mover torque. Okay, and this electrical power will create one more torque. We call it as electromagnetic torque. Under steady state conditions, both these torques will balance each other. But we wanted to know which torque will support the machine rotation and which torque will oppose the machine rotation. Okay, always remember, input energy or input power will always support the rotation of the machine. Output, indirectly the load will always oppose the machine rotation. So imagine this is the rotor shaft of a generator. This is the rotor shaft, and assume the generator was rotating in clockwise direction at a speed omega radian per second. Now the question is, which torque is supporting this machine rotation, which torque is opposing this machine rotation? As I said, a simple shortcut, I am not proving. Simple shortcut is, input torque will always support, output torque will always oppose. Any machine it may be. Okay, here what is the input torque? Is it not prime mover torque? Yes, that will support. Mechanical torque will support. Output torque already, or you can say load torque, electromagnetic torque, that will oppose. This is applicable not only for DC generator, it is applicable for synchronous generator, induction generator as well. What if the machine is a motor? Suppose if the machine is a motor, what motor will do? Motor will convert electrical power to mechanical or mechanical power to electrical. It will take electrical power as input. It will develop mechanical power as output. Correct? This is the input, guys, in motor, and this is the output. And this input power will create a torque, that is electromagnetic torque. This output, the load. See here, mechanical torque is a load, right? Output is always a load. So we call it as load torque. Mechanical load torque. And now imagine this is the rotor shaft of a motor. Assume this motor was rotating in clockwise direction. So which torque will support the rotation and which torque will oppose the rotation? Input torque. Electromagnetic torque will support, output torque. Mechanical load torque will oppose. That's it. And this is true for any rotating electrical machine. As I said, any generator, any motor. Okay, it may be DC generator or DC motor, or synchronous generator, synchronous motor. Okay, induction generator, induction motor. This is applicable for any machine. Clear? Now our interest here is to develop a formula for electromagnetic torque. See, to develop a formula for electromagnetic torque, I will use power equation. You all know that active power P is equal to 2 pi nt by 60. Am I correct? I hope you know this. Here 2 pi n by 60, is it not speed in radian per second? Therefore power is equal to omega into T. From this, the torque is equal to power divided by omega. Okay, power divided by omega. So therefore electromagnetic torque is equal to power generated by the machine divided by speed in radian per second. You remember what is generated power? Is it not Eg into Ia by omega? Okay, so therefore you can develop the torque equation of a DC generator by using this formula. And again we have a formula for Eg. Again, you remember what is Eg formula when speed is in radian per second? I can continue further. So therefore torque is equal to Eg into Ia by omega. I will quickly write down. Eg is equal to Z by A into P5 omega by 2 pi into Ia by omega. Omega will cancel. Therefore, the torque equation is Z by A into P phi Ia by 2 pi. Okay, this is the electromagnetic torque equation. Of course, you need not to remember this equation. I will tell you a simple formula to remember the equation. So, the generated power is equal to Eg into Ia. Okay. Also, you cross multiply this relation Eg into Ia, or generated power, is equal to torque into omega. Torque into omega. You just remember this equation, sufficient. Eg into Ia or torque into omega, important. So that means if you know voltage and current information, you can find out torque value. Got it? Fine. Now we will try to understand the equivalent circuit of a DC generator. Equivalent circuit of a DC generator. See, to understand the equivalent circuit of a DC generator, first of all, we must know how many number of windings are available in DC machine. Remember, there are 4 types of windings we will use in DC machine. First one, field winding. Okay, as the name itself is indicating, the purpose of this winding is to develop the field flux. Second one is armature winding. This is the winding who actually develops the EMF. Okay, EMF, current and power. And the third one is interpole winding. Fourth one is compensated winding. Okay, see, this interpole winding and compensated windings we will use in order to avoid armature reaction to neutralize armature reaction, and to improve commutation process. Okay, so these are excessive windings. Okay, interpole winding and compensated windings are used in order to neutralize armature reaction and to improve commutation process. Those are the 2 topics I am not discussing in this marathon session because there are very less number of questions from these 2 topics, but the topics are lengthy. Okay, that's why I wanted to avoid them. Fine. So in order to neutralize armature reaction, also in order to improve commutation process, we have to use these 2 windings. And remember, these windings are always connected in series with armature. Okay, so these windings are always connected in series with armature. These windings are connected in series with armature. That means they will carry which current? Obviously armature current, because they are connected in series with armature. Okay, right. Now let us develop the equivalent circuit of DC generator. Fine. Now we know DC generator is the, or DC machine, not generator, DC machine. DC machine is the only machine having a commutator and brush system. Whereas in other rotating electrical machines, we don't use commutator and brush systems. Only in DC machine we will use it, right? Now, to represent this machine has a commutator, we will draw a circle like this. See, the meaning of this circle is, yes, there is a commutator. And also we will represent 2 brushes. One will be positive brush, another one will be negative brush. Okay. And inside this commutator, now the machine will have armature winding. Okay. So the entire armature winding will have some resistance, that is armature resistance. We already discussed the formula for that. And the entire armature winding will generate some EMF. We call it as generated EMF. And the total armature winding will generate some current. We call it as armature current. Now this armature current will first go through interpole winding. I told you interpole winding and compensated windings are connected in series with armature. After interpole winding, next compensated winding is also connected in series with armature only. After these 2 windings, finally the load element will be available. This is the load. Okay. And whatever current is taken by the load, we call it as load current. and whatever voltage that will appear across the load, we call it as terminal voltage of DC generator. We call it as a terminal voltage. This is a generated EMF, but this is a terminal voltage. Therefore, can I say entire voltage generated by the machine cannot be received by load? Always there is some internal voltage drop, definitely. So what are the reasons for internal voltage drop? Armature resistance, brushes, intrapole winding, compensator winding, etc. Now one more winding is missing. What is that? Field winding. As I mentioned already, what is the purpose of field winding? To develop field flux. Which type of flux is required in DC generator? Time invariant flux. And in order to create time invariant flux, we have to excite field winding with AC supply or DC supply. We have to use DC supply. So therefore, let us take a field winding here. This field winding must be excited using DC supply. We call it as a field voltage, and this current is known as a field current, and assume this winding will have some resistance known as field resistance. And remember, this field current is responsible to create field flux. Okay, right. This is the equivalent circuit of a DC generator. But remember guys, every time I don't draw these two windings. Why? Because they are in series with armature only. Therefore, what I can do is that I can include these two winding resistances within armature resistance only, right? Therefore, whenever I gave you any numerical question stating that armature resistance is, let us say, 0.5 ohm. If I say armature resistance is 0.5 ohm, that 0.5 is including armature winding, interpole winding, and compensated winding as well. Therefore, every time you need not to draw these two windings. Clear? Okay. So minimum two brushes are required. One is positive, another one is negative. And generally number of brushes are equal to number of parallel paths, but I don't want to go to that discussion. That will be pretty long discussion. Okay. Fine. So this is the equivalent circuit of a DC generator. Now once we know the equivalent circuit, now let us try to understand what are the different types of DC generators that we have. Okay. Let us see the types of DC generators. Remember, there are generally two types of DC generators. First one is separately excited DC generator. Separately excited DC generator. Second one is self-excited DC generator. Self-excited DC generator. And again, this self-excited DC generator is subdivided into three categories. One is shunt excitation. Okay. Second one is series excitation. And third one is compound excitation. Compound excitation. Okay, so we will see all of them. First we will discuss, first of all, what is meant by self-excitation, what is meant by separate excitation. See, the DC generators are classified into two types based on the method of field excitation. First of all, field winding require which supply? DC supply. Even our machine is also generating which current? DC current only. I told you after commutator everything is DC. Okay, so if I use machine generated current to excite this field winding, we call such machines as self-excitation machines. Rather than using machine generated current, what if I use some external DC source? Then we call it as separately excited DC generator. So there are two types. Separate excitation means a separate DC source is used. Self-excitation means machine generated current itself is used for field winding. Got it? Okay, now let us discuss separately excited DC generator first. So let's talk about separately excited DC generator. Okay, as the name itself, separate excitation, the field winding will be excited using external DC source. So this is the armature part of the machine having armature resistance and generated EMF. This is the generated current, armature resistance. Okay. I don't want to draw compensated winding and interpolar winding again because they are included within RA. So directly we can develop the load circuit. So this is the load resistance, load current, and this is the voltage across the load resistance, that is terminal voltage. Okay, and this is armature current. And as I told you, field winding will be excited using external DC source. Let us say this is the field winding excited using an external DC source. Let us call it as field voltage, and the current is known as field current, and resistance is field resistance. Now you can easily understand here there are two electrical circuits. One is a field circuit, another one is armature circuit. So we will write down the KVL equation for both field circuit as well as armature circuit. Okay, what is the KVL equation for field circuit? VF is equal to IF into RF. From this, IF is equal to VF divided by RF. Suppose if this external voltage is a constant battery, let us say. If it is a constant battery voltage, VF is a constant value. If VF is a constant value, field current IF is also a constant value, correct? If field current is a constant value, remember field flux also constant. Why? Because flux is always proportional to field current. Flux is always proportional to field current. Field flux depends upon field current, obviously. The moment I said field current is constant, indirectly field flux is also a constant value. Okay. So by default, separate excitation means field flux is a constant value. Unless you change this voltage, the flux does not change. Okay, next. Coming to armature circuit, what is the first observation, guys? Is it looking like a single loop? Therefore, what is the relation between armature current and load current? Both are same. So armature current is equal to load current. Next information, current was flowing from EG to VT or VT to EG, EG to VT. Therefore, EG is greater than VT, correct? Next, write down the KVL equation, start from EG. If I start from EG, where is the first voltage drop? Across armature resistance. Next voltage drop across brushes. After brushes, next voltage drop is across load. Therefore, the KVL equation is EG is equal to first drop across armature resistance, IA, RA. Next drop is across brushes, brush voltage VB. Remember, two brushes are there. Total brush drop is VB. After brushes, next voltage drop is across load, that is nothing but VT. This is the KVL equation, guys. But usually, this brush drop is very, very small. Therefore, you can neglect it. But sometimes in the questions, brush drop may also be given. 1 volt per brush or 1.5 volt per brush. Then you have to consider brush drop. Otherwise, you can neglect brush drop. If brush drop is neglected, what is the approximate equation now? Therefore, EG is equal to VT plus IA RA. This is the KVL equation for this particular generator. Apart from these circuit equations, you can also write some of the performance equations, guys. We already developed. What is EG formula? EG is equal to Z by A into P phi omega by 2 pi. Remember, this is a formula when speed is in radian per second. And here, guys, remember, this Z, pi, 2 pi, A, these are constant values once the construction of the machine is completed. So let us separate them like a constant, and we call that constant as armature constant represented with the letter Ka. If Ka is a constant value, what are the remaining parameters? Phi into omega. So this is a shortcut formula for generated EMF. Ka phi omega. What is Ka here? Where Ka is nothing but Z into P by 2 pi A. We call it as armature constant or machine constant. Okay. Next, what is the electromagnetic torque formula? Electromagnetic torque is equal to Z by A into, we proved already, right? P phi Ia by 2 pi. Once again, even in this formula also, you can separate this Z pi 2 pi A. That is again same armature constant. So therefore, it is Ka into phi into Ia. This is electromagnetic torque shortcut formula. And then we know power generated by the machine. Power generated by the machine is Eg into Ia or torque into omega. These three formulas are known as performance equations for DC generator. We call it as performance equations. Got it? So based on the formula, based on the information in the problem, you need to decide which formula to be used. Got it? So this is a separately excited DC generator. An important note point is, unless there is exclusively mentioned, you have to believe that separate excitation means flux is a constant value. Flux is a constant value. Got it? Yes. Yes. VB is the total brush drop, guys. Total brush drop. Suppose if each brush has 1 volt drop, then the total brush drop will be 2 volt. Okay. Yes. In generator, electromagnetic torque will oppose the rotation of rotor. Correct. Rohan Singh, that is correct. In motor, electromagnetic torque will support the rotation of rotor. Got it? Okay. This is about separately excited DC generator. Now let's talk about self-excited DC generators. I told you self-excited DC generators are again 3 types. We have shunt excitation, series excitation and compound excitation. Let us discuss about the circuit diagram of each and every generator. Okay, first let us discuss about shunt excited generator. Shunt excited DC generator. Okay, so first of all, shunt excited generator is a part, or it is a type of self excitation. So once again, let me draw the armature circuit. This is the armature circuit diagram. Generated EMF, generated current, armature resistance. Okay, now in shunt excited generator, what happens is, out of this total armature current generated, a part of current is taken by field winding. A part of current, I said a part only, a part of the current is taken by field winding. Remaining current will be delivered to load. Remaining current will go to the load circuit. That means we are taking current tapping from the machine or voltage tapping from the machine, current tapping from the machine. That means the field winding must be connected in shunt with armature. So this is how the field winding is connected. Field resistance and the current is field current. And this is the load current that will go through the load resistance. Okay, and voltage across the load, we call it as terminal voltage. Got it? So this is the circuit diagram of a shunt excited DC generator. You don't need external DC voltage source right now. Got it? Now one point I would like to discuss here. See, as this particular winding is connected in shunt to the machine, what is the copper loss in this resistance? I wanted to express copper loss in field resistance. Remember, when the element is in shunt, don't write copper loss as I square into R. You have to write copper loss as V square by R, because it is a shunt element. Got it? And always our aim is to reduce the losses or increase the losses, reduce the losses. Therefore, in order to reduce this copper loss, we have to design this shunt field winding with high resistance. Okay, this winding must be designed using high resistance. Okay, if the resistance is high, then only copper losses will be less. As this resistance is very high, field current is very, very low. As the winding resistance is high, less current will go through field winding. Okay, clear? Now, let us write down various KVL and KCL equations. Suppose if armature current is, let us say, 100 ampere, this field current may be 1 ampere or 2 ampere only. Why field current is such a low value? Because field resistance is high. Got it? Okay. Now, let us write down various equations here. First, KVL and KCL equations. Okay. What is a KCL equation at this node? Currents going towards the node should be equal to currents leaving the node, right? Armature current going towards the node, field current and load current are leaving the node. So therefore, armature current is equal to field current plus load current. Correct? Yes. Next, it is a parallel circuit, right? It's a shunt circuit. Therefore, voltage between these two nodes is Vt. Then can I say voltage between these two nodes is also Vt? If voltage between these two nodes is Vt, what is IF formula? Therefore, IF is equal to Vt by Rf. Correct? Okay. Next, write down the KVL equation in this loop. Current was flowing from Eg to Vt. Therefore, definitely Eg is greater than Vt. So start writing the KVL equation from Eg. So Eg is equal to, yes, in the direction of the current, first drop is at armature resistance, IaRa. After IaRa, brush drop will be there, total brush drop Vb. After brush drop, next we have a load resistance, that is Vt. And as I mentioned, the brush drop is very, very small, therefore neglect it. Brush drop is very small, so neglect it. If it is given in the problem, you can't neglect, otherwise you can neglect it. So the moment when brush drop is neglected, then what is the equation? Eg is equal to Vt plus Ia. This is the same KVL equation even in separately excited generator also. Eg is equal to Vt plus IaRa. Even in shunt generator also same formula. Got it? So important observations in shunt generator is the field winding is designed using very high resistance. Okay, very high resistance. Got it? Therefore, it will carry low current. Winding inductance formula. Remember, Akbar here, at steady state conditions, the inductance effect is nullified. Why? Because which current is passing through field winding? DC current. And for DC currents, at steady state condition, inductance acts like a short circuit. Only in the transient condition, inductance effect will come into picture. Okay. Under steady state condition, inductance will act like a short circuit. That's why we don't consider the inductance value of the field winding. Okay. Fine. Yes. Now, in a similar manner, let us write down excitation, series winding or series excited DC generator as well. Okay. So, series excited DC generator. Series excited DC generator. Okay. See, as the name itself is indicating, this time the field winding will be connected in series with armature. So consider this is the armature circuit, armature resistance and generated EMF, generated current, armature resistance. Now the field winding was connected in series with armature, correct? That means a part of generated current is used or total armature current is used. Total armature current is used to excite field winding. And then the same current will go through the load circuit. This is load resistance and load current. Voltage across load resistance is nothing but terminal voltage. Current passing through field winding, this is field current. This time you tell me this is a shunt element or it is a series element. That is a series element. As it is a series element, what is the formula for copper loss in that element? Copper loss will be I square into R, right? Any shunt element, copper loss formula is V square by R. When the resistance is in series, the copper loss formula is I square into R. If it is I square R, how to minimize these losses? To minimize this copper loss, we must use low resistance winding or high resistance winding. Low resistance winding. That's why series field winding resistance is very low, guys. Very low. Generally 0.1 ohm to 0.5 ohm. But for shunt field winding, the resistance is high, 100 ohm to 500 ohm. You see the range. Therefore, when you see the field resistance value itself, you can decide whether the machine is a shunt machine or a series machine. If it is a series machine, the field winding resistance is very low. In a shunt machine, field winding resistance is high. Now, let us write down various equations here. Is it looking like a single series loop? As it is a single series loop, what is the relation among these three currents, IA, IF and IL? Yes, IA or IF and IL all are equal, right? Armature current, field current, load current all are equal. Remember one important observation in series machine, we all know that flux is always proportional to field current, guys. Flux is always proportional to field current. But in series machine, field current or armature current both are same. Therefore, we can also write flux is proportional to armature current. Very important. And whenever load changes, armature current will change. Whenever armature current changes, flux will change. Therefore, in series machine, you can't treat flux as a constant value. Flux may change whenever load changes. Correct? Okay. Next, let us write down the KVL equation in this loop. Current is flowing from EG to VT. So therefore, EG is greater than terminal voltage VT. And write the KVL equation, start with EG. So EG is equal to, yes, in the direction of the current, where is the first drop? IARA. Next drop, brushes, VB. After brushes, we have a field resistance, IF into RF. After field resistance, we have load resistance. Voltage across load resistance is VT. Correct? So here, brush drop is very small. You can neglect it. And then the equation becomes EG is equal to, remember here guys, armature current or field current both are same, right? So you can take armature current common. It will become RA plus RF plus VT. So summarizing, if I rearrange, EG is equal to VT plus IA into, I will call it as total resistance. What is mean by total resistance? It is armature resistance plus field resistance. So this is the equivalent circuit of a series generator and associated formulas. The formulas of series generator. Okay. All right. Fine. Now, when you compare shunt generator and series generator, field resistance is high in shunt generator, field resistance is low in series generator. Got it? Okay. Now, let us see compound generator. Remember, compound generator means it is the combination of series and shunt excitations. It is the combination of series and shunt excitation. That means two field windings will be available. Two field windings. Okay. Let us consider this is the pole core of the machine and this is the pole shoe of the machine. And a compound generator will have two field windings. Okay. One will be connected in series, another one will be connected in shunt. Let's say this is the shunt field winding, guys. Okay. Let us use a different color. So this is a series field winding. Okay. Let's say this is shunt winding. This is series field winding. Two field windings are there. And imagine both windings are carrying current in the same direction. If both windings were carrying the current in the same direction, can I say flux created by both windings will also be in the same direction? How to find out flux direction when you know the current direction? Right hand thumb rule. According to that, you see the shunt winding current is along my four fingers. Then what my thumb is representing, shunt flux or shunt MMF. Is it in this direction? So this is the direction of shunt MMF. And look at the series winding also carrying the current in the same direction. So series MMF is also in the same direction. Series MMF is also in the same direction. Therefore, both the MMFs are adding with each other or subtracting from each other, adding with each other, because both are in the same direction. Therefore, the total MMF of this machine, total, T means total, is equal to shunt MMF plus series MMF. Combination of these two. Shunt MMF plus series MMF. Okay, and such type of compound excitation is known as cumulative compound excitation. Cumulative compound excitation. Okay, cumulative, that means the sum of the two. Obviously, the other type you can imagine, right? What if both the MMFs are in opposite direction? Both will subtract from each other. That is known as differential compound excitation. And if I ask you how to create differential compound excitation, then what is your answer? Yes, reverse the current direction of any one winding. Okay, for example, imagine this is the rotor core of the machine, the core of the machine. And there are two field windings as I mentioned. This is the first field winding. Let us say this is a shunt winding. Okay, and then we have a series field winding also. Okay, now imagine shunt winding was carrying the current in upward direction, but series winding was carrying the current in downward direction. Therefore, what happens if you use right hand thumb rule? Shunt MMF is in this direction, series MMF is in opposite direction. Therefore, both MMFs are adding or subtracting from each other. This is known as differential compound excitation. Therefore, the total MMF is equal to shunt MMF minus series MMF. This is known as differential compound excitation. Okay, there are two types of excitations: cumulative compound excitation and differential compound excitation. Remember, they are not two types of machines, just two types of excitations. You just reverse the current direction of any one winding, cumulative compound connection can be changed to differential compound connection. Now we will also try to develop the equivalent circuit of compound generator. Based on the equivalent circuit, compound generators are again subdivided into two types: short shunt compound connection and long shunt compound connection. Let's see that. Suppose you see this is the armature circuit of the machine. Generated EMF, generated current, armature resistance. As I mentioned, there are two windings. One will be shunt winding, another one is series winding. So I am connecting shunt winding first and then series winding here. So this is the terminal voltage of the machine where the load is connected. This is the load resistance. This is the terminal voltage. This is the load current. This is a series winding, series current. This is a shunt winding, shunt current. This is the armature current. So this connection is what we call it as short shunt connection. Short shunt connection. Okay, and there will be another type also known as long shunt connection. Let's see that. So this is the armature part of the machine. Armature current, generated EMF, armature resistance. First I am connecting a series winding. Next I will connect a shunt winding. A very minor difference between both of them, right? Even though connections are slightly different, but the performance of both machines is almost same. This is the terminal voltage, line current, series field current, shunt field current. This is armature current. This is known as long shunt compound connection. First of all, compound means a combination of shunt and series. Okay, first I connected shunt, later series was connected. This is short shunt. Here first series was connected, later shunt was connected. This is long shunt. Now let us write down the equations also for these two circuits. Very simple equations. In this circuit, can I say series current and line current both are same? Right or not? And if you apply the KCL equation here, armature current is equal to shunt current plus line current plus load current or line current, anything is same. And then if I apply the KVL equation here, what is the shunt current formula? Shunt current is equal to, suppose if you take this node as reference, what is the voltage at this node? VT. If this is VT, what is the voltage at this node? VT minus drop in this resistance, ISE, RSE. Correct or not? Okay, drop minus or plus? Plus, right, because it is higher potential. Current will always flow from higher potential to lower potential. This is higher potential, VT plus ISE, RSE. This is lower potential. Therefore, what is ISH formula? VT plus ISE, RSE by RSH. Okay. So once you know ISH, now write down the KVL equation. EG is equal to VT plus all the drops here in the loop. Okay, I'm directly writing. First one, armature resistance drop. Next, brush drop. After brushes, next drop is series resistance, ISE, RSE. Then finally, load resistance VT. This is the KVL equation. Don't try to by heart these equations. Understand the circuit diagram, then easily you can develop the equations of the machine. Similarly, for long shunt connection also, you can understand which currents are same. Series winding current and armature current both are in series, therefore both are equal. Right? And Apply the KCL equation at this node. Armature current was going towards the node. ISH and IL are leaving. So armature current is ISH plus IL. And then ISH is equal to VT by RSH, correct or not? And then the KVL equation once again, EG is equal to first drop, let me write down in terms of VT. So VT plus IA RA plus ISE RSE brush drop VB. This is the KVL equation. Okay, very simple. See, it's a combination of shunt and series windings, that's all. Okay. Just to look at the formulas once again. This is long shunt. Okay, this is a short shunt. This is a series. This is a shunt. This is separately excited. Now we will try to answer few questions related to each generator. Okay, based on the circuit diagram, we will try to answer few questions. Okay, very important topic. You can expect one question from the circuit diagrams of DC generators. Okay. Also, a similar model we will solve in DC motors as well. DC generator circuits, DC motor circuits. Okay. So let us see. Okay. So whenever it is necessary, we will come back to the equivalent circuits. Okay, and the equations. Shunt machine, series, compound. Right. So okay, so read this problem. This is a question related to separately excited DC generator. A separately excited generator, when running at 1200 RPM, supplies 200 ampere at 125 volt to a circuit of constant resistance. Okay, see, circuit of constant resistance. That is a load. What will be the current when speed is dropped to 1000 RPM if the field current is unaltered? When I said field current is unaltered, field flux is constant. Armature resistance is given 0.04 ohm. Total brush drop at the brushes is 2 volt. Neglect armature reaction. So if you read the problem carefully, first thing, it is a separately excited generator. And initially the machine was rotating at 1200 RPM. This is the first case. And it was supplying 200 ampere to a constant resistance load at 125 volt. In the next case, the speed is dropped to 1000 RPM. What is the new current generated by the machine is the question. Okay, therefore, there are two cases in this problem. First case, 1200 RPM. So let us note down the data. So let us solve with case number 1. Case number 1, the machine was rotating at 1200 RPM and it was generating how much current? 200 ampere current. It is a separately excited machine, so load current or armature current both are same. And to understand this is the first case, I am putting a suffix number there. Okay, at what terminal voltage this is happening? 125 volt. The terminal voltage was 125 volt and the load is a constant resistance type. See, a circuit of constant resistance. So using this data, can you find out what is the load resistance? Can I say load resistance is nothing but load voltage divided by load current only? What is mean by load voltage? Terminal voltage 125. What is mean by load current? 200. This will give you the load resistance value. Okay, 1.25 by 2. Okay, 0.625. This is the load resistance value. Got it? Now, based on this information, I will write down the KVL equation and I will try to find out generated EMF first. What is the formula? EG is equal to, first case, VT plus IA into RA plus brush drop. That was given in the problem. Otherwise, I would have neglected it. So what is the terminal voltage here? 125 plus armature current 200 armature resistance was given in the problem, right? What is the armature resistance value? 0.04 ohm. And brush drop, total brush drop was 2 volt. Okay, so you just add everything, you will get the value of generated EMF. Okay, so let us see what is the generated EMF. 125 plus 200 into 0.04 plus 2 volt, 135. This is the generated EMF in the first case. But now when it comes to second case, the speed is changed, right? What is the speed now? The speed is dropped to 1000 RPM, case number 2. In case number 2, the speed was dropped to 1000 RPM. Find out what is the new current generated by the machine. This is the question. And you tell me, whenever speed changes, generated EMF will definitely change, because what is the formula for generated EMF? The shortcut formula I told you. Ka into phi into omega, correct? Here, Ka is known as armature constant. And flux is also constant. Why? Because this machine is separately excited. Separately excited, that too it was clearly mentioned, field current is unaltered. That means flux is a constant value. The moment I know Ka and phi both are constants, therefore Eg is only proportional to speed. Omega or n, anything is same, proportionality. As it is directly proportional, can I write generated EMF in the first case by generated EMF in the second case is equal to speed in the first case by speed in the second case. And if I continue, what is the generated EMF in the first case? 135. 135. Generated EMF in the second case, I don't know. That is what I need to find out. Is equal to speed in the first case 1200 by speed in the second case 1000. So you find out what is the new generated EMF. 1000 by 1200 times, right? So into 135. I am getting 112.5. This is the generated EMF in the second case. But what is the answer we need to find? What is the new armature current? The moment I got a new generated EMF, you write the KVL equation. Because KVL equation has armature current term, right? So let us write down the KVL equation. Eg2 is equal to Vt2 plus Ia2 into Ra plus brush drop. Okay. But can I write this Vt2 is nothing but IL2 into load resistance, because terminal voltage is nothing but voltage across load resistance. Voltage across load resistance is nothing but load current into load resistance plus Ia2 into Ra plus brush drop. And you know, armature current and load current both are same. It is a separately excited machine. Take it common. So this is Ia2 into Ra plus RL plus brush drop. This is the new generated EMF. Okay. Now, will you tell me why I am using the same RL once again? Because it was clearly mentioned in the problem, the circuit of a constant resistance. The load is a constant resistance type. That's why RL is a constant value. Got it? Now, everything is available. Find out this current. So, let us go to the next page. Eg2 112.5 is equal to Ia2 into Ra 0.04. What is the load resistance we got? 0.625. 0.625. Brush drop is 2 volt. So the unknown is armature current. To find out the answer. Okay, that is the new armature current developed by the machine. Okay, so it was 112.5 minus 2 divided by 0.04 plus 0.625. So I'm getting 166 ampere approximately, right? Let me check again. 112.5 minus 2 divided by point. Yes, it was 166.16 ampere. 166.16. So this is the current that is generated by the machine when speed was reduced to 1000 RPM. Okay, when the speed was reduced to 1000 RPM, that is the new current generated by the machine. Okay. Right. So very simple problem. First you need to understand this problem has two cases. First case is when a machine was rotating at 1200 rpm. Second case is the machine speed is reduced to 1000 rpm. Okay. Okay. Now let us try to answer one more question. Let us select one more question from another generator. Yes, this is a question from shunt generator now. Okay, read the problem. A shunt generator has induced voltage on open circuit of 127 volts. See, I said induced voltage. Induced voltage means EG. When the machine is on load, the terminal voltage is 110 volt. See, the terminal voltage, that is VT. 120 volt. Find the load current if the field resistance is 15 ohm and armature resistance is 0.02 ohm. First of all, you need to understand it is a shunt generator. Okay, what is the information given? EG was given. EG was equal to 127 volt. Terminal voltage VT was 120 volt. Now use KVL equation because these two values will be available in KVL equation. What is a KVL equation? EG is equal to VT plus IARA. There is no brush drop. I am neglecting it. So EG and VT both are available. I think you can find out IA from here. So what is IA? EG minus VT by RA. So substitute. What is EG? 127 minus 120 divided by what is armature resistance? 0.02. Okay, that is 7 by 0.02. 700 by 2, 350 ampere, correct? Right. So the armature current was 350 ampere. But what is the answer? We need to find load current. We need to find load current, IL. But in shunt generator, what is KCL equation? We know armature current was equal to load current plus field current, correct? If you want, I will go back. Yes, you see KCL equation, IA is equal to IL plus IF. So if I want IL, I need to find IF first. What is the formula for IF in shunt generator? VT by RF, right? So IF is equal to, here IF is equal to VT divided by RF. What is the terminal voltage? 120. Yes. Field resistance 15 ohm, right? Clearly given 15. So 120 by 15. This is a field current. Once you know field current, you can easily find out load current. Load current is IA minus IF. Okay. So do it and find out the answer. IA was already 350. Field current was 120 by 15. Generally, very low current will flow through field. So field current was 8 ampere. So 350 minus 8, 342, correct? So that is the value of load current, isn't it? Easy question, 1 mark model this is. Right? So 342 ampere, that is the load current. Got it? Fine. Now, let's answer one more question. Let me select one more machine. So this time, let us select a series machine, okay? Okay. So read this problem. This is a 2 marks model. Okay, read the problem. A DC series generator rotating at 1000 rpm, producing a terminal voltage of 300 volt and producing a current of 100 ampere. The total resistance of the machine. What is mean by total resistance in a series machine? RA plus RF together. Total resistance of the machine was 0.5 ohm. If the speed is increased to 1200 rpm, the generated current to produce same terminal voltage. What is the new generated current? to produce same terminal voltage. See, the moment I said same terminal voltage, you need to understand terminal voltage is constant. So once again, there are two cases in this problem. First case, the machine was rotating at 1000 rpm. In the next case, the speed is increased to 1200 rpm. Okay, so you take first case and find out generated EMF of the machine. Terminal voltage 300. So let us see case number 1. Okay, so in case number 1, the machine was rotating at 1000 rpm. Terminal voltage was, what is the terminal voltage? 300 volt. First case 300 volt. And what is armature current in this machine? Armature current, field current, load current, all are same because it is a series generator. How much? 100 ampere. Now find out generated EMF. What is the KVL equation? Generated EMF is equal to Vt plus Ia into Ra plus Rf. That is the total resistance of series generator. I am writing suffix number 1 because it is case number 1. So generated EMF is equal to, what is the terminal voltage? 300, current value 100, and what is the total resistance of the machine? 0.5, right? So that substitute 0.5 here. So generated EMF is 350 volt, correct? This is case number 1. But in the next case, what was happened? In the next case, speed is increased to 1200 rpm. In case number 2, the speed rises to 1200 rpm, correct? Yes, you please read this. If the speed is increased to 1200 rpm, what is the new generated current to produce same terminal voltage? That means in the second case also, terminal voltage is same, 300 volt. But what is the new current generated by the machine is the question. That is the answer we need. So you know that when speed changes from 1000 rpm to 1200 rpm, generated EMF will also change, because what is the EMF formula? EMF is equal to Ka phi into omega. But remember guys, it's a series machine, flux is not constant. Yes, in series machine, flux is proportional to field current. Field current or armature current both are same into speed. Therefore, I can write Eg is directly proportional to armature current into speed. Suppose if it is a separately excited generator, flux would have been constant. But here it is proportional to armature current. So I can write Eg1 divided by Eg2 is equal to Ia1 divided by Ia2 into N1 divided by N2. You know what is the generated EMF in the first case? 350. You don't know what is the generated EMF in the second case. That is unknown value. Is equal to armature current was known, right? First case 100. Second case you don't know. What is armature current? That is the answer we have to find actually. Speed in the first case 1000. Speed in the second case 1200. Therefore, you are getting one equation with two unknowns this time. Okay, just cross multiply, you will get Eg2 in terms of Ia2. So cross multiply and tell me Eg2 is how many times of Ia2? Okay, let's see. 350 into 1200 by 1000 into 100. Sorry, by 100, right? So 4.2 times, right? Let me do it again. 350 into 1200 by 1000 by 100. Yes, Eg2 is equal to 4.2 times of Ia2. Let us say this is equation number 1. I have a relation between Eg2 and Ia2. If I know one more relation with the same two unknowns, I can solve the problem. What is the other equation you can write? KVL equation, right? I already used performance equation here. Let's use KVL equation. What is the KVL equation for new generated EMF? Eg2 is equal to Vt2 plus Ia2 into Ra plus Rf, because it's a series machine. Now we know already we found Eg2 is 4.2 times of Ia2. 4.2 times of Ia2. Vt2 is the same 300. Ia2 into total resistance 0.5. So now you can understand there is only one unknown. Take this factor to the left side and find out what is Ia2. Solve it. Yes. So important thing you have to understand is it is a series machine, therefore flux is not constant. Flux is always proportional to field current, right? Flux is always proportional to field current. Fine. So solve it. Yes, what is a new current? It was 81 ampere, correct? The new current generated by the machine is 81 ampere. 81.08. I hope all of you got the answer. So important thing, we wanted to keep the same terminal voltage. Okay, that is the condition given in the problem. Look at the last line. If the speed is increased to 1200 rpm, what is the generated current to produce same terminal voltage? Same terminal voltage. That is why we are keeping a terminal voltage constant, it's 300. But speed changes. Whenever speed changes, generated EMF will change. Generated EMF will change. Okay. And what is the new armature current we have to find? Yes, the answer is 81 ampere. 81 ampere. Okay. 81 ampere. Clear? All right. So let's take a short break for 5 minutes. Then we will meet again. Okay guys, welcome back. So we discussed about the types of DC generators that we have. Now we will try to understand the characteristics of DC generators. Okay. So let's see. Just a moment. Hope the session was running smoothly. Let me check again. Right. Next, characteristics of DC generators. That is the next topic. Okay. Now, first we will discuss about separately excited DC generator characteristics. Then we will talk about self-excited DC generator characteristics. See, two types of characteristics we are going to discuss. First one is no load characteristics, also known as open circuit characteristics or magnetization characteristics. Okay. Second one is external characteristics or loaded characteristics of the machine. External characteristics or loaded characteristics of the machine. So we will try to discuss the first one, that too in separately excited DC generator first. Okay, separately excited generator. We know separately excited generator means field winding will be excited using an external DC voltage source. This is a generated EMF, armature current and armature resistance. As the name itself is indicating, we are going to draw the characteristics under no load condition. That means the load was not connected. So indirectly the terminals are open circuited. Correct? Okay. And field winding was separately excited. This is the field voltage and this is the field current. Got it? Okay, first let us try to understand between which parameters we are going to draw these no load characteristics. Remember, no load characteristics are drawn between generated EMF of the machine with respect to field current. That means what? We will try to change the field current value of the machine. Okay, and then we will understand how generated EMF was changing. Change field current to understand the change in generated EMF. First of all, let us try to figure out a relation between these two parameters. And remember, while developing these characteristics, we have to rotate the rotor at a constant rated speed. The speed must be constant rated value with the help of prime mover. Okay. Now, let us find out a relation. You know that generated EMF is equal to Ka into phi into omega, correct? And I said speed is constant right now. Therefore, generated EMF is directly proportional to field flux. And field flux is always proportional to. And field flux is always proportional, or you can say, field flux is always proportional to field current. Am I correct? Therefore, whenever field current changes, field flux will change. And whenever field flux changes, generated EMF will change. So let us see what happens if a field current is 0. Let us say x-axis field current is 0. If a field current is 0, according to this formula, flux must be 0. But actually, flux will not be 0. A small flux will be available known as residual flux. Because of that residual flux, a small EMF will be generated by the machine. So therefore, even though x-axis field current is 0, a small EMF is always generated by the machine. We call it as residual EMF. This is residual EMF. Next, what happens if a field current increases? If a field current increases, field flux will be increased. If a field flux increases, generated EMF will also increase. So, as the x-axis field current increases, y-axis generated EMF will also increase. But the question is, how far this generated EMF increases? Yes, this generated EMF will increase till flux reaches to saturation. And once the flux reaches to saturation, even though field current increases, flux cannot increase, thereby generated EMF also cannot increase. So let us say up to this point, generated EMF increases. Beyond this, saturation will occur. Once saturation occurs, the EMF is almost a constant value. And this point is what we call it as knee point location. Knee point. And after knee point, the core is said to be saturated. So at this knee point, whatever field current is available, we call it as rated field current. And corresponding to that knee point, whatever EMF is available, this is rated EMF. Got it? So this is magnetization characteristics or open circuit characteristics or no load characteristics of a DC generator. Okay, you will conduct this experiment in the laboratory generally by connecting a voltmeter here. You can measure EG. By connecting an ammeter here, you can measure IF and draw the graph by changing field current, how generated EMF was changing. Okay, we need not to discuss that much depth. This is what the curve looks like. Okay, yes. So this is the portion once the core is saturated. Okay, right. Now let us also try to understand external characteristics of this machine. External characteristics, also known as loaded characteristics. See, as the name itself is representing, we will be drawing the characteristics under loaded condition now. Okay, that means the load is connected. Imagine this is the load resistance, guys. Suppose if the switch is closed, what is the meaning of it? Once I said switch is closed, load is connected. Once load connected, current started to flow through this load, right? Now armature current was not zero, it is a finite value. Okay, now let us first understand between which parameters external characteristics are drawn. Remember, external characteristics are drawn between load voltage and load current. Very clear? What is meant by load voltage? Terminal voltage. And load current, that is nothing but IL. You can take IL or IA because both are same in this machine, right? IL and IA both are equal. Now, to develop characteristics between these two parameters, first we need to develop a mathematical formula, then we can draw the characteristics. And remember, while doing this experiment, we have to rotate the machine at a constant rated speed. Also, we have to maintain rated field current. Remember guys, I said rated field current and rated speed. That means generated EMF is a rated value. What is generated EMF formula? Ka phi into omega. I said field current is rated value, so flux is rated value. And speed is also rated value. Therefore, generated EMF is a rated value. What is mean by rated EMF? Rated EMF means residual voltage value or knee point voltage value. This knee point voltage value, that is rated EMF. Okay, but we are drawing the graph for VG or for VT. Yes, we are drawing the graph for VT, not for EG. Okay, so let us write the mathematical equation for VT. What is a KVL equation we know? Yes, EG is equal to VT plus IARA. From this, VT is equal to EG minus IARA. This is the KVL equation I am going to use. Suppose, let's start the discussion with no load condition. Suppose, what if this switch is open? If this switch is open, can I say current will be 0, IA or IL both are 0? If IA is equal to 0, then what is EG? VT is equal to EG. And EG is rated EMF. Therefore, when the machine is under no load condition, the load current will be 0, then the terminal voltage is equal to EG. Okay, and EG is rated EMF, guys. This is what we call it as no load terminal voltage. Next, what happens if load increases? Suppose if the load is increasing, indirectly the load current increases. If load current increases, what about armature current also increases? If armature current increases, what about this resistance drop? This resistance drop is also going to increase. Whenever resistance drop is increasing, can I say terminal voltage is going to decrease according to the equation? Because VT is equal to EG minus IARA. Therefore, we will find drooping voltage characteristics or rising voltage characteristics. Definitely drooping voltage characteristics. See, the voltage was drooping. What is the reason for that drop in voltage? IARA drop. Okay, the reason is IARA drop. This gap is IARA drop. But generally, we will design armature winding to have very low resistance or very high resistance, very low resistance. Why armature winding resistance should be very low? Then only losses can be minimized. Generally, armature winding resistance is very low. Therefore, the drop is very, very small. Okay, you can almost neglect the drop. Suppose if the drop is almost neglected, can I say from no load to full load, the voltage is almost a constant value? Okay, so usually IARA drop is very small. If IARA drop is very small, you can almost neglect it. If you neglect this small drop in voltage, I must say the voltage is almost constant from no load to full load. Therefore, separately excited DC generator will offer drooping voltage characteristics or rising voltage characteristics, drooping voltage characteristics. At no load condition, the terminal voltage is equal to rated EMF. As the load increases, the voltage was reducing and the drop is very, very small, mainly because of IARA, armature resistance drop. Got it? Yes. This is about characteristics of separately excited DC generator. I am neglecting armature reaction, guys. Generally, if armature reaction is considered, you may have a little bit more drop. A little more drop you may expect because of armature reaction, but you can neglect it. Understand? Right. So this is about characteristics of separately excited DC generator. Got it? Fine. Now let us try to understand self-excited DC generator. This is important. Yes. Self-excited DC generator. In that, first I will take shunt generator. Directly I will write down shunt generator characteristics. You know, self, why the word is used as self generator? Let us understand. First we will try to figure out no load condition, no load characteristics. Then we will draw loaded characteristics. Okay, now see, this is the armature circuit of the machine. Generated EMF, armature current and armature resistance. Okay, here we have the field winding. This is the field resistance and this is the field current. The terminals are open circuited, guys. Why? Because I said machine is under no load condition. See, the moment when the terminals are open circuited, no need to draw them, right? This is a simplified circuit. Okay. Now in this circuit, you see it looks like a single loop, right? Therefore, can I say armature current and field current both are equal? Okay, both are equal. And also write down the KVL equation in this circuit. If you write the KVL equation, start with EG, then EG is equal to, where is the first voltage drop? IARA. Neglect brush drop is very small. After brush drop, next drop is across a field resistance IFRF. But right now, IA and IF both are same only. So you take current common, IF common, then it is RA plus RF. And you all know that shunt field winding will have high resistance or low resistance? High resistance. As field resistance is very high, you can neglect armature resistance. Okay, because armature resistance is very small compared to field resistance. Therefore, the approximate formula is EG is equal to IF into RF. From this, IF is equal to EG by RF. Remember, this is the formula valid only under which condition? No load condition. Apart from this formula, there are other formulas we already developed. What is the formula for EG, guys? EG is equal to Ka phi into omega. Remember, flux is always proportional to field current. And field current, we developed one formula now. Field current is EG by RF. Field current is equal to EG by RF. Now, by using these three equations, I will try to explain self-excitation phenomena in shunt generator. Okay, so please listen very carefully. Imagine you went to market to purchase a DC generator, that too shunt generator. You purchased a new generator and you installed that shunt generator in your laboratory, but you did not connected prime mover yet. Let us say prime mover is not connected. If a prime mover was not connected, can I say speed of the machine is equal to 0, omega is equal to 0. Now look at the first equation. When omega is equal to 0, what is Eg? Obviously, Eg is also 0. Okay, when Eg is equal to 0, then what is the field current? According to the last equation, when Eg is 0, field current is also equal to 0. And look at the second equation. When field current is 0, then what about field flux? Not 0. Residual flux will be available. Even though field current is 0, there is a small flux always available. We call it as residual flux. Generally, residual flux is very small or very large? Very small. Okay. Now that residual flux will be available even though there is no field current. Now, imagine prime mover was connected. The moment when the prime mover was connected, can I say the machine started to rotate? So now omega is 0 or rated value? Yes, omega is rated value. Now look at the first formula. Now omega is rated value. Already what is the flux available in the machine? Already residual flux is available. Therefore, omega is finite. Flux is also finite. Therefore, can I say Eg is a finite value? That means Eg is not 0 now. Eg is a finite value. That means what? Eg increases. Earlier Eg was 0. But now Eg value developed because of which flux? Residual flux. Now look at the last equation. The moment when Eg increases, immediately can I say If increases? Therefore, If is not 0, If increases. And whenever If increases, look at the second equation. Whenever If increases, can I say flux increases? Yes. Whenever If increases, flux value increases. And whenever flux increases, look at the first equation. Whenever flux increases, again can I say Eg value will increase. And again when Eg increases, If will increase. When If increases, flux increase. Again flux increases means Eg will increase. Can I say this loop will continue now? And how far that loop will continue? I must say the loop will continue till flux reaches to saturation. When I said flux reaches to saturation means that is residual point or rated point or knee point, that will be definitely knee point location. Knee point location means voltage will reach rated value. Got it or not? Okay. So this loop will continue till flux reaches to saturation. That means voltage will reach rated value. Therefore, if you draw the curve now, by taking generated EMF on y-axis and field current on x-axis, initially when there is no rotation, field current is 0. Even though field current is 0, there is one flux available in the machine. What is that? Residual flux. So even though field current is 0, residual flux is available. Because of that residual flux, the moment you rotate the machine at rated speed, a small voltage will be initially generated. We call it as residual voltage. And that residual voltage, whatever is generated, whatever residual voltage is generated, it's a closed loop, right? And whenever voltage induces in any closed loop, what will happen? Current will circulate. So that residual voltage will circulate a current through this field winding. And that field current will increase the field flux. Okay. So whenever flux, so this residual voltage will circulate field current. Now field current increases. When field current increases, the flux increases. When flux increases, EMF will increase. Again field current will increase. Again EMF. Again field current. Again EMF. And the process will continue till voltage reaches to rated value. So this is rated field current. And this will be rated EMF. So this is how self-excitation is possible in DC generators. So what is the mandatory condition for self-excitation, guys? Yes, the mandatory condition is residual flux is mandatory. If residual flux is absent, development of EMF is not possible in shunt generator. Just imagine, what if residual flux is absent? This flux would have been 0. If flux is 0, next time, even though you rotate the machine with rated speed, EMF cannot be generated since there was no flux. Okay, that's why residual flux is mandatory. Okay, now one more thing is, you come back to the circuit. Initially when there was no rotation, there is no EMF, there is no current, but what is the only flux available? Residual flux. Because of that residual flux, a small EMF is generated. Okay, so imagine, let's take a small example. The total flux in the machine is equal to residual flux only in the first case, right? When you don't rotate the machine, what is the only flux available in the machine? Residual flux. Imagine this residual flux value was 1 milliweber, just for example, 1 milliweber. Therefore, the total flux also 1 milliweber. Now, using this 1 milliweber residual flux, the moment I rotate the machine, a small voltage will be developed. What that small voltage is doing, it will circulate a current through field winding. Therefore, this field current will now create some additional flux. The field current will create some additional flux. Who is creating this additional flux? Field current. And what happens? This additional flux will join with residual flux so that resultant flux will increase. Okay. If resultant flux increases, Eg value will increase. Whenever Eg value increases, again the current will increase in the loop. Whenever current increases, this additional flux will increase again, total flux will increase again, and the process will continue. But when you are conducting this experiment in the laboratory, you made a small mistake. Let's say the mistake is you connected this field winding with a wrong connection like this. You connected field winding with an opposite polarity like this. You reverse the field connection. The moment I reverse the field connection, what will happen, guys? When you try to rotate the machine with rated speed, always what is the first voltage that will be generated? Residual voltage. Whatever residual voltage is generated, now that will circulate a current through field winding in the opposite direction, right? Therefore, which current reverses now? Field current reverses. The moment when field current reverses, can I say this additional flux will also reverse, because who is creating additional flux? Field current. The moment I said additional flux reverses, now additional flux is not positive anymore, it is negative. That means it is now adding to residual flux or subtracting from residual flux? Subtracting. That is demagnetization. Once additional flux is subtracted from residual flux, the resultant flux will decrease now. If resultant flux decreases, EMF will decrease. When EMF decreases, current will decrease. Again, flux will decrease. And the process will continue. Finally, flux becomes zero. Finally, flux becomes zero. That means machine was able to build up the voltage or unable to build up the voltage? Unable to build up the voltage. Where is the mistake happening? The mistake is wrong field connection. Because you are connecting field winding in a wrong way, that's why there is no development of EMF. That's why if you went to any DC machines laboratory, I hope most of you might have gone through DC machines lab, you will find some nomenclature like this. Okay, there will be terminologies mentioned: A, F, F. What is the meaning of it? If you connect A to F and A to FF, that means correct field connection. If you connect field winding with a wrong polarity, then development of EMF is not possible. Got it? Yes. So what are the mandatory conditions, guys? First mandatory condition is residual flux is mandatory. Second mandatory condition is correct field winding connection. We have to connect field winding with a correct polarity. There are two more mandatory conditions. Okay, actually we have to derive them, but we don't have time to derive, but I will directly write down. First mandatory condition is residual flux is mandatory. Okay. Second condition is correct field polarities. Correct field winding polarities. And the third mandatory condition is field resistance must be less than critical resistance. Must be less than critical resistance. Okay, I am not proving this. Actually, in regular class we will prove it. Okay, we don't have that much time. Next, fourth condition is speed must be more than critical speed. Okay, speed must be more than critical speed. These are the four conditions. If all these four conditions are satisfied, then only development of EMF is possible. You may have a doubt here, sir, what is mean by this critical resistance? How do you find critical resistance? Very simple. You have seen already this, no load characteristics, right? You draw the characteristics once again. Okay, critical resistance. I wanted to find out critical resistance. Okay, so you draw the no load characteristics again. No load characteristics are drawn between EG and IF. You know, this is how the graph is, right or not? Now, I wanted to find out critical resistance. To find critical resistance, what we will do is simple. You just draw a tangent on this EMF curve. Tangent. You just draw a tangent on this EMF curve, and the slope of this tangent is nothing but critical resistance. Slope of that tangent is nothing but critical resistance. You know how to calculate slope of a straight line. Is it looking like a straight line passing through origin because it is like a tangent? And the slope of that tangent is nothing but a critical resistance. Okay, suppose you got critical resistance is equal to, let us say, 200 ohm. The slope is 200, let's say. Now, in order to build up the voltage, field resistance should be always less than critical resistance. As critical resistance is 200, I must say field resistance should be less than 200 ohm. Suppose I gave you critical resistance is 200 ohm. Which of the following field resistances can be used? Option A, 250 ohm. Option B, 200 ohm. Option C, 300 ohm. Option D, 150 ohm. Then there is only one option which is less than critical resistance, that is 150 ohm. That is what you need to use. Got it? So critical resistance is just nothing but slope of the tangent drawn on EMF curve. Okay, why this is critical resistance? The proof I am not doing, you try to believe me. Okay, right, that is a critical resistance. Okay, yes, field resistance should be always less than critical resistance. Fine. This is about the no load characteristics of a shunt excited DC generator. If any condition failed, the machine cannot develop the voltage. Now let us develop the external characteristics also. External characteristics of a DC shunt generator, just like a separately excited generator, we can draw. First, let me draw the circuit diagram. This is the armature circuit of the machine having generated EMF EG, armature current IA, armature resistance RA. Field winding will be connected in shunt with armature. This is a field resistance, this is a field current, and here we have the load. It's a topic generally I discuss for 3 hours in regular classroom, but here we are trying to finish within half an hour. Okay, so you try to understand the intensity, right? So the external characteristics are always drawn between what and what? VT and IL. So we will take terminal voltage on y-axis and the load current or armature current on x-axis, because both are almost same. So what is a KVL equation? We know EG is equal to VT minus IA, EG is equal to VT plus IA RA. From this, VT is equal to EG minus IA RA. Okay, same equation, just like separately excited machine. Suppose let us, if I am discussing about no load condition means, can I say current is a constant value? Current is 0, no load condition. If current is 0, the resistance drop is 0. If resistance drop is 0, VT is equal to EG. And this machine can generate voltage up to which value? Rated value. Therefore, VT is equal to EG, where EG is rated value. So therefore, at no load, current is 0, VT is equal to EG, which is the rated value. This is the no load terminal voltage. Now what happens if load increases? Simple. If load increases, load current will increase. If load current increases, indirectly armature current also increases. If armature current increases, armature resistance drop increases. If armature resistance drop increases, then terminal voltage will decrease. That means a shunt generator will also offer drooping voltage only, right or not? Drooping voltage characteristics, just like separately excited generator. But there is one important point I need to discuss, that is a short circuit condition. Suppose what happens if this load is short circuited? For example, if load is short circuited, what is the voltage across the load? That is nothing but terminal voltage. Let us discuss about short circuit condition. Just wait. When load is shorted, what will happen? When the load is shorted, what is the voltage across a short circuit? 0, right? So therefore, when the load is shorted, Vt is equal to 0. If Vt is equal to 0, then what about field current? Field current is always equal to Vt by Rf. When Vt is equal to 0, field current is also 0. If field current is 0, then what is the only flux available? The only flux available in the machine will be residual flux only. If only residual flux is available, then what is the generated EMF of the machine? Generated EMF is equal to residual EMF only, which is very small or very large? Very small. Now you write down the KVL equation. What is the KVL equation here? EG is equal to IARA plus VT, but VT is 0 because of short circuit. From this, what is armature current becomes? EG divided by RA. Correct or not? Yes. EG divided by RA. But EG is right now rated EMF or residual EMF? EG is residual EMF, which is a small value, right? Residual EMF is very small. As this voltage is very small, armature current is also becomes very small. Generally, what we will believe is that, sir, when the load is short circuited, it is like a fault condition. Because of a fault condition, the machine will generate a large amount of current. But that is not true in shunt generator. In shunt generator, when the load is short circuited, only residual voltage will be available. Only residual voltage means a very small amount of current will be generated. A very small amount of current will be generated. Got it? Clear? So, can you mark that point on the graph now? Can we mark that point on the graph? Yes, let us try to mark that point on the graph. So, under short circuit condition, the y-axis terminal voltage was 0, right? The y-axis terminal voltage is 0 and x-axis current is very small. Let us say this is that small current. Short circuit current. Therefore, the curve is coming like this, right? So this is the characteristics of DC shunt generator under loaded condition. So initially it was like a drooping curve, and when the load is almost like a short circuit, you can see a sharp drop in the voltage. Not only drop in the voltage, even the drop in current as well. Okay. Suppose if it is a separately excited generator, what would have happened in this situation? If it is a separately excited generator, even though terminal voltage is 0, flux would have been rated flux only because it is separately excited. If it is rated flux, EMF is rated value. Rated EMF means a large current would have been generated. That is like a fault condition. Got it? So, but here it is very small current is generated under short circuit condition. This is about external characteristics of a separately excited DC generator. It is like a drooping curve. Drooping voltage characteristics. Okay, drooping voltage characteristics. Clear? Fine. Now, let's try to understand series generator characteristics also. Series generator characteristics. First, we will try to understand a no load condition. Then we will try to connect a load. First of all, what is meant by series generator? Field winding will be connected in series with the machine, right? So, let us say this is the armature circuit of the machine. Generated EMF, armature current, armature resistance. Field winding will be connected in series. This is a field resistance, and here we have the terminal voltage. But I am talking about no load condition first. See, when I said the machine is under no load condition, the load current is equal to 0, obviously. If load current is 0, then field current is also 0, guys. Why? Because both are same only, right? Load current or field current, both are same. If field current is 0, then what is the only flux available? Residual flux only. Because of this residual flux, the machine will generate residual EMF. The machine will generate residual EMF. But that residual EMF can circulate any current or cannot circulate any current. It cannot circulate any current because it is open circuit here. Therefore, additional flux cannot be created. Okay. Whereas in case of a shunt generator, what is happening? You look at the shunt generator. You look at the shunt generator circuit diagram. Even though load is not connected, whatever residual flux is created, that can circulate some current through field winding. Whereas that situation is not possible in series machine. That's why series generator cannot build up the voltage under no load condition. So I must write, yes, series generator cannot develop EMF under no load condition. Only residual voltage can be developed. Further development of EMF is not possible. Okay, that is in series generator. So in order to develop the voltage, definitely load has to be connected. If the load was connected, what will happen, guys? Already residual EMF is there, right? The moment when the load is connected, now there is a closed loop is formed. As the loop is closed, because of the voltage induced, immediately current started to circulate. That means field current is zero or increased. Whenever field current increases, flux will increase. Whenever flux increases, voltage will also increase. That's why series generator will offer rising voltage characteristics. If you take the current on x-axis and terminal voltage on y-axis, I repeat again, if the load current is zero, what is the field current also zero, because load current and field current both are same, guys. If field current is zero, only residual flux is available, then machine will develop only residual EMF. Therefore, when the load current is zero, voltage will be equal to residual EMF only. Residual EMF only. Now what happens if load current increases? When I said load current increases, indirectly field current also increases. Flux will also increases. When flux increases, EMF will also increase. Therefore, you will find rising voltage characteristics. But the question is how far the voltage will rise, guys? Up to saturation only. Imagine at this point saturation reaches. This is the rated current and rated voltage is reached. Now what happens beyond saturation? Beyond saturation, even though current increases, EMF does not increase, right? So beyond saturation, I must write flux is a constant value. Flux is a constant value. Therefore, generated EMF is also a constant value. But we are drawing the curve for generated EMF or terminal voltage. Terminal voltage. What is the formula for terminal voltage? Terminal voltage is equal to Eg minus Ia into total resistance drop. Here Eg is constant because of saturation, but resistance drop keep on increasing whenever current increases. Whenever x-axis current increases, resistance drop keep on increasing. Because of the increase in this resistance drop, you will find drop in the terminal voltage. So therefore, up to saturation, you will find rise in the voltage, but beyond saturation, you will find the drop in the terminal voltage. Okay. What is the reason for this drop in terminal voltage? Resistance drop. Total resistance drop. That is armature resistance as well as series field resistance. Okay. This is before saturation. This is rated characteristics, guys. This is after saturation. Generally, we will operate the machine in the saturation zone or in the linear zone. In the linear zone means before saturation. Before saturation means this machine will offer rising voltage characteristics or drooping voltage characteristics, rising voltage characteristics. So, DC series generator offers rising voltage characteristics. Rising voltage characteristics. Got it? What about DC shunt generator? DC shunt generator offers drooping voltage characteristics. DC series generator offers rising voltage characteristics. Okay? Clear? Okay. Now, once we understand shunt and series generator characteristics, we will try to develop now compound generator characteristics. That is not so important. It is a combination of shunt and series. Okay. So I will skip that part because it is not not so important. If you understand shunt characteristics and series characteristics, that is sufficient. Okay. If I take compound characteristics also, it will the time keep on going. Okay. We can't cover other topics. Okay. So anything simple points. Shunt generator will offer drooping voltage characteristics. Series generator will offer rising voltage characteristics. What are the rules to be satisfied to develop EMF in shunt machine? Yes, residual flux is mandatory. Next one, connection of field winding. Okay, that is very important. The polarities must be satisfied such that additional flux will join the residual flux so that resultant flux increases. Third rule, field resistance must be always less than critical resistance. Speed must be always more than critical speed. Now, there was one question in the previous GATE exam related to this concept. Okay, so I will add that question, you try to understand. Okay, so okay, so read this problem. A self-excited shunt generator fails to build up the voltage. When the machine will fail? When the machine will fail? If field circuit is open, yes, machine will fail. Why? Because if the field circuit is open, current will not go through field winding. Yes or not? When current does not go through field winding, additional flux cannot be created. Only residual flux will be available in the machine. Resultant flux does not increase. Therefore, development of EMF is not possible. Armature circuit is open. Yes, even if armature circuit is open, machine will fail. Why? Because shunt generator means the circuit is like this. This is armature, guys. This is a field. Okay. Suppose if field is open, field current is 0. What if armature is open? If armature circuit is open, again can I say field current is 0 only? Because armature open means there is no current to field. Therefore, even in the second case also, development of EMF is not possible. Next, residual flux is absent. Yes, if residual flux is absent, we can't develop the EMF. If residual flux is absent, we can't develop the EMF, right? 1 second, guys. Okay, next. What happens if direction of rotation is wrong? This is also correct, guys. Even if direction of rotation is wrong, what happens is here residual voltage polarity will change, guys. Okay, so usually it is plus minus voltage, but when you rotate the rotor in opposite direction, then it will become minus plus voltage. Okay, because of that minus plus voltage, the current will generate in the reverse direction and it will flow like this. Therefore, when you rotate the rotor in opposite direction, whatever residual voltage is inducing here, its polarity will reverse. That current will go in the opposite direction through field winding. Therefore, additional flux will demagnetize from residual flux. Resultant flux becomes 0. Development of EMF is not possible. So, all these 4 conditions will fail the machine to develop the voltage. Therefore, the answer will become option C. Got it? Yes. That's it. This is about characteristics of DC generators. With this, we conclude generators part. Now we will quickly go through motors part. Okay? Yes. First of all, you understand motor means it is a machine which converts electrical form of energy into mechanical form of energy, right? And construction wise, both are absolutely same. Okay? Okay, so now let us understand DC motors. First, we will try to understand what is the operating principle of a motoring machine. It's a very simple operation, guys. Motors will operate based on a simple principle known as Lorentz force equation. Okay, Lorentz force equation. What Lorentz force equation states that whenever a current carrying conductor is placed inside a magnetic field, it will experience a force on it. And because of that force, the machine started to rotate. Okay, now you see a simple point. Imagine I have a magnetic field here. A north pole and a south pole is there. Flux will always flow from north pole to south pole. And imagine in this magnetic field, let us say there were two conductors. Let us call them as conductor A, conductor B. And as it is a motor, this machine will generate current for us, or we have to supply current to it. We have to supply current to it. Let us say I am giving current out of the plane here into the plane here. Indirectly, I am supplying the current, guys. Please understand it. We are supplying the current to the machine. That's why current direction is decided by source. That means supplier will decide the current polarity. Okay, now this is a normal conductor or current carrying conductor. Current carrying conductor. Whenever current carrying conductor is placed inside a magnetic field, it will experience a force. How to identify the direction of force? Fleming's left hand rule. According to Fleming's left hand rule, thumb will represent the direction of force. Point finger will represent the direction of magnetic field. Central finger will represent the direction of current. Okay, so if you know magnetic field direction and current direction, you can easily find out the direction of force. Let us practice here. In the morning, we discussed about Fleming's right hand rule. That is to identify the polarity of EMF. Now, Fleming's left hand rule to identify the direction of force. So see, magnetic field is from north pole to south pole. Current is out of the plane here. In this conductor, current was out of the plane. My central finger was out of the plane. So what my thumb is representing? The direction of force experienced by the conductor. Therefore, the force is in upward direction. In a similar manner, this conductor, the force will be in downward direction. And you tell me, these two forces together will rotate the machine in which direction, guys? Clockwise direction. That is torque. The torque is created in clockwise direction. Because of this torque, the machine started to rotate in clockwise direction. That means you tell me rotation is creating the torque, or torque is creating the rotation. The torque is creating the rotation. Got it? So therefore, now the machine is stationary or rotating? Yes, the machine was rotating. In which direction the machine is rotating? Clockwise direction. Because the machine is rotating, EMF will start inducing. Because now they are normal conductors or they are normal conductors or rotating conductors. Rotating. Whenever conductors are moving inside a magnetic field, EMF will be induced according to Faraday's law. How to find out EMF polarity? Fleming's right hand rule. And if you find EMF polarity, you will get EMF cross here, EMF dot here. Therefore, what is your understanding? In case of a DC motor, the current direction and EMF direction both are opposite. Alright. Whereas in generator, EMF direction and current direction both are same. But here, current direction is opposite to EMF direction. That is why in a motor, the EMF is known as back EMF. The EMF is called as back EMF. Why? Because it is opposing the current flow. Because you see EMF, current both are opposite direction. Okay, we call it as back EMF. But the formula will be same. Principle is the same. Only thing is that in a generator, EMF will generate the current, but in a motor, EMF will oppose the current flow. Okay, so anyway, because of this force only, the machine started to rotate, and it is a self-starting motor. DC motor is a self-starting motor. Okay, right. Now let us draw the equivalent circuit of DC motor. Equivalent circuit of DC motor. The only difference is current flow, guys. In case of a generator, machine will generate the current. In case of a motor, machine will take the current. Okay, so see, this is the armature circuit of the motor. Armature resistance. This is induced EMF, but this time the EMF is known as back EMF. And armature current is taken by the machine. This is not generated by the machine, this is taken by the machine. And this is armature resistance. Okay. Okay. Now here the terminal voltage will be there. This is the terminal voltage. Remember guys, this terminal voltage is not output load voltage. This time it is input source voltage. Okay, this is a source voltage. From this source, the machine will draw the current. The machine will draw the current, not generating the current. Okay, so what will happen? Procedure you see. You give the supply voltage. From the supply voltage, machine will draw the current. And those current carrying conductors will experience a force. Because of the force, machine will rotate. Because of the rotation, EMF is induced. Therefore, EMF induction is last stage, right? First current will flow, then force is created, then machine will rotate. That rotation will induce EMF. Okay. And then field winding is as usual. Just like DC generator, even in DC motor also, we need time invariant field. Therefore, the field circuit is DC excited. Okay. So this is, equivalent circuit of a DC motor. Okay. What is the only difference you are observing? Current direction reverses. In a generator, current will flow from EG to VT, but here it was flowing from VT to EB. And if you look at this circuit, is it not looking like a separately excited DC motor? Simply, I can directly write down this is separately excited DC motor. Why it is a separately excited DC motor? Because the field winding is excited using an external DC source. A separate DC source we are using to excite the field winding. Therefore, it is a separately excited DC motor. Got it? Important thing is, okay, important thing is, VT is not load voltage this time, guys. VT is a source voltage. Generally, that source is infinite bus bar. A DC bus bar we will use. That bus bar voltage will be used as a source. As it is a bus bar voltage, usually it is always a constant value. Okay, bus bar voltage is usually a constant value. Got it? Okay. Now let us write down various KVL and KCL equations here. Let us write down the KVL equation for the field circuit. What is the KVL equation? IF is equal to VF by RF, correct? Or let me rewrite. For field circuit, let us write down the KVL equation. VF is equal to IF into RF. From this, IF is equal to VF divided by RF. Suppose if this external DC voltage is a battery, let us say, constant voltage, then field current will be a constant value. If field current is a constant value, then field flux is also a constant value. Field flux is also a constant value. Got it? So always remember, separate excitation means flux is almost a constant value. Got it? Next, let us write down the KVL equation here. What is the first observation? Armature current or line current, both are same, right? It's a single loop. So armature current is equal to line current. Next, current was flowing from VT to EB, guys. Therefore, EB is lower voltage. EB is less than VT. And write the KVL equation, start with VT because current was flowing from VT. Therefore, VT is equal to, in the direction of the current, first drop is at brushes. After brushes, armature resistance, then back EMF. Brush drop is very small, you can neglect it. Therefore, what is the back EMF equation? EB is equal to VT minus IA RA. Now you compare this equation with generator equation that we have written in the morning session. If you look at the same equation in a separately excited DC generator, EG is equal to VT plus IARA. But here EB is equal to VT minus IARA. That means what is happening? Current direction reverses. That's why plus IARA becomes minus IARA. Got it? Now, apart from these circuit equations, we have certain performance equations we discussed already in the generators. What is the EMF equation? EG. Here it is EB. Ka phi into omega. Same formula. What is the torque equation? Ka phi into Ia. Got it? And what is the power generated by the machine? This time the power generation is a mechanical power generation, because this machine was converting electrical power to mechanical power. Therefore, the generated power is mechanical power generated. So the formula will be Eb into Ia, or torque into speed in radian per second. These are the performance equations for the machine. Okay. Right. And another important observation is, who will decide the current drawn by the motor? Who will decide the current drawn by the motor? The load will decide. Generally, if the machine was not connected to any load, the current will be almost equal to 0. If the load increases, the current drawn by the motor will also increase. I am not proving it. In regular class, we will prove it. Why current is dependent on load only. But you try to understand here in a simple shortcut. If load is 0, current drawn by motor is 0. Okay. Generally, a very small current will be drawn to overcome losses. But generally, losses are very low. Therefore, I am neglecting no load current. If load is very low, current drawn by motor is almost neglected. And whenever load increases, current drawn by motor will also increase. Okay, so the current drawn by DC motor, especially armature current drawn by DC motor, is dependent on the mechanical load. Okay, armature current drawn by DC motor is dependent on mechanical load. Armature current drawn by DC motor is proportional to load. Is proportional to load. If load is 0, the load means what? Mechanical load. If the shaft was not connected to any load, then the current drawn by motor is very, very small. You can neglect it. Right. Now, we will try to answer one question related to separately excited DC motor. Then we will take a break. Okay. Right. Okay, all of you go through this question. Yes, go through this question. A separately excited DC motor supplied from 400 volt is rotating at 1000 rpm during no load condition with negligible armature current. Just now I told you, no load current condition means armature current is almost neglected. Armature resistance is 0.1 ohm. Now, voltage is modified. They said very clearly voltage is modified and a full load torque is applied. Motor is rotating at 900 rpm. With the same voltage, load torque is reduced to half of full load. The speed is increased to 920 rpm. What is the magnitude of current during a full load is the question. It's a 2 marks problem and it is a previous GATE question only. It is a previous GATE question. 2 marks problem. Okay, first you need to understand here there are 3 cases in this problem. Okay, there are 3 cases. First case is no load condition. You can clearly see no load. Second case is now armature, now voltage is modified and full load torque is applied. This is the second case. And third case is half load torque. Half of full load torque is applied. Load torque is reduced to half of full load. Therefore, overall, 3 cases are available in the problem. Let me note down the details. Important thing is machine is separately excited. Therefore, flux is a constant value. Got it? Okay. So let us note down no load condition first. That is like case number 1. Case number 1, which is no load condition. No load condition. Okay. So what is the supply voltage during no load condition? 400 volt. So the voltage in the first case was 400 volt. And no load means armature current is negligible, I told you. So armature current was 0 ampere. And machine was rotating at how much speed during no load condition? 1000 rpm. The speed was 1000 rpm. Okay. So the moment when the data was given, immediately find out back EMF of the motor. What is the back EMF of the motor? back EMF is always equal to Vt minus Ia into Ra. But right now Ia is 0. Therefore, back EMF is equal to terminal voltage, which is a 400 volt. Clear. First case is done. Now in the second case, what was happened, guys? Now voltage is modified. That means in the next case, the voltage value is not 400, it's a different value. Okay. Case number 2. This is full load torque. Full load torque case, right? And the voltage was modified. I don't know what is the new terminal voltage. But the torque I know. What is the torque? Full load torque. Okay. And you tell me, in this particular case, machine is rotating at how much speed? 900 RPM. Now the speed was reduced to 900 RPM. What is the current drawn by the motor? I don't know. This is the answer we have to find actually. Why current is not 0 this time? Because the load is connected. As the load was connected, current drawn by the motor is not 0, it's a finite value. This is the current drawn at full load. I think this is the answer you need. Right or not? Okay. So see, speed changes, right? When speed changes from 1000 to 900, can I say back EMF will also change? What is the formula for back EMF in terms of speed? Back EMF is equal to Ka phi into omega. Flux is constant since this machine is separately excited. Therefore, back EMF is directly proportional to speed. So from this I can write EB1 divided by EB2 is equal to N1 divided by N2. So what is the back EMF in the first case? 400. Back EMF in the second case, I don't know, I have to calculate it. Speed in the first case 1000, speed in the second case 900. If you cross multiply, you will get the new back EMF. Second case back EMF. Is it not 360 volt? Yes. Okay, I got this back EMF using performance equation. Now let me also use KVL equation. What if I use KVL equation? The new back EMF is equal to new terminal voltage minus Ia2 into Ra. Back EMF 360, terminal voltage I don't know, armature current I don't know, but resistance was known, right? What is the resistance? 0.1 ohm, correct? This is a 2 marks problem, guys. It's slightly difficult, okay? It's a previous GATE question only. So from this, Vt2 is equal to 360 plus 0.1 Ia2. This is like one equation. Okay, now let's move to the third case. In the third case, what happened? You please continue the problem. With the same terminal voltage, with the same voltage. That means in the third case, voltage is the same as the second case. The load torque is reduced to half of full load and the speed increases to 920 RPM. See, now let us move to case number 3. I will write here. Case number 3, this is half load torque. Half load torque. Okay, but the same voltage they are using. That means third case voltage is the same as second case voltage. Both are unknown only. But the torque is half load torque. Half of full load. And the speed is changed to 920 RPM. Okay. And current also changes, right? Why current will change? Why current will change? Because the load changes. Whenever load changes, current drawn by motor will also change. Okay. Never assume current constant. Therefore, find out what is the new back EMF. Once again, back EMF is equal to Ka phi into omega, flux constant. So back EMF is only proportional to speed. Why flux is constant, guys? It's a separately excited motor. So therefore, EB2 by EB3, second case by third case is equal to second case speed by third case speed. What is the back EMF in the second case? 360. By back EMF in the third case, I don't know, I have to calculate. Speed in the second case 900, speed in the third case 920, cross multiply, you will get the back EMF in the third case. Let me get my calculator. Calculate the back EMF in the third case now, cross multiply. (920 by 900) into 360. 368 volt. So the back EMF in the third case is 368 volt. This is the back EMF in the third case. I used performance equation. Let me also use KVL equation. What is the KVL equation in the third case? EB3 is equal to VT3 minus IA3 into RA. EB3 is 368. Can I say VT3 or VT2 both are same? Why? Because same voltage they are using. Minus IA3 into RA 0.1. So from this VT2 is equal to 360 plus 0.1 IA3. This is like one more equation. You see the previous equation, VT2 one equation we got. Once again we got VT2 equation only. As both are VT2, can I both equate both of them? Let's say this is equation 2, this is equation 1. If I equate both equations, yes, I can write, therefore 360 plus 0.1 IA2 is equal to 368 plus 0.1 IA3. So if you find a relation between IA2 and IA3, you can solve the problem. How do you find relation between IA2 and IA3? Yes, that is where torque information you have to use. In the second case, the torque was a full load torque. In the third case, the torque was half of the full load torque. What is the formula for torque? Torque is equal to Ka phi into Ia. And remember, it is separately excited, so flux is constant, therefore torque is proportional to Ia. So second case torque by third case torque is equal to Ia2 by Ia3. Okay, second case full load torque, guys. Third case half of full load torque is equal to Ia2 by Ia3. You cross multiply, therefore Ia3 is equal to 0.5 times of Ia2. I just equated the torque. As torque becomes half, current also becomes half. Now you use this Ia3 here, therefore you can solve the problem. So 360 plus 0.1 Ia2 is equal to 368 plus 0.1 into what is Ia3? 0.5 Ia2. And you solve it, you will get Ia2. And remember, Ia2 means it is the current drawn by the motor in the second case. Second case means what? Full load. It is the current drawn by the motor at full load. It is the current drawn by the motor at full load. Please solve this and let me know what is the current value. All of you, solve it and let me know the current value. Yes, come on. Yes, 160 ampere. Correct. Correct, Rohan Singh. 160 ampere. That is the current drawn by the motor in the second case. Second case means full load. Got it? Second case means full load. Okay, if you read the problem carefully, they are asking us to calculate, look at the last line, magnitude of current drawn during full load. Full load means the second case only, right? Therefore, I asked what is the current drawn by the motor, that was 160 ampere, correct? Okay, that's it. So, three cases. First, no load. We know no load current is 0. So, back EMF is equal to terminal voltage. And then full load case, calculate the new back EMF. Two equations I am using in the entire problem. One is a performance equation for back EMF. Another one is KVL equation. Got it? Right. Fine, guys. Let's have a lunch break. And then we will meet after the break again. Okay? So, let's take 20 minutes break. Okay? Right, guys? We will meet after the lunch. Okay guys, welcome back. So we discussed about separately excited DC motor, and we understood one problem also related to separately excited DC motor. Now let's move to our next discussion, that is shunt excited DC motor. Okay. Now just like a shunt excited DC generator, we have a shunt excited DC motor. Okay, field winding will be connected in shunt with armature circuit. So this is just like a revision now for you, because we already studied generator circuits. Now motor circuits are very simple, because the only difference is current direction will reverse. That's all. Okay. So see here, this is the armature circuit, back EMF of the motor, armature resistance and armature current. Okay. So field winding will be connected in shunt with armature. So this is a field resistance, this is a field current, this is armature current. Remember, the arrow marks are important. The motor was drawing the current, not generating the current. Okay. So this is terminal voltage. This terminal voltage is nothing but a DC bus bar voltage. Therefore, it is generally a constant value unless you modify it. Okay. So this is shunt excited DC motor. Now let us write down various KVL and KCL equations here. Okay. So first let us write down the KCL equation here. Line current was going towards the node, armature current and field current were leaving. Therefore the KCL equation is line current IL is equal to IA plus IF. Okay. From this, what is IA is equal to? IA is equal to IL minus IF. What is the same equation in shunt generator? In shunt generator, IA is equal to IL plus IF, but in shunt motor, IA is equal to IL minus IF. Also, what is the formula for field current? Okay, it is a shunt motor, right? If this voltage is Vt, can I say the voltage across this winding is also Vt? Therefore, the field current is Vt divided by Rf. Vt divided by Rf. Got it? Okay, and as I told you, this Vt is generally a bus bar voltage. Bus bar means it is a constant value. If Vt is a constant value, then can I say field current is also a constant value? Unless you change this Vt or field resistance, field current is constant. The moment I said field current is constant, indirectly field flux is also a constant value. Got it? Field flux is also constant. Okay, therefore it is very important in case of a shunt motor, as long as you keep supply voltage constant, field current and field flux are going to be constants. Okay. Next, write down the KVL equation, same KVL equation. EB is equal to Vt minus Ia Ra. In shunt generator, what is this formula? Eg is equal to Vt plus Ia Ra. In shunt motor, just a moment guys. Yes, in shunt generator, Eg is equal to Vt plus IaRa. In shunt motor, Eb is equal to Vt minus IaRa. Got it? Okay. Now, let us solve one question related to shunt motor also before moving to series motor. What is the KCL equation in shunt generator? In a shunt generator, Ia is equal to IL plus IF. In a shunt motor, Ia is equal to IL minus IF. Okay. Let us solve one question. Okay. So read this problem. A shunt generator delivers 50 kilowatt at 250 volt and 400 RPM. The armature and field resistances are 0.02 ohm and 50 ohm. Calculate the speed of the machine running as a shunt motor and taking 50 kilowatt input and 250 volt. Okay. See, interesting question. In the first case, the machine is acting like a shunt generator and it is delivering an output power of 50 kilowatt at 250 volt and 400 RPM. This is generator details. In the next case, the same machine is operated as a motor In the next case, the machine is operating as a motor and motor means it will absorb the power. It is taking 50 kilowatt input at 250 volt. What is the speed of the motor? Therefore, there are two cases in the problem. First case, the machine is acting like a generator. In the next case, the machine is acting like a motor. So what I will do is that I will take first generator case. I will try to calculate EG. Next, I will take motor case. I will try to calculate EB. When you know EG and EB, you can easily relate the speed value. Okay. So let us take case number 1. That means when the machine is like a generator. Yes. What is the details about generator? Delivers output power. The output power of the generator was 50 kilowatt. At how much voltage? 250 volt. With how much speed? 400 RPM. Okay. And what is the formula for output power of a shunt generator? Output power means indirectly load power. Load power is nothing but load voltage into load current. Okay. So what is the formula for load voltage? VT, load current IL. So this is 50 kilowatt, that is 50 into 10 power 3. Voltage was 250. So you calculate what is the load current IL. So you will get load current IL. So solve it. Let me get my calculator. I think it is 200 ampere, right? 250 cancels 4 times in 1000. 4 into 50, that is 200 ampere. Okay. So the load current was 200 ampere. Okay, after finding load current, you also calculate the field current. What is the formula for field current in shunt generator? VT divided by RF. Here, VT was 250 and field resistance was 50, right? Therefore, 5 amperes was going to field circuit. Now I know the load current and field current. Can I calculate armature current? Yes, armature current is equal to IL plus IF, that is 205 ampere. Okay, I got 205 ampere as armature current. Once I know armature current, calculate generated EMF of the machine. What is the formula for generated EMF? Generated EMF is equal to VT plus IA RA. VT was 250, IA was 205. What is armature resistance we got? 0.02, right? 0.02. Therefore, we will get generated EMF. Let me solve it. So 250 plus 205 into 0.02. Yes, 254.1. This is the voltage of the machine when it is acting like a generator. Okay. Now, in the second case, the same machine is used as a motor. Okay. So, now the motoring machine. But the data is very important. When it is acting like a motor and taking 50 kilowatt input, this is input power now. Okay. Yes. So in the motor case also, terminal voltage was same 250, but this time the input for power was 50 kilowatt, correct? Yes, input power was 50 kilowatt. What is mean by input power of any system? Can I say input power is nothing but input voltage into input current? For a shunt motor, what is mean by input voltage? VT, input current IL. Therefore, input power is VT into IL. Okay, so therefore, the input power is VT into IL. That means what? In a generator, output power is VT into IL. In motor, input power is VT into IL. So now the input power was 50 kilowatt. Voltage was 250. You will get the line current. I think you will get the same line current. How much? 200 ampere. Okay. What about field current? I think field current is also same. Why field current is same? Because terminal voltage is same, right? Even in the motor case also, the terminal voltage was same, 250. Okay. So therefore, this is 250 divided by field resistance 50. Field current is again 5 ampere. But armature current will change. Why? Because the KCL equation is different. What is the formula for armature current in shunt motor? IL minus IF. This will become 245 ampere. That is armature current. The moment I know armature current, I can calculate back EMF of the motor. What is the formula for back EMF? VT minus IARA. So this problem is all about whether you know the difference between motor formulas and generator formulas or not. Okay, so what is the terminal voltage? 250 minus armature current 245, armature resistance 0.02. Just to solve it, you will get the answer for back EMF of the motor. Okay, so let's see. 250 minus 245 into 0.02. So the answer is 245.1 volt. That is the back EMF of the motor. Now that I know generated EMF of the machine and back EMF of the machine, can I find a relation between the two? Because we know, I will solve here, or else I'll go to the next page. Because we know EMF is equal to Ka phi into omega. Who will decide the magnitude of the flux? Flux will be based on field current. What is the field current in generator case? 5 ampere. What is the field current in motor case? Also 5 ampere. Therefore, field current is same in both cases. That means flux is constant. Flux is constant. The moment I say flux is constant, EMF is directly proportional to speed only. Therefore, generator EMF by motor EMF is equal to generator speed by motor speed. What is generator EMF we got? 254.1. What is the motor EMF we got? Motor EMF 245.1 is equal to, what is the generator speed? 400 RPM. Find the motor speed now. Okay, therefore if you cross multiply, the motor speed will be equal to, just solve it. Yes, motor speed is equal to 245.1 into 400 divided by 254.1. Yes, the motor speed will be 385.83 RPM. Yes, I hope all of you got the same answer. 385.83 RPM. Okay.
Responsible for the security of railway property and passengers. 385.8 RPFA possible interpretation. Without further context, it's difficult to say definitively what 385.
Clear?
Here are possible interpretations. 1. RPF. The railway recruitment.
Yes. So this is about the observation. Simple problem, but only thing is that whether you know the difference between generator equations and motor equations or not. Okay. Right. Fine. What is the armature current? Did I make any mistake? Okay, armature current was 195. I think I wrote 245. Yes, correct. This is 195 ampere. Please correct it. IL was 200. I thought 250. IL was 200. 200 minus 5. This is 195. Therefore, this also becomes 195. The values will slightly change. Okay, because the resistance is very small, you don't get a major change. Okay, so 250 minus 195, 250 minus 195 into 0.02, this is 246.1. Okay, and the same variation you can observe here also. 246.1 into 400 by 254.1. 387. 387.4 RPM. Got it? So this is a question related to a shunt motor. Okay, very simple. Once you know generator equations, motor equations are nothing, just the reversal of the current you need to observe. Okay, now we will try to discuss about series excited motor. Just like a series generator, we are discussing about a series motor. We know what is mean by series excitation, right? Field winding will be connected in series with armature. So this is the armature circuit of the motor. This is the back EMF EB, armature current IA, armature resistance RA, and field winding will be connected in series with armature. Okay, so here we have the supply terminal voltage. So this is the line current IL, field resistance RF, field current IF, armature current IA. Got it? Okay, this is about a DC series motor. Fine. Now let us write down various relations. Very simple. All currents are equal, right? In series motor, armature current or field current or line current all are equal. We know flux is always depends upon field current, right? We know flux always proportional to field current. But in series motor, field current and armature current both are same. Therefore, flux is proportional to armature current as well. And you try to understand that armature current will never be a constant value. It will change whenever load changes. I told you current drawn by motor is always depends upon load condition. Whenever load changes, armature current will change, thereby the flux also changes. And what will be the KVL equation? EB is equal to VT minus IA into RA plus RF, because both currents are equal, and that is what we call it as a total resistance drop. IA into total resistance drop. This is the back EMF of a series motor. What is the only difference between series motor and shunt motor? In case of shunt motor, flux is a constant value as long as you keep supply voltage constant. Okay, but in case of a series motor, flux is changing. Okay, whenever load changes, flux changes. That is a crucial observation everybody has to understand. Okay, now we will answer one question related to series motor diagram also. Okay, let us answer one question. Right. Okay, so read this problem. A 500 volt DC series motor driving full load torque at 1200 RPM by drawing 100 ampere from the source. Total resistance of the motor is 0.2 ohm. Now, load is reduced to half. See the load in the sense load torque. The load torque is reduced to half. What is the new speed of the motor is the question. Therefore, there are two cases in this problem. In the first case, motor was driving full load torque. This is case number 1. In the next case, the motor was rotating half load torque. This is the second case. So what I will do is that I will take first case, I will calculate back EMF of the motor. I will go to the next case. As the load changes, armature current will change. Find the new armature current, because I told you current drawn by motor is always dependent upon the load. As the load changes, armature current will change. Find the new armature current. Once you know what is the new armature current, find out what is the new back EMF. Using that new back EMF value, find out what is the new speed. That's the idea. Okay. So let us take case number 1. Case number 1. In case number 1, what is the supply voltage of the motor? 500 volt. And how much torque the machine is driving? Full load torque. Therefore, the torque in the first case was full load torque. And the motor was rotating at 1200 RPM. The speed is 1200 RPM. And drawing how much current? 100 ampere. Therefore, armature current or field current, line current, all are same because it is a series motor. Now, using this information, find out what is the back EMF of the motor. What is the formula for back EMF? Back EMF formula is equal to Vt minus Ia into total resistance drop, that is armature resistance plus field resistance. So Vt was 500, armature current was 100, total resistance is given, right, 0.2. Therefore, this was 480 volt. This is the back EMF of the motor in the first case. Completed. Now we will move to the next case now. In the next case, what was the modification happened? Torque is reduced to half. Okay, let's move to case number 2. In case number 2, no change in supply voltage, guys. Supply voltage was once again 500. Since in the question there is no information that voltage modified. That means you have to believe it is a DC bus bar. DC bus bar means voltage is always constant. Okay, but what was the modification? The torque is now reduced to half of full load. Whenever torque changes, can I say armature current will change? Thereby you find out what is the new speed of the motor. So the important data is find the new armature current. That is your first task. To find out the new current, you just understand what was the change in the torque. What is the torque equation? First of all, we know that torque is equal to Ka phi into Ia. And remember, it is a series motor, and in series motor flux is not constant, flux is proportional to armature current. Then is it not looking like a torque proportional to armature current into armature current? Therefore torque is proportional to what? Ia square. So therefore torque is proportional to Ia square. Very important. If it is a shunt motor, this flux would have been constant, so torque is only proportional to Ia. But is a series motor, torque is proportional to Ia square. As it is proportional to Ia square, first case torque by second case torque is equal to first case current by second case current whole square. What is the torque in the first case? Full load, right? What is the torque in the second case? Half of full load, is equal to armature current in the first case 100. Find out the new armature current Ia2. So here torque will cancel. You can easily find out new armature current. I think it is 1 by root 2 times, correct? So probably 100 by root 2. Yes, it was 70.7 amperes. Okay, this is the armature current in the second case. The moment I know armature current, calculate the new back EMF. What is the formula for new back EMF? KVL equation. Vt minus Ia into total resistance drop. So Vt was the same 500, but armature current was 70.7. Armature resistance was 0.2. So let me find out the back EMF. Okay, 485.85 volt. This is the new back EMF. The moment you know new back EMF, how to find out new speed? Use the performance equation. Back EMF is equal to Ka phi into omega. And remember, flux is proportional to armature current here, guys. Armature current into speed. Suppose if it is a separately excited motor or shunt motor, this flux would have been constant. Then back EMF is only proportional to speed. But this motor is a series motor, so flux is proportional to armature current. So from here I can write back EMF in the first case divided by back EMF in the second case is armature current in the first case by armature current in the second case into N1 by N2. Now you know what is the back EMF in the first case. We already calculated 480 by what is the back EMF in the second case? 485.85. 0.85 is equal to armature current in the first case 100 ampere, armature current in the second case 70.7, speed in the first case. What is the speed in the first case? 1200 rpm. And find out what is the speed in the second case. You will get the answer for N2. Separate N2 and let me know the answer. Come on, do it. Yes, what is N2? Okay, so if you cross multiply, you'll get everything. 485.85 into 100 into 1200 divided by, yes, I am getting 1717 rpm. 1717 rpm. That is the new speed of the motor. That is the new speed of the motor. I am doing it here. 1717 rpm. This is the speed of the motor when the torque was reduced to half of full load. Okay. So very important observation is it is a series motor, guys. In case of series motor, flux is not a constant value. Flux is proportional to armature current. Flux is proportional to armature current. Okay. Yes. That's all. Fine. Okay. Now, Similarly, you can understand, compound motor also. Once again, it is a combination of shunt and series. Just like generator, you can develop the equations even for compound motor as well. Okay, so I will quickly go through them. You have idea already. Compound motors are having two connections, right? Short shunt connection and long shunt connection. This is a short shunt connection, back EMF, armature current and armature resistance. You first connect a shunt winding, later connect a series winding. Okay. So here we have the terminal voltage. This is a series current. This is armature current, shunt current and shunt resistance. Got it? And this is the line current as well. This is short shunt compound connection. But it's a motor, that's all. Okay, short shunt compound connection. Similarly, long shunt compound connection, I don't want to draw it again. First you connect a series winding here, later shunt winding will come. Okay, so the only difference is current direction reverses. Okay, if I write the formulas here, line current and series current both are equal. And KCL equation, armature current is equal to line current minus shunt field current. And shunt field current will be equal to Vt minus ISE RSE by RSH. KVL equation will be Vb is equal to Vt minus IA RA drop and ISE RSE drop. That's all. These are the simple equations related to compound excited DC motor. All right. Compound excited DC motor. Clear? Right. So now let us quickly move through the next topic. I am not drawing long shunt compound connection once again. A similar model we already studied in generators. So series winding will come here, later shunt winding will come here. Okay, simple. Right. Now let's move through speed control of DC motors. This is the next important topic. Speed control of DC motor. And we will discuss about speed control of shunt motor as well as a series motor. Okay. First of all, before developing speed control, very important topic, guys. Every year we will get one question from speed control topics. Okay. It may be speed control of DC motor or speed control of induction motor. Definitely one question will come. So listen carefully. So to understand the speed control problems, okay, it's usually 5-6 hours topic, but we will try to finish it within half an hour. Okay, only summary points I'll tell you. To control the speed of a DC motor, first we need to write speed equation, so that from equation we will understand how speed can be modified. You know what is a back EMF formula, right? Back EMF has two formulas. One is KVL equation, Vt minus IA RA. Another one is a performance equation, EB is equal to Ka phi into omega. As both are back EMFs only, let us equate both of them. Ka phi into omega is equal to Vt minus Ia into Ra. From this, speed omega is equal to Vt minus Ia Ra by Ka into phi. So this is the speed equation, guys. Now our aim is we wanted to change this speed. Yes, if you wanted to change the speed, you have three options. Okay, you change IA RA drop, speed will change. You change field flux value, speed will change. You change supply voltage value, again the speed will change. So in three ways we can control the speed of the motor. Okay, first one is armature resistance control method. Armature resistance control method. Okay, second one is field flux control method. Field flux control method. Third one is armature voltage control method. Armature voltage control method. Okay, so by using these three methods, we can control the speed of a given DC motor. Now we will try to understand armature resistance control method both in shunt motor as well as series motor. Field flux control method both in shunt motor and series motor. and voltage control method in shunt motor as well as series motor. Okay, right. Due to the time constraint, I may not be able to take all the topics that we have in DC machines. Important topics I am selecting. So let us see first one, armature resistance control method. Armature resistance control method. Right. First point is this method is used to control the speed of DC motor below the rated value. That means using this method, we can reduce the speed of the motor. We can't increase the speed of the motor. Okay. To control the speed of DC motor below its rated value. Below its rated value. Okay, that means we can reduce the speed of the motor, but we can't increase the speed of the motor. Okay, first point. Next, during this method, additional resistance will be added in series with armature circuit. Okay, additional resistance is added in series with armature circuit. In series with armature circuit. So what happens the moment you add additional resistance in series with armature circuit, this resistance drop value will increase because you are adding extra resistance, right? The moment when resistance drop increases, speed of the motor will decrease. Let's see what will happen in shunt motor and series motor. Suppose if I take a shunt motor, this is the armature circuit, guys. This is the back EMF of the motor, armature current and armature resistance. Okay. And here we have the field circuit, right? And here we have the supply voltage. Now, this is the circuit diagram of a DC shunt motor before adding any additional resistances. You can see I am not adding any additional resistance right now. That means the motor is under normal rated condition. Normal rated condition means this is the case before adding external resistance. Okay. Now, first question, what is a formula for field current? Field current is equal to Vt divided by Rf. And am I changing voltage in this method? No. I am adding just extra resistance, that's all. I am not changing voltage. Therefore, field current is constant. If field current is a constant value, flux is also a constant value, yes. Next, what is the formula for speed now? This is the first case, before adding external resistance. Speed formula, same formula I will use, same omega formula. Omega is equal to Vt minus Ia Ra, but as it is first case, before adding the resistance, assume the current is Ia1 by Ka into phi. Could you tell me why I am not writing any suffix for Vt? Because Vt is constant in this method. I am not changing voltage. Why there is no suffix number for phi? Because the flux is also constant. The only parameter that was changing is armature resistance drop. This is the speed before adding external resistance. Now what happens, see what I am doing is I am adding some external resistance in series with armature. Only in series with armature extra resistance was added, external resistance. Therefore, now this is the circuit after adding the resistance. Okay. So after adding external resistance, what is the new speed? Let us say omega 2. Yes, what is the formula? Vt changing or not changing? Not changing. Same Vt minus armature current Ia2. Why I am writing Ia2? Because this is a second case after adding resistance. Always remember, guys, never assume armature current is constant in the problem. Who will decide the magnitude of armature current? I told you many times, the load will decide. Whenever you create some disturbance in the machine, there is a chance that armature current may change. Whenever you disturb voltage or whenever you disturb resistance, whenever you disturb flux, any disturbance, there is chance that armature current may change. That will be decided by load. Therefore, I will never assume the new current same as the old current. That is Ia2. But Ia2 into Ra only or Ra plus R external? Ra plus R external by Ka into phi. This is the formula for speed after adding external resistance. Okay, so definitely because of this extra resistance, this resistance drop will increase. When resistance drop increases, speed will decrease. Therefore, omega 2 is less than omega 1. So this is the formula for speed whenever we add additional resistance in series with armature. And the same phenomena can be observed even with series motor as well. Let's go to series motor armature resistance control method. Imagine this is the armature part of a DC series motor. Field winding will be always connected in series with armature. Okay, this is a circuit diagram of a DC series motor. Okay, this is line current, field resistance, field current, and this is armature current. Got it? Now let us write down the speed equation before adding external resistance. First case, before external resistance was added, the speed formula omega 1 is equal to same formula Vt minus Ia1 into Ra plus Rf divided by Ka into phi 1. Remember, this is a series motor. In a series motor, never assume flux is constant. Who will decide the magnitude of the flux? Armature current will decide. It's a series motor, so flux is directly proportional to armature current, and armature current and field current both are equal, guys. First case, everything is first case. Now, after adding external resistance, where we are adding external resistance, guys? We are adding external resistance in series with armature circuit. Okay, in series with armature circuit, some external resistance is added. So see, the moment when extra resistance was added, indirectly a disturbance is created. So let us see what is the new speed equation now. Omega 2 is equal to Vt we are not changing, supply voltage is the same, minus, it is a new armature current, Ia2 into Ra plus Ref. In addition to that, extra resistance is also added, divided by Ka into phi 2, guys. Why I am writing phi 2? Why flux is changing? Armature current changes. Okay, so here I must write phi 2 is directly proportional to Ia2. Ia2 or If2 both are same. So because of this extra resistance, resistance drop will increase. Whenever resistance drop increases, speed will decrease. Therefore, armature resistance control method, both in shunt motor as well as series motor, yes, both in shunt motor and series motor, the addition of external resistance in series with armature will change the speed of the motor and the speed will be reduced. Okay, and one important thing is never assume current is constant, especially armature current. Who will decide armature current? The load. The load may be a constant torque load. The load may be a constant power load. The load may be a torque proportional to speed, square of the speed, like fan load. Any load it may be. The load will decide whether the current is constant or variable. Okay. So while solving the numerical questions, they will definitely mention you what is the type of the load they are using, and the load will decide whether the current is constant or variable. Okay. Fine. This is about armature resistance control method, and we can only reduce the speed, we can't increase the speed. Okay. Now, let us move to the next one, that is field flux control method. Field flux control. See, the idea of field flux control method is very simple. You reduce the magnitude of the flux, speed of the motor will increase. Got it or not? Therefore, field flux control method is used to increase the speed of the motor, not to decrease the speed of the motor. Got it? You may have a doubt, sir, why don't you increase the field flux? You can't increase the flux, guys, because saturation limit will be there. You can only reduce the flux. So whenever flux reduces, speed will increase. Let's see how can we reduce flux in shunt motor and series motor. So first we will see shunt motor, field flux control method. field flux control method. Okay, so once again I am taking shunt motor circuit diagram. So this is the back EMF of the motor, armature current and armature resistance. So field winding will be connected in shunt with armature. So this is the field resistance and this is the field current. And here we have the supply terminal voltage. Okay. So this is the line current and this is the armature current. Okay. So right now you can see there were no additional resistances added. Okay. So this is the case before adding the external resistance. Before adding external resistance, what is the speed of the motor? This is the first case. Vt minus Ia into Ra by Ka into phi 1. This time flux is variable, guys, because it is a flux control. Flux will depend upon field current. What is the formula for field current right now in this circuit? Voltage Vt, resistance is Rf, therefore field current is Vt divided by Rf. This is the first case. And this field current will create some field flux that will create some speed. Now let us see after adding the resistance. Now see where we are adding external resistance here. See, this time the external resistance is added in field circuit, guys. External resistance was added in field circuit. See, the moment when extra resistance is added in field circuit, what happens to field current? Decreases, because what is the formula for new field current now? If2. Yes, the new field current If2 is equal to Vt divided by not only Rf, in addition to this Rf, extra resistance was added. Due to this, field current decreases. Whenever field current decreases, flux also decreases, because flux is always dependent upon field current. When flux decreases, can I say speed of the motor will increase? Therefore, operating speed of the motor increases. Therefore, omega increases. So, will you tell me what is the new omega right now? Omega increases, fine. What is the new omega? So, the new omega is equal to, same formula, Vt minus, new case, it is Ia2. I told you any disturbance, armature current may change. Ia2 into Ra only. Remember, we are not adding additional resistance in armature circuit. We are adding additional resistance in field circuit. Okay. So, Ia2 into Ra by Ka into phi 2. Because the flux changes, right? This is the new speed equation. Here, phi 2 is less than phi 1 because the flux decreases. Therefore, omega 2 is more than omega 1. This is the new speed equation. So whenever flux decreases, speed of the motor will increase. Therefore, we can control the speed of the motor above the rated value or below the rated value, above the rated value. Got it? Above the rated value. Clear? Is there any issue? Is it clear now? Let me check once. Am I clear now? Yes? Okay. Hope I can continue, right? From my end, everything is clear. Let me check once. Okay. All right. So now let us try to understand how the same mechanism can be achieved in series motor. In series motor, how can we reduce the flux to increase the speed of the motor? Very simple. In case of shunt motor, you added additional resistance in series with shunt field winding so that field current decreases, flux decreases, speed increases, right? Now let us see how to do that same thing in case of a series motor now. So let us take a series motor diagram. Okay, so this is the armature circuit of the motor. This is the back EMF, armature current and armature resistance. Okay, this is how the field winding is connected in series with armature. Terminal voltage. This is the line current, field resistance, field current and armature current. So right now additional resistances are not added. There are no additional resistances added. Therefore, I will get rated speed here. Okay, this is the case before adding additional resistance. Okay, so what is the speed equation now? Omega 1 is equal to Vt minus Ia1. This is the first case, Ia1 into Ra plus field resistance Rf by Ka into phi 1. This is the first case. And here armature current or field current both are same guys. Flux is always proportional to field current. Now in the next case, the idea is we wanted to reduce the flux. To reduce the flux, we have to reduce field current. And in order to reduce field current, what we will do is that we will add an additional resistance in parallel with series field winding. See, we call it as a diverter resistance. An extra resistance was connected in parallel with field winding. See, the moment I connected extra resistance in parallel with field winding, entire current will now go through field winding, or some current is diverted. Some current is definitely diverted to this resistance. Because some amount of current diverted to this resistance, what happens to this current? Decreases, right or not? If a field current decreases, what about field flux also decreases? Thereby operating speed of the motor will also decrease. Sorry, operating speed will increase. When flux decreases, speed will increase. This is a second case, guys. Okay, so therefore after adding the resistance, after adding external resistance, yes, field current decreases, If decreases due to diverter resistance. Okay, diverter resistance. Yes, because If decreases, flux decreases. Okay, whenever flux decreases, speed increases. Okay, speed increases. What will be the new speed? Omega 2. Omega 2 is equal to Vt minus Ia2, the new armature current, Ia2 into, you look at this, for this Ia, Ra is available, the resistance drop, Ra plus, it is Rf only or Rf parallel to R external, Rf parallel to R external, Rf parallel to R external by Ka into phi 2, that is a new flux. And remember, because of this extra resistance, will you tell me field current and armature current are same now or different? This is the new field current If2. This is the new armature current Ia2. Can I say Ia2 and If2 both are not equal because of this parallel branch? Okay, you have to apply a current division rule there. Okay, so what I will do is that this is the field circuit, guys. This is the diverter resistance, extra resistance we added. This is the new field current If2. This is the new armature current Ia2. Now, by using a current division principle, you can find a relation between these two. Yes, that new field current If2 is the total armature current into opposite resistance by total resistance. Got it? That is how you can find out the relation between new field current and new armature current. Always remember, flux is proportional to field current. But this time, field current and armature current are not equal. There is a relation. This relation you have to follow. Okay. So, points are very simple. In case of shunt motor, how to reduce field flux? By adding extra resistance in field circuit, in series with field circuit. Okay. Okay. Now, in case of series motor, how to reduce field current? by adding additional resistance in parallel with field winding. That will divert the field current. Therefore, we call it as a field diverter control method. Okay, field diverter control method. Okay, field diverter control method. Clear? So, Neha, I think you got the difference between armature resistance control method and field. This is armature resistance control method. Resistance drop will increase, speed will decrease. This is a field diverter control method. Hope you got the difference between the two. Hope you understand. Okay, right. That's all. This is about speed control of DC series motor using a flux control. Flux control means always speed increases. That is to control the speed above the rated value, guys. That is to control the speed above the rated value. Got it? Okay. Now let us try to understand the last method, voltage control method. I told you there is another method, we call it as armature voltage control method. In any circuit, generally voltage is something that we can reduce or we can increase. Remember, voltage means we can only reduce it, we can't increase it. Why? Because if you try to increase the voltage, insulation may damage. So we can only reduce the voltage, we can't increase the voltage. So let's see voltage control method also. Okay. Variable voltage control method. See, in the previous two methods, we are keeping supply voltage constant. But in this method, we will try to control the speed of the motor by changing the supply voltage value. So let us do it with shunt motor first. This is the armature circuit of a shunt motor, back EMF, armature current and armature resistance. Field winding will be connected in shunt with armature. And here we have the supply voltage. Okay. So what is the formula for field current? Yes. So this is the circuit diagram of a shunt motor. Let us write down the speed equation. Omega is equal to Vt minus IaRa by Ka into phi. Remember guys, in this particular method, we are not going to add any additional resistances. As we are not adding any additional resistances, the only reason for a drop in voltage was IaRa drop is this can be neglected. Why? Because generally armature winding is designed with low resistance or very high resistance, very low resistance. As armature resistance is very, very low, IaRa drop can be usually neglected. If IaRa drop is neglected, the approximate omega equation is Vt by Ka into phi. But remember, don't neglect IaRa drop if extra resistance is added. You can neglect IaRa drop only when extra resistance was not added. Correct? Okay. Now, what we are doing? Our discussion is change the speed of the motor by changing this voltage. I told you voltage can only be reduced. So let us see what happens if Vt reduces by, let us say, 20%. I reduced the voltage by 20%. What is the immediate observation from the above equation? Whenever voltage reduces by 20%, we may assume the speed reduces by 20%. But that is not actually true. That is not actually true. Let us see why. Why? Because it is a shunt motor. In shunt motor, what is the formula for field current? The formula for field current is Vt by Rf. So, whenever you reduce voltage by 20%, field current will also reduce by 20%. When field current reduces by 20%, flux also reduces by 20%. So see what is happening now. Numerator reduces by 20%, denominator also reduces by 20%. That means ratio is constant. So if ratio is constant, indirectly speed is a constant value. Approximately speed is constant. That means the shunt motor speed cannot be controlled when voltage is varying. If whenever voltage varies, definitely field current also varying, thereby flux remains a constant value. Flux remains constant value. Therefore, what to do now? Sorry, not flux, speed is constant value. What to do now? Our aim is to change the speed, but speed was not changing, speed is constant. So what to do now? Yes, this is where you need to separately excite the motor. What happens if the field winding is separately excited? For example, if I am separately exciting this field winding, instead of shunt excitation, let us use separate excitation. If I use a separate excitation here, guys, then even though this terminal voltage changes, field current does not change because the field is separately excited. When field current was not changing, I can say field current is constant. When field current is constant, flux is constant. When flux is constant, speed is only dependent upon Vt. Therefore, whenever Vt decreases, speed decreases. Therefore, controlling the speed of a shunt motor using voltage variation is possible only when the field winding is separately excited. Only when the field winding is separately excited. Okay. Suppose if field is separately excited. If a field is separately excited, then flux would have been a constant value. Therefore, speed is only proportional to Vt. I am neglecting Ia Ra drop. Okay, because generally armature winding is designed using very low resistance. Therefore, Ia Ra drop is neglected. So, approximately speed is proportional to Vt. So, whenever Vt reduces, speed of the motor will also reduce. Correct? Speed of the motor will also reduce. Okay. Yes. Whereas in series motor, this is not the case. In series motor, whenever voltage reduces, speed will decrease. Okay. See, if it is a series motor, what will happen? This is the this is the back EMF of the motor, armature current, armature resistance. So here we have the field winding. This is the supply voltage. Okay. So this is a field resistance, field current. What is the speed equation, guys? Speed equation is equal to Vt minus Ia into RT, total resistance drop. The total resistance drop means Ra plus Rf. So now we are changing voltage value. Whenever voltage changes, whenever voltage reduces, the speed of the motor decreases. Okay, because this time flux will not change like shunt motor. In shunt motor, voltage and flux both are reduced by same percentage. But in series motor, that is not possible. In series motor, if you reduce voltage by let us say 10%, flux may not be 10%. It may change by 5% only or 4% only because there is no direct relation, right? Here, flux will depend upon current value or voltage value, current value. Whereas in shunt motor, flux will depend upon field current will depend upon this voltage. Got it? Okay. Therefore, in series motor, whenever voltage reduces, speed will definitely decrease because flux will not decrease by same percentage as voltage. Okay. That's why you don't need a separate excitation kind of thing in series motor. Whenever voltage reduces, speed will definitely decrease. Okay. So if I solve one numerical question, then you will get more clear idea. Okay. Right. So a 4 hours topic, I tried to finish in 20 minutes approximately. So because summary is more important, right? It's a last minute preparation. So just basic things are important. So I request all of you, take 2 minutes time, just take the video little backwards and you please read these problems once again, then we will solve numerical questions. Okay. 2 minutes, you just go back once and come back to the live again. Okay. I request all of you, please go through the formulas once again so that we can solve numerical questions. Okay. Just 2 minutes, guys. 2 minutes, you go back and come back. Come back to the video. This is a field diverter control method, guys. Okay. So we are diverting the field current. Therefore, field current decreases, flux decreases, speed increases. And variable voltage control method is not possible in shunt motor because speed remains constant even though you decrease the voltage. Minor change may be there if you consider IA drop, but generally IA drop is negligible. So therefore, speed is going to be constant. Clear? Now, in series motor, such scenario will not repeat. Whenever you change voltage, the speed of the motor will definitely change. Okay, guys, we are almost approaching 5 hours now. Okay, I wanted to take induction machine also today itself. So actually the plan is 10 hours video, 5 hours for DC, 5 hours for induction. So we are almost at the end. Please make it fast. It's a vast subject, you know, machines. It's not possible to cover in a single video or a short period of time. Okay. Now, let us solve some numerical questions related to this concept, speed control. Okay. So let me take the first question. Okay. All right. Read this problem. A shunt motor supplied at 250 volt runs at 900 rpm. Armature current drawn is 30 ampere. The resistance of the armature circuit is 0.4 ohm. The resistance required in series with the armature to reduce the speed to 600 rpm when armature current is 20 ampere. See, first case armature current was 30 ampere, second case armature current was 20 ampere. What is the resistance required in armature circuit in series with armature circuit to reduce the speed to 600 rpm? Therefore, here two cases are there. First case is before adding external resistance in armature circuit. Second case is after adding external resistance in armature circuit. Got it? So let us take first case and calculate the back EMF of the motor. So first case is before adding external resistance. What is the terminal voltage of the motor? 250 volt. Terminal voltage is constant in this method, right? And what is the armature current in the first case? 30 ampere. IA1 was 30 ampere. And what is the speed of the motor? 900 rpm. Machine was rotating at 900 rpm initially. So calculate what is the back EMF of the motor. What is the formula for back EMF? Back EMF is equal to Vt minus Ia into Ra. Vt was 250. Armature current was 30. What is armature resistance? 0.4. Okay. So therefore, back EMF is equal to 238 volt. This is the back EMF of the motor in the first case where the motor was rotating at 900 rpm. Now let us move to case number 2. This is after adding additional resistance. Remember where we are adding additional resistance, guys? Armature circuit, not field circuit. Okay, we are adding additional resistance in armature circuit. That means, can I say there is no change in field current? Flux is constant. Now, after adding external resistance, Vt is the same value, but speed was reduced to 600 rpm. The new armature current was 20 ampere. That was given in the problem. The new current was 20 ampere. What is the extra resistance added? Is the question. So see, you know the speed change. Earlier speed was 900, but now the speed was 600. So as you know the change in speed, can you find out the change in back EMF? Yes. What is the formula? Back EMF is equal to Ka phi into omega. In this method, flux is constant. Therefore, back EMF is only proportional to speed. So first case back EMF divided by second case back EMF is equal to first case speed divided by second case speed. What is the back EMF in the first case? 238 by second case back EMF I don't know, is equal to first case speed 900, second case speed 600. So can you find out what is the new back EMF now? Just use calculator, you will get the value of new back EMF. Right. EMF I don't know. Okay, let me open the calculator. So 238 into 600 by 900. Better. So 158.6. 158.6. This is the new back EMF of the motor. See, the moment you know the new back EMF, you write the KVL equation now. Already performance equation is used. So now use KVL equation. What is the KVL equation for the new back EMF? It is Vt minus Ia2. This is a second case. Remember, this is the equation after adding additional resistance, right? After adding additional resistance means Ra plus R external. Okay. So what is a new back EMF? 158.6 is equal to terminal voltage 250 minus new armature current 20, right? It was given 20 into armature resistance was 0.4. Extra resistance we have to calculate. So solve it, you will get the extra resistance required. That is the extra resistance we have to add to reduce the speed of the motor to 600 rpm. Okay, solve that, you will get the answer for the extra resistance value, right? So if I solve it, 250 minus 158.6 divided by 20 minus 0.4, so 4.17 ohm, correct? Am I correct? Just to solve it, you will get the answer. Yes. 250 minus 158.6 by 20 minus 0.4. 4.17. Yes. The extra resistance required is 4.17 ohm. Correct, Nagendra. That is the extra resistance value. Yes. Yes, Vinayak Chavan, your answer is also correct. Excellent. Right? Yes, Ranga, your answer is correct. Rohan Singh, very good. Answer is correct. 4.17 ohm. That is the additional resistance required to reduce the speed. Okay. Now, let us try to select one more problem. Okay. Let us add one more problem. Okay, let us select one question from series motor. Okay. Read this problem. A 500 volt DC series motor, driving a load whose torque is inversely proportional to speed. The condition is given, whose torque is inversely proportional to speed. At 1000 rpm by drawing 50 ampere. Total resistance of the motor is 1 ohm. Determine the new voltage required. See, new voltage required means voltage was changing, right? Determine the new voltage required to reduce the speed to 500 rpm. Neglect armature reaction and magnetic saturation. So see, in the first case, speed was 1000 rpm, guys. In the second case, speed has to be reduced to 500 rpm. So what is the new voltage required is the question. Definitely we need to reduce the voltage, then only speed of the motor can reduce. Okay, so there are two cases again. In the first case, voltage was 500, motor was rotating at 1000 rpm by drawing 50 ampere. Okay, take case number 1, calculate the back EMF of the motor. Okay, case number 1. Yes, this time variable voltage, guys, voltage is changing. So first case voltage VT1 500 volt, machine was rotating at 1000 rpm, and current drawn by the motor, it is a series motor, so all currents are equal. It was 50 ampere, right? Fine. Calculate the back EMF of the motor. What is the formula for back EMF? Vt minus Ia into Ra plus Rf. This is known as total resistance drop. So Vt was 500, current was 50. What is the total resistance given? 1 ohm. Total resistance is 1 ohm. Okay, therefore the back EMF was 450 volt. Clear? Now in the next case, what was happened? What is the new voltage required? That means voltage modified. In the next case, case 2. Okay, what is the new voltage required? The voltage modified. Okay, the voltage is modified to reduce the speed to 500 rpm. That means the new speed of the motor was 500 rpm. Calculate. Therefore, what is the new voltage required? They did not give you what is the new current. Did they mention what is the new current like previous problem? No. That means, are you going to take current constant? Never. I told you, never take current constant. You have to find out the new current. You have to find out this new current using the type of the load connected to motor. There will be definitely some information given. Yes, you see this first line. The series motor driving a load whose torque is inversely proportional to speed. Torque is inversely proportional to speed. That is given. It is given in the problem. Torque is inversely proportional to speed. As torque was inversely proportional to speed, T1 by T2 is equal to N2 by N1. Correct? What is N2 in the question? 500 rpm. N1 was 1000. Therefore, the ratio was 2, 1 by 2. Therefore, T1 by T2 is equal to 1 by 2. T1 by T2 is equal to 1 by 2. At the same time, what is the torque equation? We know torque is equal to Ka phi Ia. And which motor it is? It is a series motor. In a series motor, can I say flux is proportional to armature current only? Therefore, torque is proportional to Ia square. From this, T1 by T2 is equal to Ia1 by Ia2 whole square. What is T1 by T2? 1 by 2. What is armature current in the first case? 50 ampere by armature current in the second case whole square. So you will get the answer for new armature current. First get the value of new armature current. Once you know the new armature current, you can calculate what is the new back EMF. If you know new back EMF, you can find out what is the new terminal voltage required. So let us see. Is it not 50 into root 2? Yes. So the new current was 70.71 ampere. Okay, 70.71 ampere. Am I correct? N2 by N1. Okay, correct, right? Isn't it? Okay, 70.71 ampere. Now that I know what is the new armature current, I will find out what is the new back EMF of the motor. What is the new back EMF formula? I will use the performance equation Ka phi into omega. So EB is proportional to flux proportional to armature current since it is a series motor. Therefore, EB1 divided by EB2 is equal to Ia1 divided by Ia2 into N1 divided by N2. What is the back EMF in the first case? 450. 450. Back EMF in the second case, we don't know. Armature current in the first case, 50. Armature current in the second case, 70.7 into speed in the first case, 1000 rpm, speed in the second case, 500 rpm. Therefore, you will get the new back EMF. First calculate the new back EMF. Once you know new back EMF, you can find out what is the new terminal voltage. Let us see. If I cross multiply everything, 450 into 70.7 into 500 divided by 50 into 1000. I am getting the new back EMF 318.15. That is a new back EMF. But the requirement is to calculate new back EMF or new supply voltage. New supply voltage, that is where you need to write KVL equation. What is a KVL equation for new back EMF? Vt minus Ia into RT, total resistance. So supply voltage Vt2 is equal to Eb2 plus Ia2 into RT. What is the back EMF we got? 318.15. This is a 2 marks problem in previous GATE exam only. Okay, Ia2 was 70.7 and the total resistance was 1 ohm given, right? So you calculate, you'll get the answer for new supply voltage, right? So solve it, you'll get the new supply voltage. 318.15 plus 70.71. Yes, 388.86. Okay, 388.86. This is the new supply voltage required so that you can reduce the speed of the motor from 1000 RPM to 500 RPM. This is a variable voltage control method. Okay. Yes, correct. Correct. Rohan Singh, Nagendra, very good. So, important observation, make a note point. If you are having a notebook with you, please make a note point. In speed control problems, never assume the new armature current same as the old armature current. Never assume it unless it is given in the problem. The new armature current you have to find out using the condition given in the problem. Some kind of condition will be always given. Some kind of condition. It may be torque constant, it may be power constant, torque variable, power variable. Some kind of condition will always be given. Based on the condition, you need to answer the problem. Okay. Okay. Yes. Right. We will take up one more problem. Then we will stop DC machines and we will move to induction machine. Okay. We don't have time left. This is the last important. Starters are not much important. Of course, you need to study for the examination point of view. But here we can't discuss because of the time constraint. Anyway. So let us add one more problem. This is, I hope all of you got the answer, 388.86. Right. 1 second, guys. Okay. Right. Two problems I will solve, then we will end it. Okay. This is another GATE question only, previous GATE question. Okay, important question. This is also based on series motor. Please read the problem. Yes, read the problem. A 500 volt DC series motor having an armature and field resistances of 0.1 ohm and 0.2 ohm respectively. It is drawing a rated armature current of 100 ampere and driving a constant torque load at 1200 RPM. Now, a diverter resistance of 0.4 ohm. I told you field diverter control method. A diverter resistance of 0.4 ohm is connected in parallel with series field winding. Okay. What is the new speed of the motor? So read the problem again. It was a 500 volt DC series motor having an armature and field resistances of 0.1 ohm and 0.2 ohm respectively. Okay, field resistance, armature resistance separately given. Machine was initially drawing 100 ampere and driving a constant torque load. Please, the condition if you read it carefully, constant torque load, that is the condition given at 1200 RPM. Now the diverter resistance is added. So again, there are two cases. First one is before adding diverter resistance, second one is after adding diverter resistance. So let us take before adding diverter resistance, case number 1. Before adding the diverter resistance, okay, that means circuit will be like this. This is armature, this is field, this is the supply voltage. This is the first case, guys. Therefore field current value and armature current value both are equal. So let us write down the details. What is the terminal voltage? 500 volt. 500 volt. What is the current drawn by the motor? Armature current and field current both are equal, right? How much is that? 100 ampere. So calculate back EMF of the motor. Back EMF is equal to Vt minus Ia into Ra plus Rf. What is the terminal voltage? 500 minus armature current 100 into what is armature resistance? 0.1, field resistance 0.2. 0.1 plus 0.2, 0.3 into 100, 30, 470. So back EMF was 470 volt. This is the initial data. And what is the speed at which the machine was rotating in this case? 1200 RPM. In the first case, the speed is 1200 RPM. This is the data. Now coming to the next case, diverter resistance is added. Second case, after adding diverter resistance or external resistance, it is very clearly given the diverter resistance of 0.4 ohm is connected in parallel with series field winding. It is in parallel with series field winding. That means if you draw the rough diagram, this is the armature circuit, this is the field circuit. Now diverter resistance was added in parallel with this series field winding. Okay, yes, here the diverter resistance is added. This is the new field current and this is the new armature current. Got it? Okay, so let us see. Supply voltage is the same. How much is the supply voltage? 500 volt, no change in supply voltage. I don't know what is the new armature current because I told you current you cannot assume same. And how much diverter resistance is added? 0.4 ohm. So what is the new speed is the question. To find out this new speed, you have to find out new back EMF. To find out new back EMF, I need to calculate the new current first. How do I find current? That is where you need to use the condition given in the problem. What is the condition given? Yes, the machine was driving a constant torque load. That was the condition given. What is the formula for torque? Torque is equal to Ka phi into Ia. They said torque is constant. We know Ka is a constant value. Therefore, what is the relation between flux and armature current? Therefore, armature current is inversely proportional to flux. And you always remember, flux is dependent on which current? Field current. Therefore, armature current is inversely proportional to field current. As it is inverse proportionality, what is the equation I can write? Ia1 by Ia2 is equal to 2 marks problem. If2 divided by If1. What is Ia1? First case, armature current, field current both are same only, 100 ampere. Therefore, here armature current in the first case 100 ampere. I don't know what is armature current and field current in the second case, but field current in the first case also 100 ampere. If I cross multiply, 100 square is equal to Ia2 into If2. That means I need a relation between Ia2 and If2. Why I am not assuming second case armature current and second case field current same value? Yes. Why? Because diverter resistance is added. Because the diverter resistance is added, armature current and field current both are not same. I have to use current division principle here. This is the field winding resistance. This is the X, just a minute. Okay. So this is the new armature current IA2 and this is the new field current IF2. So you can relate both of them using a current division principle, right? So what is the new field current? New field current is equal to total armature current into opposite resistance R external by RF plus R external. This is a difficult problem, 2 marks problem. You should have some patience. Okay. So what is the diverter resistance added? 4 ohm, 0.4 ohm. And what is the field resistance? 0.2 plus 0.4. So is it not 4 by 6, 2 by 3? So therefore, the new field current is equal to 2 by 3 times of new armature current. This is the relation I got. Substitute this relation here. Therefore, 100 square is equal to IA2 plus what is IF2? 2 by 3 times of IA2. Now you will get IA2 answer. Correct? So let me use calculator. So IA2 square root 3 by 2. Sorry, 1 second. So I'm getting 122.4 ampere. This is the new armature current, right? Once I know new armature current, I think I can find out new field current also if I use this equation. So what is the new field current? 2 by 3 times into 2 by 3, 81.64. Once I know what is the new armature current and new field current, I think now I can find out the new back EMF, right? Yes. How to find out the new back EMF? KVL equation. The new back EMF is equal to Vt minus Ia2 into, remember KVL equation, armature will have armature resistance, but these two are in parallel, right? Parallel. So it is armature resistance plus RF and R external both are in parallel. So the terminal voltage was 500. What is the new armature current we got? 122.4 plus armature resistance 0.2. Correct? How much is armature resistance? 0.1, right? Armature resistance was 0.1. Now, what is a parallel combination of field resistance 0.2 ohm and the external resistance 0.4 ohm? Is it not 2 by 3 times of 0.2? 0.4 by 3, 0.1 something. Okay, I'll directly write the, yes, 0.12. That is a parallel combination, 0.12. Okay, now you will get the new back EMF. Uh, if I make any calculation mistakes, please let me know. Minus 500. 1 second. 122.4 plus 0.22. Okay, 377.88. This is the new back EMF. The moment I know new back EMF, you can find out what is the new speed of the motor. What is the formula for back EMF? Back EMF is equal to Ka phi into omega. It is a series motor. Back EMF is proportional to flux. Flux depends upon field current. Don't write flux depends upon armature current here. If you write flux depends upon armature current, that's a mistake. Why? Because armature current and field current are not equal. Armature current, what happened? Screen. Okay. 1 second, guys. Is it visible now? Okay. Right. Okay. Anyway, back EMF is proportional to field current into speed. I think you might have not watched the solution that I have written here due to the screen problem. But anyway, as the audio was available, I request you to try. Okay. I can't solve again because time is not there. Okay. You try to solve it based on the audio that I gave you. Anyway, I can continue here. So I will tell you summary once again. Once I finish it, I will tell you once again what is the procedure. You try. So from this I can write EB1 divided by EB2 is equal to IF1 divided by IF2 into N1 divided by N2. Got it? So what is the back EMF in the first case? If you go back and substitute, back EMF in the first case was 470. 470. Back EMF in the second case was 377.88. Field current in the first case 100. What is the field current in the second case? 81.64. 81.64. Speed in the first case. What is the speed in the first case? 1200 RPM, right? 1200 RPM divided by speed in the second case, you find out the answer. That is the new speed of the motor. That is the new speed of the motor. Okay. First case speed was 1200 RPM. Second case speed you have to find out. I'll show you the question. Don't worry. I'll tell you the summary again because you did not watch the screen. Let me finish it up. Into 100 into 1200 divided by 470 into 81.64. So I'm getting 1181 RPM. 1181.7 RPM. 1181.7 RPM. So that is the new speed of the motor. That is the new speed of the motor. Okay. Right. Now let's go back once again. You see, it was a 500 volt DC series motor. You can take a screenshot of this problem and solve it once the session is over. Okay. It was a 500 volt DC series motor having an armature and field resistances. It is drawing a rated current of 100 ampere and driving a constant torque load at 1200 rpm. Diverter resistance is added. Okay, diverter resistance means we discussed, right? Field diverter control method. So see that this is the first case, guys. Before adding the resistance, just like other problems, I calculated back EMF of the motor. Clear? I calculated back EMF of the motor. Just a moment. Okay, I calculated the back EMF of the motor. Right. Now look at this. Now this is after adding additional resistance. You see that additional resistance was added in parallel to field winding. Additional resistance was added in parallel to field winding. So I found a relation between armature current and field current because the given question has torque is a constant value. That was clearly mentioned in the problem. Okay. So now armature current and field flux has the relation. Now I found what is the new field current in terms of new armature current, and then I found a new back EMF and then the new speed. Okay. So using these slides, you try to figure out this problem. Okay. Those who have not watched completely. Please try to figure out this. Okay. Right. Fine. Okay, so now let us try to answer one more question. That is the last question for DC machines, speed control. Okay, look at this. This is another important model. That's why I wanted to solve it. Right. So please go through this question. I request you to try for 1 minute and then I will solve it. First, understand the problem. Understand the problem. Try for 1 minute, then I will solve it. Come on, guys. Try for 1 minute and then I will solve it. Okay, so see the problem. A DC shunt motor is connected to a constant voltage source and driving a constant torque load. Now the first question is, increasing the resultant flux reduces the speed if which of the following conditions satisfied? Second question, increasing the resultant flux increases the speed if which of the following conditions satisfied? Okay, two questions indirectly. One important data in the problem is machine was driving a constant torque load. Okay, hello. All right, now let's see. A DC shunt motor is connected to a constant voltage source driving a constant torque load. This is the important data given in the problem. Now the first question is, increasing the resultant flux reduces the speed. First of all, what is the speed equation? You remember? Speed equation of a shunt motor, Vt minus Ia Ra by Ka into phi. Now the point is, increasing the flux reduces the speed. Any quantity, if it is increasing, can I say the change in the quantity is a positive value? Phi means flux, d phi means the change in flux. What is the change in flux? Increasing the flux. Increasing the flux means the d phi is a positive value. Okay. Reduces the speed. Reduces the speed. Any quantity, if it is reducing, what is the change in that quantity? Negative. Therefore, indirectly, increasing the flux means d phi is a positive value. Decreasing the speed means d omega is a negative value. That means, what is the ratio d omega by d phi? Is it not a negative value by positive value? That means a negative value only. Therefore, d omega by d phi is less than 0 indirectly. That means it is indirectly looking like change in speed with respect to change in flux is less than 0. Got it? That means it is a derivative of speed equation with respect to flux equation or flux value. But I need to develop the equation in terms of torque first, because it is given machine was driving a constant torque load. Okay, let us see everything now. What is the torque equation? Ka phi into Ia. From this, what is Ia is equal to? Ia is equal to torque divided by Ka phi. Consider this is equation number 1. What is the speed equation? Speed is equal to Vt minus Ia Ra by Ka into phi. Okay. Now what you do is that in place of Ia, you just replace this equation. Okay. So therefore, omega is equal to Vt by Ka into phi minus Ra by Ka into phi into Ia. What is Ia? Torque by Ka into phi. Okay, so therefore Vt by Ka into phi minus Ra by Ka into phi whole square into torque. So I wrote this torque equation, sorry, speed equation in terms of torque. You may have a question, sir, why you are writing in terms of torque only? Because that is a condition given, right? It is the condition given. Machine was driving a constant torque load. Okay, that's why you try to get the speed equation in terms of torque. Now for the first problem, what is d omega by d phi less than 0? Because flux is increasing, speed is decreasing. Okay, now indirectly differentiate this omega equation with respect to phi. If you differentiate with respect to phi, you will get the answer. Okay, so in the first problem, d omega by d phi is less than 0. What is the differentiation of omega with respect to phi? Is it looking like 1 by phi? What is the differentiation? Minus Vt by Ka into phi square minus Ra torque, both are constants, Ra into torque divided by, this is Ka square. Then tell me, what is the differentiation of 1 by phi square with respect to phi? Is it not minus 2 by phi cube? 2 by phi cube. Am I correct? This is less than 0. So minus minus will become plus, right? Already minus is there, and the differentiation 1 minus of 2 by phi cube. So minus into minus plus. You take this minus quantity to the left side. 2 Ra torque divided by Ka square into phi cube is equal to, this minus will become not is equal to, less than, right? Less than, simple. Less than Vt by Ka into phi square. So remember here, this phi square will cancel phi times, Ka will cancel Ka times. Okay. So if I continue next, what is the next step? Numerator 2 Ra torque divided by Ka phi is less than Vt. Let me continue next page. 2 Ra torque divided by Ka phi is less than Vt, correct? And now let us replace torque equation. What is the torque equation? Torque is nothing but Ka phi into Ia divided by Ka phi is less than Vt. Ka phi will cancel. 2 Ra into Ia, that is indirectly 2 Ia Ra is less than Vt. Okay. Now, what is the equation in terms of Ia Ra? Can I use a back EMF equation? What is the KVL equation for back EMF? Vt minus Ia Ra. From this, Ia Ra is equal to Vt minus Eb. Substitute this Ia Ra here, but don't forget 2 multiplication is there. 2 into, what is Ia Ra? Vt minus Eb less than Vt. So tell me which option is satisfying this. Simplify this and tell me which option is satisfying. So if you further multiply 2 Vt minus 2 Eb less than Vt, 1 Vt you can take outside. So tell me which option is satisfied. Come on. You further simplify and look at which option was said. Okay, I will show you the question again. Look at this question, guys. Eb greater than 1 by 2 Vt, Eb less than 1 by 2 Vt, Eb equal to Vt, Eb equal to, that means Eb Vt relation I need. Okay, come on. So you can solve it further, right? So if you further multiply 2 Vt minus 2 Eb, okay, if I continue here, so 2 Vt minus 2 Eb is less than Vt. So 2 Eb is greater than Vt, Eb is greater than Vt by 2. I think this is the truth. Eb is greater than Vt by 2. Correct? Eb is greater than Vt by 2. Eb is greater than Vt by 2. Now look at the second problem, guys. In the second problem, what was given? In the second problem, you see this time. In the second problem, they said increasing the resultant flux. Once again, increasing the flux means d phi positive. D phi positive increases the speed. Increases the speed means d omega is also positive. Increasing the resultant flux increases the speed. That means d phi positive, d omega positive. That means what is d omega by d phi? Positive by positive, positive. That is greater than 0. Okay, d omega by d phi greater than 0. Same procedure. But only change is this time greater than 0, greater than. I think the final answer will be EB less than VT by 2. Okay, EB less than VT by 2. Correct? Right. Okay. Oh. So I think due to these long hours, the screen is getting struck. Okay, because the system was running from past 6 hours. Okay. Now look at the second question, guys. The second question is increasing the resultant flux increases the speed. Increasing the resultant flux means d phi is positive, increases the speed. That means d omega is also positive. Okay. Therefore, what is d omega by d phi? Is it not greater than 0 this time? If it is greater than 0, I think everything will be same derivation, but only thing is that the symbol will change. It will become EB less than VT by 2 in the next problem. EB less than VT by 2. Okay. All right. Clear? Fine. So take this screenshot and please solve the second problem also. You try to solve it. It will be easy. Change, increase in field flux increases the speed. So d phi positive, d omega also positive. Therefore, d omega by d phi is a positive value which is greater than 0. Clear? Okay. Fine. So with this, we will stop DC machines here. There are some more topics like starters, losses and efficiency calculations, but I would like to cover only important topics. Okay, we don't have that much time. Okay, right. All right, guys. So let's take a break for 5 minutes. I will also go through that problem why the screen is trucking. Okay, so take a break for 5 minutes, then we will start induction machines. Okay, induction machines. Okay. Okay guys, welcome back. So let us start our next discussion, that is induction machines. Okay, fine. So coming to induction machines course, I will try to list out the topics first of all. In those topics, some important topics we will try to cover. All right, all right. So let me list out the important topics. Right. So first we need to understand the basics of induction machines, which I will cover a little quickly. Okay. You all know that induction motor will not run at a synchronous speed. It will always rotate at a speed less than synchronous value. And then we will go through slip calculations. What is the importance of a slip and what are the calculations associated with slip? Then once you learn about slip calculations, then we need to understand equivalent circuit of induction motor. Equivalent circuit of induction motor. Okay. And then power flow diagram. This is the most important part of induction machines subject. More questions are there even in the previous GATE exam also. Power flow diagram. And then electromagnetic torque equations. Torque equations like starting torque, maximum torque, relation between starting and maximum torque, condition for maximum torque, etc. And then characteristics of induction motor, that is torque speed characteristics of induction motor. Okay. Once we are done with characteristics, then we need to learn about testing, no load test and blocked rotor test. In next, starters. Okay, another important topic. Okay, very important topic. DC motor starters are not so important, but induction motor starters are very important. And then speed control of induction motor. Speed control. Next, induction generator. Okay, induction braking. And finally, single phase induction motors. Single phase motors. We may not be able to cover each and every topic because of the time constraint that we have. I will try to cover up the major topics which are very, very important from the examination point of view. Okay. So without wasting our time, let us go to the first topic, which is the basics of electromagnetic or basics of induction motor. See, we will try to understand how an induction motor will rotate quickly. Okay. Generally 2 to 2.5 hours time we need to understand every detail about induction motor basic, but I will try to cover up very quickly. See, induction motor will operate based on mutual induction along with Lorentz force equation. I can say it will operate based on mutual induction plus Lorentz force equation. Lorentz force equation. So you must have a bit of idea about transformers to understand induction motors course, because induction motor is considered as a rotational transformer. Okay, a transformer which is rotating, that is also called as an induction motor. So transformer will operate based on mutual induction principle, and induction motor will also operate on the same principle. We call it as mutual induction. Okay. And then Lorentz force equation. Lorentz force equation we studied in DC motor as well. Okay. See the idea, what is going to happen. Consider we have an induction motor having a stator part. This is the stator part of the machine. And the stator is having a balanced three-phase distributed winding. And this is the rotor part. Rotor will also have balanced three-phase distributed winding. Okay. Right. Now the point is the stator part, whichever is available, that will be excited from balanced three-phase source. Okay. So here the source will be connected. The source will be connected. From this source, the machine will draw balanced three-phase current. Okay. So whenever AC current is passing through any distributed winding, especially distributed winding, rotating magnetic field will be created. And that rotating magnetic field created by the stator will cross the air gap and link the rotor winding. What is the medium between stator and rotor? Air gap only. So that magnetic field will cross. This is a stator field, guys. The stator field will cross air gap and link the rotor winding so that a mutual EMF is induced in rotor winding. A mutual EMF is induced. Okay. This is like in a transformer also, which winding is connected to source? Primary winding will be connected to source, but EMF will induce in secondary winding also. Correct? In a similar manner, stator winding is excited, that will induce EMF in rotor winding, that is known as mutual EMF. And once EMF is induced, now what I will do here is that very simple thing. I will close all these rotor terminals directly like this. I will short circuit the terminals. The moment when the rotor terminals are short circuited, as there exists some voltage in the rotor, immediately current will pass through rotor. Because rotor is a closed circuit. Suppose if you keep it open, current does not circulate. As we are closing the rotor, current started to circulate in rotor. Okay. Therefore, rotor conductors are normal conductors or current carrying conductors. Current carrying conductors. The moment you understand rotor conductors are carrying current, now apply Lorentz force equation. What is Lorentz force equation? States that any current carrying conductor placed inside a magnetic field will experience a force. And because of that force, the rotor started to rotate. The rotor started to rotate. So, you see, initially mutual induction process is there. You are exciting stator winding, but that will induce EMF in rotor. Most important thing is rotor must be a closed circuit. If rotor is a closed circuit, then only current will flow, and that current carrying rotor conductors will experience a force, and because of the force, the rotor started to rotate. This is simply, you can explain the principle of induction motor, but there are so many questions. What is rotating magnetic field? Why rotating field is required? Okay, and why induction motor cannot rotate at synchronous speed? Why it will rotate at a speed less than synchronous value? There were so many questions. So first we will start with simple basics, that is electromagnetic torque. Basic electromagnetic torque. Right. See, if you wanted to produce electromagnetic torque in any rotating electrical machines, there are three conditions to be satisfied. First condition is stator and rotor must have, there will be proof, guys, okay, behind all these conditions there will be proof, okay, but I am not going to discuss those proofs based on the time constraint that we have, okay. We will directly write down the conditions, okay. So there are three conditions to be satisfied to create electromagnetic torque. Let me check the screen. Is it everything fine now? I just reset my system. I hope it is fine. Yeah. Yes. So the first condition is stator and rotor must have same number of poles. Stator and rotor must have same number of poles. Same number of poles. Suppose if a stator has 4 poles, rotor has 6 poles, then machine cannot rotate. Both stator and rotor must have same number of poles. Second rule is the relative speed between stator field and rotor field. The relative speed between stator field and rotor field must be equal to 0. Must be equal to 0. I said the relative speed. It is not the speed, it's the relative speed. The relative speed between not stator and rotor, it is a stator field and rotor field must be equal to 0. And the third rule is the phase angle difference. The phase angle difference between stator field, okay, between stator field and rotor field, between stator field and rotor field must be finite. The phase angle difference must be finite. So there will be proof to satisfy all these three conditions, but we can't discuss that proof right now. But you try to understand these conditions must be satisfied to create electromagnetic torque. If any condition failed, the torque cannot be created. Okay. Now let me write down the basic electromagnetic torque equation, guys. The simplified electromagnetic torque equation. Electromagnetic torque is directly proportional to minus F1 F2 sine lambda. Okay. Don't worry about the equation, it is easy. Here F1 is nothing but stator MMF or stator field, anything is same. F2 is nothing but rotor MMF or rotor field, and lambda is the angle between these two. Suppose, imagine this is stator MMF and this is rotor MMF. The angle between these two is nothing but lambda. Okay. Suppose what happens if stator MMF and rotor MMF both are in phase with each other? If both fields are in phase with each other, can I say lambda becomes 0? The moment when lambda becomes 0, what is sine 0 degrees? 0. Then a torque cannot be created. That's why the phase angle difference between stator field and rotor field must be finite. If lambda is finite, then only torque can be created. Okay, that is very, very important. Next thing, always remember these fields are rotating in nature. See, rotor field and stator field both are rotating in nature. It is very easy to understand. Rotor means it's a rotating body. That's why rotor field is rotating with a synchronous speed. But why stator field is rotating? That's always a question. Stator means it's a stationary body, right? If stator is stationary, how stator field is rotating? That's a miracle, right? So that is what we need to prove. Stator may be stationary, but stator field is always rotating, guys. And it will rotate at a synchronous speed. If both fields are rotating at a synchronous speed, what is the relative speed between these two fields? 0. That is the second condition. You see this. Please read the second condition. The relative speed between stator field and rotor field must be equal to 0. That means both fields must travel with the same speed. Then only the relative speed will be 0. Okay. Now we will try to answer the question how stator field is rotating even though stator is stationary. Even though stator is stationary, how stator field is rotating. Okay, that is what we call it as rotating magnetic field theory concept. Rotating magnetic field, we simply call it as RMF. Okay, so very simple, guys. To create rotating magnetic field, two conditions must be satisfied. First condition, a polyphase distributed winding is required. A polyphase distributed winding is required. See, lot of proofs will be there in induction motor subject because we are running marathon session, which is a short period of time, right? So all the proofs I may not be able to do, but you try to believe, you try to understand every formula I'm writing is valid. Okay, right? So a polyphase distributed winding is required. Next, this winding must carry a polyphase AC current. This winding must carry a polyphase AC current. What is mean by polyphase? Very simple. Polyphase means any number of phases except single phase. Except single phase, you take any number of phases. It may be 2 phase, it may be 3 phase, it may be 6 phase, it may be 12 phase. Any number of phases except single phase is known as polyphase. Okay, and that polyphase winding must carry AC current. If it carries AC current, automatically rotating magnetic field will be created. All right. So I will show you one graphical, representation how rotating magnetic field will be created. You will try to understand. Okay. Just a moment. Guys, give me 1 minute. I'll just drink a glass of water and we'll come back. Okay, so let's start. So let's understand how this rotating magnetic field is possible in three-phase system. I told you polyphase system is any number of phases except single phase, right? Okay. Let us consider a simple system. I have a three-phase distributed winding. Just take this. Imagine this is the stator part. Three-phase winding I wanted to place. Let us say this is phase A, this is A, this is A dash. So A and A dash will form phase A. Next, after 120 degrees, we will have B and opposite side we have a B dash. After one more 120 degrees, this is C and this is going to be C dash. Okay. See, I wanted to copy this diagram. Okay. So, okay, right. Now, this is the stator I am selecting. It is a three-phase balanced distributed winding. Now, how rotating magnetic field will be created? Now, to create rotating magnetic field, what is the second rule to be satisfied? I have to excite this winding with AC current, polyphase AC current. Therefore, if it is a three-phase winding, excite this winding with three-phase current. So, automatically, that three-phase current will create rotating magnetic field. Okay, so let's see. So, when it is a three-phase current, I would like to select, let us consider the three-phase current as follows. See this? Okay, so I am taking the time on x-axis and the current on y-axis. A three-phase current waveform I would like to draw. Simple. Let us say this is a phase A current. So phase B current will start after 120 degrees. This is phase B current. Okay, next after one more 120 degrees, phase C current will start, right? Okay, this is a three-phase current waveform I selected, and I assume the sequence was ABC sequence. You can also understand what happens if it is ACB sequence, right? Okay, this is a phase A current, phase B and phase C. Is it visible to everybody? Yes, it's covering, right? The screen is covering. Okay. Now, let us take a time instant t1. Let us select first time instant t1. At this time instant t1, which current was positive and which currents are negative? According to the waveform, you can clearly understand phase A current is positive. Assume positive current means cross polarity. Phase B current is negative and phase C current is also negative. So A is a positive current, B and C are negative currents right now. And you know, if A is cross, automatically A dash is dot. If B is dot, B dash is cross, C is dot, C dash is cross. Now use right hand thumb rule to identify the direction of magnetic field. These three conductors are carrying the current into the plane. Bottom side three conductors are carrying the current out of the plane. So my thumb will represent the direction of magnetic field. So this is the direction of magnetic field at a time instant t1. Got it? Now let us select time instant t2. After some time, let us say time instant t2. This time you tell me which current is positive and which currents are negative. This time phase B current is positive, phase A and C currents are negative. Positive means cross polarity. A and C are negatives right now, therefore they are dot polarities. Yes, we know if A is dot, A dash is cross, B is cross, B dash is dot, C is dot, C dash is cross. Use right hand thumb rule, identify the direction of flux direction. These three conductors are carrying the current into the plane, these three out of the plane, so the magnetic field is in this direction. This is at a time instant t2. You take one more time instant, let us say a time instant t3. At a time instant t3, which current is positive and which currents are negative? Phase C current is positive, cross polarity. A and B currents are negative, dot polarity. So C positive, so C is a cross polarity. A and B are dot polarities. Got it? And if A is a dot polarity, what about A dash cross? B is a dot polarity, B dash cross. C is a cross polarity, C dash dot. Now you use right hand thumb rule. This is the direction of magnetic field. Therefore, what is your observation? From time instant t1 to t3, the magnetic field is at the same location or changing its position. Definitely the magnetic field was changing its position. And if I ask you the question, the magnetic field was rotating in which direction? Definitely you can understand the magnetic field was rotating in clockwise direction. That is what we call it as forward rotation magnetic field. Okay. Okay, forward rotating magnetic field. Adarsh, you're asking about ECE marathons. I don't have a complete idea about ECE marathons. Okay, you can ask Rakesh sir directly, right? All right. Which part most of the questions will come? See, electrical machines, every part will carry equal number of marks. You can check the past 10 years papers, you can understand that. Every part will carry 3 to 4 marks. Maximum 3, sorry, minimum 3, maximum 4. Sometimes 2, sometimes 4, sometimes 3, like that. Okay. So anyway, the magnetic field was rotating in which direction here? In this particular diagram, it was rotating in clockwise direction. This is known as forward rotating magnetic field. Forward rotating magnetic field. All right. Forward rotating magnetic field. So suppose if I change the sequence from ABC to ACB, let us say, that is negative sequence. If I apply negative sequence, the same magnetic field will rotate in backward direction. Okay. So for positive sequence, forward rotating magnetic field will be created, and for negative sequence, backward rotating magnetic field will be created. Okay. So positive sequence, forward RMF is created. Forward RMF. Negative sequence. Suppose if the supply is a negative sequence type, then the same magnetic field will rotate in backward direction. Backward direction. So the points you need to understand is the winding is stationary. The core is stationary. Core is not moving. Winding was not moving, but the magnetic field is moving. In forward direction, if it is ABC sequence, in backward direction, if it is ACB sequence. What if it is a zero sequence? Neither forward nor backward, RMF does not produce. RMF does not produce. If RMF does not produce, torque cannot be created. In order to create torque, rotating magnetic field is compulsory. If rotating magnetic field is not created, torque cannot be created. That's why zero sequence components are ineffective in induction motor. Okay, ineffective. Zero sequence components are ineffective in induction motor. Only positive sequence components and negative sequence components are effective. If you give positive sequence supply, forward RMF will be created. I am writing the magnitude of that forward RMF also. Yes, the resultant MMF will be equal to 3 by 2 F max cos omega t minus theta. Of course, this equation is not important for you. Ampere turns per phase. That is a forward RMF equation. If it is backward RMF equation, the resultant MMF, F indicates MMF guys, magneto-motive force, MMF. It will be 3 by 2 F max cos omega t plus theta. Okay, MMF unit is ampere turns per, sorry, not per phase, per pole. Okay, ampere turns per pole. And if it is zero sequence, RMF cannot be created, therefore machine cannot be rotated. So very simple points. You excite induction motor with ABC sequence, machine will rotate in forward direction. You excite induction motor with ACB sequence, machine will rotate in backward direction. Okay, right. Now, next important observation is rotational induced EMF concept. Rotational induced EMF. Let's take a simple example question. Okay, very simple. This is going to be helpful in induction machines course. You take a small magnetic field, guys. Let me consider a magnetic field. I have a north pole here, and assume we have a south pole here. Flux will always go from north pole to south pole. Okay, so let us draw some finite number of lines. I am drawing 5 flux lines, for example, phi 1, phi 2, phi 3, phi 4, and phi 5. Now, whenever conductor is on, let us say, third flux line, for example, and this conductor was moving in upward direction at a speed of 10 meter per second, for example. So, whenever conductor was moving in upward direction, right now the conductor was linking which line? Phi 3. After some time, it will link phi 4. After some time, it will link phi 5. So, are you finding there is a change in flux? Definitely, yes. Whenever change in flux is observed, EMF will be definitely induced. Because what is the EMF formula? You can use BLV sine theta. According to this formula, induced EMF is directly proportional to velocity. And what is the velocity of the conductor right now here? 10 meter per second. Therefore, induced EMF is directly proportional to 10. Very clear. Remember, for the production of EMF, flux is important or change in flux is important? Change in flux is highly important. Okay. Now, in the next case, let us assume that when conductor was moving in upward direction at 10 meter per second velocity, what happens if the poles are also moving in upward direction with the same velocity 10 meter per second? If poles are also moving in the same direction with the same speed, what will happen, guys? Let me know in the chat box. If poles are also moving in the same direction, right now the conductor was linking flux line phi 3. After some time, what will happen? After some time, conductor will link phi 4 or it will link again phi 3. It will again link phi 3 only. Why? Because conductor and flux lines both are traveling in the same direction with the same speed. If a conductor was linking the same flux line once again, automatically can I say EMF does not induce. There is no change in flux now. There is no change in flux. If there is no change in flux, the induced EMF will be equal to 0. The induced EMF will be equal to 0. So why the induced EMF is equal to 0? Because the conductor and field both are traveling with the same speed. Indirectly, this 0 is nothing but 10 minus 10. That is what? The relative speed is 0. See here, field, conductor both are traveling in the same direction with the same speed. Therefore, the relative speed between the two is 0. That's why the EMF is 0. You take one more case. Let us say conductor was moving in upward direction at 10 meter per second. Let us say the field is moving with 13 meter per second. Let us say if the field was moving at 13 meter per second. Therefore, what is the meaning of it, guys? Now conductor is crossing the field or field is crossing the conductor? The field is crossing the conductor with how much speed? 3 meter per second. Therefore the induced EMF is 3. It is indirectly 13 minus 10. Therefore what is your observation here? When conductor and field both are traveling, induced EMF is proportional to velocity of the conductor or velocity of the field, or it is proportional to relative velocity between the two. Yes, it is proportional to relative velocity between the two. The relative velocity between the two or relative speed between the two. Okay. When conductor and field both are moving, the induced EMF is directly proportional to relative speed between velocity of the magnetic field and velocity of the conductor. If both are traveling with the same speed in the same direction, the relative speed will be 0, then EMF does not induce. It is the same concept on which induction motor is working. Okay, let us see now. Suppose you see the working of induction motor. Working of induction motor. Okay, so let us see. First, we will be taking there are two types of induction motors. I am not going through construction part of induction motor to save the time. There are two types of induction motors, guys. Squirrel cage induction motor, slip ring induction motor, based on the design of rotor circuit. And the only difference between both machines is, in case of squirrel cage induction motor, external resistance cannot be added into rotor. But in slip ring induction motor, external resistance can be added into rotor. Okay, that is the only difference. Everything will be same. Okay, I don't want to go to construction part of the machine, which will waste the time. Okay, I will directly go to the subject. Now, working of induction motor. I already told you induction motor will work based on mutual induction and Lorentz force equation combination. Okay, see what will happen. You take the stator part of the machine. Okay, this is the stator part of the machine. Okay, and whenever stator winding is excited from balanced three-phase supply source, I just told you, distributed winding carrying AC current, immediately rotating magnetic field will be created at synchronous speed. Now that stator field will cross air gap and link which winding? Rotor winding. This is the rotor. And remember, rotor is a closed circuit. So the magnetic field created by stator will link rotor winding. Therefore, a mutual EMF is induced in rotor. And as rotor is a closed circuit, this EMF will generate current through rotor. Those current carrying rotor conductors will experience a force and rotor started to rotate. Now, point is, I wanted to study this operation based on Lenz's law. Okay, let's see how. Interesting, very important. Listen. To understand the working of induction motor with the help of Lenz's law, first let me consider a stationary line. So imagine this is a stator, okay, a stationary line. Stator will always have a three-phase balanced distributed winding. Okay, stator will have three-phase balanced distributed winding. And we will excite this. See, these three circles represent three-phase distributed winding. Okay, and it is a stationary line, indirectly stator. We are exciting this three-phase winding with ABC sequence supply. Okay, so assume the supply frequency is equal to F. Also assume stator has P number of poles. Okay, whenever three-phase balanced distributed winding is excited with AC supply, it will create stationary magnetic field or rotating magnetic field. Yes, it will create a rotating magnetic field. Okay, that is what we studied, right? Whenever distributed winding is carrying AC current, it will create a rotating magnetic field. At how much speed? Synchronous speed. See? So this is a synchronous speed. Imagine this length is equal to ns RPM. Ns is equal to 120 F by P. Okay, right. That means you tell me stator is stationary. stator conductors are stationary, but stator field is rotating. Therefore, this dotted line is representing the position of stator or position of stator field. Yes, this is the position of stator field. If I ask you the question now, what is the speed of stator field with respect to stator? The answer will be ns rpm. Okay, the speed of stator field with respect to stator is ns rpm. Now what will happen? This stator field will cross the air gap and link the rotor winding. You tell me, at the time of starting, rotor is stationary or rotor is rotating? I am talking about starting. Starting means, can I say rotor is also stationary? These are the rotor conductors. And rotor is a closed path or open path? Closed path. Rotor is having a closed circuit, right? And now tell me, what is the speed of stator field? ns. But what is the speed of rotor right now? 0. Can I say there exists a relative speed between what and what? Stator field and rotor conductors. How much is the relative speed? You tell me. ns minus 0. Therefore, there exists a relative speed ns minus 0. Between what and what? Between stator field and rotor conductors. Because of this relative speed, an EMF induces in rotor. This is what we call it as rotational induced EMF. That is what I explained right now. The induced EMF is directly proportional to relative speed between magnetic field and conductors. Right now, the magnetic field is traveling with ns speed, conductors are traveling with 0 speed. Therefore, there exists a relative speed. Because of this relative speed only, an EMF is induced in rotor. And rotor is a closed circuit, right? In any closed circuit, when voltage induces, immediately what will happen? Current will flow in rotor. Therefore, rotor conductors are normal conductors or current carrying conductors? Current carrying conductors. These current carrying rotor conductors will experience torque according to Lorentz force equation. Current carrying conductors will experience force or torque. Therefore, can I say this torque is the effect here? What is the reason for this torque? Current in rotor. What is the reason for current? EMF. What is the reason for EMF? Relative speed. This is the cause. Remember guys, this is the relative speed between what and what? Stator field and rotor conductors. Now what Lenz's law states that effect will always oppose the cause of the production. Opposing means effect will try to reduce the cause or will try to increase the cause. Effect will try to reduce the cause. Opposing means effect will try to reduce the cause. That means whatever electromagnetic torque is created, that will try to reduce what? Speed or relative speed? Relative speed between what and what? Relative speed between stator field and rotor conductors. Am I correct? So how to reduce the relative speed between stator field and rotor conductors? See, stator field was here, rotor conductors are here. How to reduce this gap? Can I say this gap can be reduced by pushing these rotor conductors in the direction of stator field? Yes. You push the rotor conductors in the direction of stator field, automatically the relative speed can be reduced. Okay. Who will push the rotor? Yes, the electromagnetic torque. Whatever electromagnetic torque is created, that will push the rotor in the direction of stator. So therefore, now rotor conductors are not stationary, guys. The rotor conductors started to rotate. The rotor conductors started to rotate. All right or not? So now the rotor conductors are rotating. Imagine the rotor conductors are rotating with a speed nr. Who is pushing the rotor? Electromagnetic torque. Why electromagnetic torque is pushing the rotor in this direction only? Because then only the relative speed will decrease between stator field and rotor conductors. Okay. Now nr is 0 or finite value. Yes, now this is not 0, guys. That is ns minus nr. Okay, let me write clearly. This is now ns minus nr. This is the cause, guys. This is the relative speed between what? Yes, that is relative speed between stator field and rotor conductors. Stator field and rotor conductors. Got it? So now go back to the field diagram. Yes, what is the relative speed between stator field and rotor conductors? It is ns minus nr. Okay, ns minus nr. Now, who is pushing the rotor? As I told you, electromagnetic torque will push the rotor. Electromagnetic torque will push this rotor. Electromagnetic torque is pushing the rotor. That means, can I say electromagnetic torque is a supporting torque or opposing torque? Supporting torque. If there is a supporting torque, can I say there will be opposition torque also? Yes, that opposition torque is nothing but a mechanical load torque. The mechanical load torque is an opposition torque. So when this supporting torque and opposition torque both are balanced each other or both are balancing each other, that is where steady state condition will come into picture. Steady state. Steady state means supporting torque and opposition torque both are balanced. Now speed will neither increase nor decreases. This is known as steady state condition. Now you may have a doubt here, sir, why nr is always less than ns? Why nr is not equal to ns? For suppose, let's take a small example. For suppose, if nr really reaches to ns, what will happen? For suppose nr really reaches ns, what will happen? If nr really reaches ns, what is the relative speed between stator field and rotor conductors? Is it not this relative speed becomes 0, ns minus nr becomes 0? The moment when ns minus nr is 0, rotor EMF is 0, rotor current is 0, electromagnetic torque is 0. That means so far who is pushing the machine? Electromagnetic torque. Now that electromagnetic torque suddenly becomes 0. The moment when this supporting torque suddenly becomes 0, this opposition torque will decelerate the machine. Immediately the rotor speed will decrease. Okay. So even though forcefully you take the rotor to synchronous speed, it can't stay there. It can't stay there. It will immediately decelerate and nr becomes less than ns. Okay. This is the situation when nr really reaches ns. That's why nr will never become ns. It will always be less than ns. So steady state means the condition where supporting torque and opposition torque balances each other. That steady state will come into picture only when nr is less than ns. Only when nr is less than ns. Okay. So therefore, induction motor will find the steady state. Will find the steady state at a speed less than ns rp. Okay, less than ns rp. Clear? So whatever electromagnetic torque is created, that is a supporting torque, it will always try to reduce the relative speed between stator field and rotor conductors. But it can't succeed. It can't make this relative speed to 0 because the opposition torque is there. Suppose, what if I remove this opposition torque? The moment I said opposition torque is removed, that means who is removed? Load torque is removed. When I say load torque is removed, indirectly the motor is under which condition? No load condition. If the motor is under no load condition, now see, there is no opposition torque, but there is a supporting torque. Okay, there is no opposition, but there is support. So immediately motor will accelerate. And speed will reach synchronous speed. Got it? Immediately motor will accelerate and speed will reach synchronous speed. Therefore, what is the only case where nr reaches ns value? No load condition. Now, you may have a doubt, sir, nr is reaching ns. But this is not actually possible. Why? Because even though load torque is 0, there is still some opposition, especially due to friction. We all know that any rotating object will have a friction, right? And that friction is still opposing the machine. Therefore, ideally speaking, nr may reach ns at no load condition, but practically nr may be very close to ns but not exactly reach ns because friction opposition is there. Ideally, if I neglect friction, then nr can definitely reach ns under which condition? No load condition. Okay, so I can write that point. So at no load condition, no load, nr is almost equal to ns. But with load, So when I said load is connected, that means opposition torque is present. It is never possible to reach ns. Nr is definitely less than ns. Okay. So now we are eligible to discuss about the important term called as slip. Okay. So let us understand what is meant by slip. Hope there are no issues now. I really appreciate everybody. You're staying this much long to learn the subject. So that perseverance, that that confidence, that patience is very important to succeed in competitive exams. Okay. Okay. Fine. Now let us see what is meant by slip speed. The next observation is slip speed. Okay, slip speed is defined as the speed of the rotor from synchronous speed. Okay, it is technically it is defined as it is the speed by which rotor slips from synchronous value. It is the speed by which rotor slips from synchronous value. That means you see this rotor from synchronous speed, whatever gap is there, that is what we call it as slip speed. So slip speed is simply equal to ns minus nr rp. Okay, you see the rotor from, you stand on the synchronous speed point and then see the rotor, whatever speed is there, that is known as slip speed, ns minus nr. What is a unit? rpm, obviously. The moment you know slip speed, now you can understand what is mean by per unit slip. Per unit slip represented with the letter s. Okay, per unit slip is nothing but the ratio between actual slip speed. Per unit quantity is the ratio from actual value to base value. Okay, therefore per unit slip is equal to ratio between actual slip speed with respect to base synchronous speed. Base speed is always synchronous speed, guys. Okay, so actual slip speed ns minus nr by base speed, that is ns. This is the formula for per unit slip. Suppose if the speeds are expressed in radian per second, you can also write formula for per unit slip as omega s minus omega r by omega s. This is another formula. Okay. Now, if you know per unit slip, how do you find percentage slip next? We all know that percentage slip is simply product of per unit slip multiplied with 100. Right? You multiply per unit slip with 100, you'll get percentage slip. Also, you cross multiply this formula. If I cross multiply this formula, s into ns is equal to ns minus nr. From this you can separate nr, right? Nr is equal to 1 minus s into ns rpm. This is another formula. Okay, very simple. Slip is equal to ns minus nr by ns. Slip is different, slip speed is different. Slip speed means ns minus nr rpm. Once you know slip speed, then you can find out per unit slip, that is ns minus nr by ns. And if you know slip value, then nr is equal to 1 minus s into ns. 1 minus s into ns. Got it? Clear? Yes. Next. Now, once we understand what is the definition of a slip, now we will try to understand the equivalent circuit of induction motor, then we will solve some numerical questions. Okay, see, important. Equivalent circuit of induction motor. To understand the equivalent circuit, I will be taking two cases, guys. One is starting condition, second one is running condition. Okay, first one starting condition, second one running condition. So first let us consider starting condition at the time of starting. Starting condition means, can I say NR is equal to 0? Because we know every motor will start from 0 speed, right? NR is equal to 0. If NR is equal to 0, slip will be equal to 1, because slip equal to ns minus NR by ns. When NR is 0, slip equal to 1. And in this case, induction motor is very much equivalent to transformer. Okay. Induction motor is similar to transformer. Why? Why? Because transformer, every part is stationary. Can I say right now induction motor is also stationary? Why? Because I am talking about what? Starting. At starting, rotor is stationary. There are no movable parts at all. As there are no movable parts, induction motor is very similar to transformer. If it is very similar to transformer, you know, transformer primary frequency and secondary frequency both are same only. Therefore, in induction motor, at the time of starting, stator frequency and rotor frequency both are same. Stator frequency and rotor frequency both are same, and this is nothing but supply frequency. Just like a transformer. In a transformer, primary frequency, secondary frequency both are equal, and they are equal to supply frequency. Similarly, in induction motor, especially at the time of starting, stator frequency and rotor frequency both are absolutely same, and it is equal to supply frequency. And as the machine is similar to transformer, can I say transformer circuit is valid for induction motor also? So let us draw transformer circuit. In a transformer, series branch, shunt branch will be there. I hope you have idea about a transformer. This is primary resistance R1, that is nothing but stator resistance R1. Primary means stator, secondary means rotor. Next, stator leakage reactance X1. Then you will be having a shunt branch. We call it as no load shunt branch. Core loss resistance RC. Magnetizing reactance XM. Okay. With this primary is completed. This is the primary branch. Coming to the secondary branch, indirectly the rotor branch. Rotor will have a resistance R2. Rotor will have a leakage reactance X2. And rotor is a closed circuit. Okay. So here we have the supply voltage V1. Okay. So this is the primary induced EMF E1. Secondary induced EMF E2. Secondary current I2. Primary current I1 dash. No load current I1. Total primary current I1. Got it? I don't want to discuss more details about circuit diagram. This is a transformer circuit indirectly. Okay. And remember, rotor is a closed circuit. Don't forget that. And here, can I write E1 by E2? That is nothing but voltage ratio of induction motor. So here, E1 by E2 is nothing but T1 by T2. Turns ratio T1 by T2. Okay, I don't have space sufficient. Okay, E1 by E2 is equal to turns ratio T1 by T2. And remember, all the parameters I expressed in this rotor right now, they are all rotor parameters at the time of starting. Okay. Now let us see the equivalent circuit under running condition. That is important. Running condition means machine was rotating in nature, right? Okay. Equivalent circuit under running condition. Running condition means, can I say NR is not equal to 0? NR is a finite value. But we know one thing, NR is always less than NS. NR is always less than NS. NR will never reach synchronous speed. We have seen the reasons already. Okay. Now you can't treat this machine like a transformer. Why? Because there are rotating parts comes into picture. Okay. Which part doesn't move, whether it is starting or running condition? Stator. And stator is always connected to supply source. That's why stator frequency doesn't change. Stator frequency is still equal to supply frequency. But rotor frequency will change, guys. Now, under running condition, the rotor frequency will be equal to slip times of stator frequency or slip times of supply frequency. There will be a proof for this, but I am not discussing the proof right now. Okay, so very important. Under running condition, stator frequency doesn't change. Why? Because stator winding was connected to supply. What is mean by supply in power system? Indirectly, infinite bus bar. When you connect stator to infinite bus bar means voltage and frequency are always constant values. Okay. But rotor frequency is going to change. The rotor frequency is going to change. Clear? Because rotor frequency is now equal to slip frequency. Okay, that is S times of supply frequency. We also call it as simply slip frequency. This is known as slip frequency. Okay, in a similar manner, rotor voltage will also change, guys. Rotor voltage will also change. Now, rotor voltage, that is E2 under running condition, will become S times of rotor voltage at starting. You try to understand here what is E2, guys. This E2. This E2 is rotor voltage or stator voltage? Rotor voltage, but at starting. But under running condition, rotor voltage will change to S times of E2. So you please try to figure out E2 is rotor voltage per phase, at starting. Okay. Next, S into E2 is rotor voltage per phase under running condition. That is what we call it as slip voltage indirectly. Stator nothing will change, but in the rotor everything is changing. Rotor voltage will change from E2 to S into E2. Rotor frequency will change from supply frequency to slip times of supply frequency. One more thing, guys, when I said rotor frequency changes, which parameter will change in rotor? Can I say reactance will change? Because reactance is proportional to frequency. When frequency is multiplied by slip times, the reactance will also multiplied by slip times. So the rotor will have a resistance R2 and a reactance S times of X2. Therefore, let us draw the circuit diagram under running condition now. Stator nothing will change. Same resistance R1, same leakage reactance X1. It is stationary part. Same no load branch, core loss resistance and magnetizing reactance. What is core loss resistance? What is magnetizing reactance? In a transformers you will study. And this is the stator branch, no changes. But coming to the rotor branch, this is the stator voltage E1, supply voltage V1. But coming to the rotor branch, what is the EMF in rotor now? The EMF in rotor is S into E2. The resistance in the rotor is the same. Resistance is independent of frequency. We are neglecting skin effect. And reactance will change. Now the reactance is S times of X2. Why the reactance was multiplied by S times? This is the rotor current I2. Why the reactance was multiplied by S times? Because frequency is multiplied by S. When frequency multiplied by S times, reactance will also be multiplied by S times. So what is X2? What is S into X2? X2 is rotor leakage reactance at starting. S into X2 is rotor leakage reactance under running condition. Now what is the turns ratio or voltage ratio from primary to secondary? Voltage ratio E1 by S into E2. This will not be equal to turns ratio T1 by T2. Important. At the time of starting, you see, guys, voltage ratio and turns ratio are equal. Why? Why? Because the machine is similar to transformer. In a transformer, voltage ratio and turns ratio are always equal. But at running condition, voltage ratio and turns ratio are not equal because turns ratio changes or voltage ratio changes. Voltage ratio changes. Okay. Why voltage ratio was not equal to turns ratio? Because voltage ratio changes, right? At starting, what is the voltage ratio? E1 by E2. But under running condition, it was E1 by S into E2. Therefore, voltage ratio modified. As voltage ratio is modified, now voltage ratio was not equal to turns ratio. Turns ratio will never modify, right? Once a construction is completed, number of turns are going to be fixed. Only voltage ratio will modify. Okay. So as voltage ratio modified, voltage ratio was not equal to turns ratio. This is the problem. If voltage ratio was not equal to turns ratio, transformer principles cannot be applied. Transformer principles cannot be applied. And one of the important transformer principle is transferring the parameters from primary to secondary, secondary to primary, right? In a transformer, you might have studied, right? How to transfer primary winding resistance to secondary or secondary winding resistance to primary. Why we need to transfer parameters? We need to transfer parameters in order to make the machine as a single electrical circuit. Strictly speaking, this machine is a single electrical circuit or two isolated circuits. Two isolated circuits. There is air gap between the two. But in order to do mathematical analysis, to apply network theorems, to apply KVL, KCL equations or power transfer, maximum power transfer theorems, for anything, you have to make this entire machine as a single circuit. To make it as a single circuit, you have only one choice, that is transfer the parameters from one side to another side. To transfer the parameters from one side to another side, transformer principle has to be applied. Transformer principle will be applicable only when voltage ratio and turns ratio are equal. But here, voltage ratio and turns ratio are unequal. That's why you can't apply transformer principle. Therefore, what I need to do, at starting, is it applicable? Yes. At starting, this is just like a transformer because voltage ratio, turns ratio are equal. Now you can transfer the parameters. But under running condition, I can't do that because voltage ratio and turns ratio are unequal, right or not? They are unequal. So what to do now? I have to modify the circuit. Which circuit I have to modify? Rotor circuit. Why? Because the modifications were happened in rotor only from starting to running. So let us modify this original rotor circuit. Okay. Modified rotor equivalent circuit. Okay. Look at the original rotor circuit. This is extremely important, guys. Listen carefully. In the original rotor circuit, what was the voltage? S into E2. What was the resistance? R2. What was the leakage reactance? S into X2. What was the current? I2. Now, can I write magnitude of the current here by applying KVL equation? What is the magnitude of current I2? Can I say current is simply voltage by impedance? Voltage is S into E2 by impedance was square root of R2 square plus S into X2 whole square. Okay. Now what you do is that take S square common in the denominator. Out of root it will become S. One S will cancel. Therefore, the equation becomes E2 divided by root over. The first term will become R2 by S whole square plus X2 square. Now you see whether it is a first equation or second equation, the current magnitude will be same or different? Same. Okay. When I say current magnitude is the same, the circuit behavior, circuit performance will also be same. But if you look at the second equation, what is a voltage term now? Is it looking like E2? So that means this circuit can be modified as the new voltage term is E2. What is the resistance term now? R2 by S. R2 by S. What is the reactance term? X2. Okay. Now you try to figure out the difference between the two. Whether it is a first circuit or second circuit, the current magnitude is the same or different? Same. Therefore, I can simply replace this first circuit with this second circuit. But what is the advantage with the second circuit? The advantage is in the second circuit, what was the voltage? E2. If the voltage was E2, what is the voltage ratio from primary to secondary? E1 by E2. If it is E1 by E2, can I say this is just like a starting condition? If it is like starting a condition, voltage ratio and turns ratio are equal, therefore machine will behave like a transformer. Therefore, you can transfer parameters from secondary to primary. That is why rather than this original circuit, you better use this modified circuit. If I use this modified circuit, then only parameters can be transferred from secondary to primary. Why we are transferring the parameters? That's the biggest question. I told you transferring parameters is necessary in order to make the entire circuit as a single electrical circuit. Right? Okay, so from here onwards, I am going to use this second circuit. In the second circuit, what is the resistive part? R2 by S. Reactance part, X2. Also, one more modification I am doing. You see this resistive part, R2 by S. Can I write this R2 by S as very simple? You see, for this R2 by S, I am subtracting one R2. I am also adding one R2. No change in the equation. I just subtracted and also added. Now, from the first two terms, you take R2 common. If I take R2 common, it looks like 1 by S minus 1 and then R2 is there. Therefore, if you look at this, is it looking like a single resistance R2 by S is a series combination of two resistances? One resistance is R2, another resistance is R2 into 1 by S minus 1. You will understand very soon why I wrote these two series resistances. Okay, so I will further modify this circuit. See, so the voltage is E2, guys. Now the single resistance R2 by S, okay, I am repeating it as series combination of two resistances. One resistance is R2. Don't forget there is a reactance. And there is one more resistance now. What is the other resistance? R2 into 1 by S minus 1. You will understand the significance of that, dividing a single resistance into two resistances a little later. So out of these three circuit diagrams I have drawn here, which circuit diagrams you can use to transfer the parameters from primary to secondary or secondary to primary? Yes, circuit number 2 and circuit number 3. But who is the original rotor circuit? Circuit number 1. Circuit number 1 is the original circuit, but to transfer the parameters from primary to secondary or secondary to primary, we have to use circuit number 2 or circuit number 3. Got it? Okay, fine. Now, before moving to the next session, we will solve a few numerical questions, guys. Okay. Before moving to the next session, we will solve a few numerical questions. I need a short break. I'm standing from the morning. Okay. Take a break for 5 minutes. Then we will start problems related to slip calculations. Okay. Take a break, then we will solve numerical questions. Okay. Okay, guys, welcome back. Right. So we will continue our discussion. So we have seen the importance of the equivalent circuit and why we are changing the rotor branch parameters exclusively to transfer parameters from rotor to stator or stator to rotor. Okay. So now let us solve some questions related to slip calculations. Okay, guys. Okay. So these questions are very easy. I hope you can answer it. Right. Read the problem. Read the problem. A three-phase, four-pole, 50 Hz slip ring induction motor is rotating at 1360 RPM. What is percentage slip of this motor? Okay. Very simple question. First, you calculate the synchronous speed of this machine. What is the synchronous speed? Synchronous speed is equal to 120 into F by P. So it is 120 into what is the supply frequency? 50 Hz by how many poles are there? 4 poles, correct? So 120 into 50 by 4, this is 1500 RPM, right? And what is the speed at which the rotor was rotating? We know rotor will never rotate exactly at synchronous speed. In this given question, NR was 1360 RPM. 1360 RPM. So now you have NS value with you and NR value also with you. Therefore, what is the operating slip of the machine? NS minus NR by NS. It's a simple question. 1500 minus 1360 by 1500. If you want percentage value, multiply with 100. First you will get per unit value. Multiply with 100 to get percentage value. Can I say the answer is 140 by 1500 into 100? Yes. Let me calculate. Yes. So the answer will be 9.33 percentage. Okay. So per unit value will be 0.093. And you multiply with 100, 9.3 percentage is the slip at which the motor is operating. Clear? Right. This is a simple question. Now let us add one more question. These are all 1 mark models. 1 second. Okay, read this problem. A 3-phase 6-pole wound rotor induction motor. Remember, wound rotor machine or slip ring rotor machine both are same only. Okay. Yes, wound rotor machine or slip ring rotor machine both are same. A 3-phase 6-pole wound rotor induction motor is supplied from 50 Hz source, operating with a slip of 0.06. What is the rotor speed of the machine? Okay. This time they are asking NR value. What is the NR formula? 1 minus S into NS. Okay. Separately calculate synchronous speed. Synchronous speed is equal to 120 F by P. Therefore, 120 into what is the supply frequency? 50 by 6 poles are there. Therefore, NS was 1000 RPM. Now substitute that 1000 here. So 1 minus slip 0.06 into 1000. So I hope you will get 940 RPM, correct? 0.94 into 1000, 940 RPM. That is the value of rotor speed, correct? Okay. Next. Okay. Another question. Read this problem. Okay. The rotor of an induction motor cannot run at synchronous speed because if it did so, which of the following will happen? We know that induction motor will never run at synchronous speed. In case if it runs, what will happen? Okay. Can I say if it did so, that means if rotor really runs at synchronous speed, what will happen? That means they are asking what will happen if NR is equal to NS. We studied already. If NR is equal to NS, what is the relative speed between stator field and rotor conductors? 0. The moment when this relative speed is 0, the induced EMF in rotor will become 0. When induced EMF is 0, the current in the rotor will be equal to 0. Then the torque is also equal to 0. Therefore, look at the first statement. Rotor EMF and current would become 0. Yes, rotor EMF and current both becomes 0. So first statement is correct. Second statement, torque would become 0. Yes, the torque would become 0. Second statement is correct. Just a minute. Yes, the second statement is correct. Third statement, stator core loss would be 0. Stator core loss. See, there is nothing related to core losses here. Rotor core loss may become 0, but not stator core loss, because core loss will always depend upon voltage and frequency. And they are talking about stator core loss. Stator core loss will depend upon stator voltage and frequency. Right now, rotor voltage and frequency may become 0, but stator voltage and frequency doesn't change because they are supply values. Therefore, third statement is a wrong statement. Suppose if it is rotor core losses would be 0, then it is correct. Because core loss depends upon voltage and frequency. As rotor voltage is 0, rotor core loss is 0. Next. Rotor would continue to rotate at synchronous speed. This is also wrong. Why? Rotor cannot continue to rotate at synchronous speed, because immediately the rotor will decelerate. I explained already, right? In case if NR really reaches to NS, what will happen? Yes, here I explained. If NR really reaches to NS, NS minus NR becomes 0, torque becomes 0, then supporting torque becomes 0. Because of this opposition torque, rotor will immediately decelerate. Okay, therefore, the last statement is wrong. Rotor cannot continue to rotate at synchronous speed. That means what are the correct statements? 1 and 2 only. This is like MSQ question. Fine. Next. Let us see. Read this problem. A 6-pole 50 Hz induction motor runs at a speed of 960 rpm. What is the frequency of rotor induced EMF? Frequency of rotor induced EMF they are asking. They are asking rotor frequency. We studied already, rotor frequency is equal to slip times of supply frequency, correct? What is the supply frequency here? 50 Hz. So you calculate a slip value, you will get the answer. What is the slip formula? Ns minus Nr by Ns. First calculate Ns in this question. What is Ns formula? 120 into F by P. So 120 into, what is the supply frequency? 50 Hz by 6 poles. Therefore, 1000 rpm. Correct? Okay. Now the moment you know Ns, calculate slip value. Slip is equal to Ns minus Nr by Ns. So 1000 minus, what is Nr? 960 by 1000. So slip is equal to 0.04. Substitute that. Okay. So 0.04 into supply frequency 50. Is it not 2 Hz? Okay. So the rotor frequency is equal to 2 Hz. 2 Hz. 2 Hz means, you see, very, very small. Generally, the rotor frequency is very small compared to supply frequency, because the slip is usually very, very small. Correct? It's a simple problem again. Okay, 1 mark type. That means option C was correct. Okay. Next. Okay. To answer few more questions, we have to discuss the next topic. Okay. Now, yes, these are the examples related to simple slip formulas. To the next stage will be 2 marks questions. Before answering 2 marks questions, let us solve some more important topics. Now the next one is field theory in induction motor. Field theory in induction motor. If you remember the starting part of this induction machines, I told you basic electromagnetic torque equation. You remember it? What is the basic electromagnetic torque equation? I will go back once. That is important. Let me go back. I told you there are 3 rules to be satisfied to create electromagnetic torque. I request all of you, please read these 3 rules once again. Please read these 3 rules once again. Yes. First rule is stator and rotor must have same number of poles. Second rule is relative speed between stator field and rotor field must be equal to 0. Third rule is phase angle difference must be finite. Now our focus will be on the second rule here. Second rule. What is second rule is saying? Relative speed between stator field and rotor field must be equal to 0. Okay. Now I wanted to prove this particular rule in induction motor. Okay. So how this particular principle is satisfied? Okay. So how relative speed between, it is not relative speed between stator rotor conductors, it is relative speed between stator field and rotor field. Okay. So let us see how this principle is going to be satisfied. Just a moment. Okay, that is what field theory we wanted to discuss. Okay, to understand this, I will be taking the running condition of the induction motor. We know when induction motor was rotating, NR is not equal to 0. NR is always less than NS. And important thing is rotor frequency is equal to slip times of stator frequency. Yes or not? Okay, now let us focus on the field diagram. So to understand the field diagram, you just take a stationary stator. Please remember very clearly, this is an important observation. Slightly confusing, but you should not confuse. Please focus so that you can understand. Okay. All of you, please focus. Right. Now, first let me start with stator. Stator is always stationary, right? This is a stationary line indicating the stator part. And stator will have 3-phase balanced distributed winding. We are exciting this 3-phase winding with a frequency equal to F. Okay, let us assume F is the frequency, P is the number of poles. Whenever 3-phase balanced distributed winding is excited with AC supply, it will create stationary magnetic field or rotating magnetic field. Yes, it will create rotating magnetic field. At how much speed? Synchronous speed. Now I wanted to know how much is that synchronous speed. Therefore, the speed of stator field, with respect to stator, the speed of stator field with respect to stator. Okay, let us call it as NS1. Generally it is synchronous speed. Why I am using a suffix 1? Suffix 1 indicates stator. It is a speed of stator field. Simple formula, 120 into F by P. Any field speed, guys, 120 F by P is the formula. But what F you are using is important. If you are finding the speed of stator field, use a stator frequency. If you are finding the speed of rotor field, use rotor frequency. Right now we are finding the speed of what? Stator field. So use stator frequency. Okay. Therefore this is 120 into stator frequency by P. This is indirectly NS RPM. Got it? So this is a speed of what? Stator field with respect to stator. So therefore what you do is that from stator, draw a line having a length equal to NS. Okay, so this is NS1 and this NS1 is nothing but NS right now. Therefore, this is the position of what? Stator field. That is the position of a stator field. The panel is also overheating because of, full day. It is lagging actually. Okay, anyway. So this is the speed of stator field with respect to what? Stator. Now, where is rotor? Under running condition, rotor will rotate exactly at synchronous speed or near to synchronous speed. Near to synchronous speed. 1 second. The rotor will rotate near to synchronous speed. So this is the position of rotor, guys. These are the rotor conductors, NR. Now tell me, rotor means what is its frequency? Can I say rotor frequency is equal to slip frequency? Therefore, rotor frequency is equal to S into F. Rotor and stator will always have same number of poles. Now, try to understand, rotor is a concentrated winding or rotor is also a distributed winding. Rotor also has a distributed winding carrying AC current with how much frequency? S into F. Therefore, find out what is the speed of rotor magnetic field now. The next question, the speed of rotor field. The speed of rotor field with respect to rotor. If you are finding the speed of stator field, you are finding with respect to stator. If you are finding the speed of rotor field, you are finding with respect to rotor. Yes, this is represented with the letter NS2. 2 is the word I am using for rotor, that is secondary. I told you same formula 120 F by P. But as it is the speed of rotor field, which frequency I have to use? Rotor frequency. What is mean by rotor frequency? 120 into, is it not S into supply frequency divided by P? Now you write S outside, then it will be 120 into F by P. Right or not? And this 120 into F by P, is it not Ns? Therefore, the rotor field speed is S into Ns. And you know the formula for S already. What is S formula? Ns minus Nr by Ns into Ns. Now Ns and Ns will cancel. Therefore, finally, what is the answer? Ns minus Nr. This is the speed of what? This is the speed of what? This is the speed of rotor field with respect to rotor. This is the speed of rotor field with respect to rotor. Okay, now what you do is that from rotor, just to draw a line with how much length? With a length of Ns minus Nr. So, from rotor, you just draw a line with a distance of Ns minus Nr. Can I say Ns minus Nr means it will exactly cover this distance? So, this is Ns2 indirectly. What is meant by Ns2? It is the speed of rotor magnetic field with respect to rotor. That means rotor field is at this location. The rotor field is at this location. Got it? So finally, from this diagram, you try to answer the question. What is the speed of stator field with respect to stator? All of you please try to respond in the chat box to my questions. What is the speed of stator field with respect to stator? Come on. What is the speed of stator field with respect to stator? Ns, correct. Just little info. I don't know what is your name. I hope it is your name, right? Correct. Ns. Yes, correct, Rohan Singh, correct. Next question. What is the speed of rotor field with respect to rotor? What is the speed of rotor field with respect to rotor? Rotor field with respect to rotor. Rotor field with respect to rotor. When I use the word called with respect to, that is relative speed. Yes, Ns minus Nr. Correct. Excellent. Rotor field with respect to rotor, that is Ns minus Nr. Correct. Next one. Next question. What is the speed of rotor field with respect to stator? What is the speed of rotor field with respect to stator? Rotor field with respect to stator. Rotor field with respect to stator. Ns, correct, excellent. Rotor field with respect to stator, it is Ns. Therefore, finally you tell me what is the relative speed between stator field and rotor field. Final answer. What is the relative speed between stator field and rotor field? Relative speed between stator field and rotor field. Relative speed between, yes, 0, correct. Relative speed between stator field and rotor field is 0. Relative speed between stator field and rotor field is 0. Is it the condition to be satisfied for the production of electromagnetic torque? Yes, I told you. In order to create electromagnetic torque, the relative speed between stator field and rotor field must be equal to 0. Must be equal to 0. Okay. So then only electromagnetic torque can be created. Then only electromagnetic torque can be created. Okay. Yes. Both are on the same line, right? That's why the relative speed between stator field and rotor field is equal to 0. Okay. So you need to remember this diagram to answer any questions related to field theory of induction machine. Okay. Please remember the diagram so that you can answer any question related to field theory of induction machine. Now we will answer one such question. Okay. Let us answer one question. Just a moment, guys. I'll just restart my system. It was hanging due to long usage. Okay. Give me 2 minutes. I'll just restart the system. Just a 2 minutes. Let me restart it. It is hanging. The session may not run if it is like that. Okay. So we are back. All right. Okay. Now let us answer a few questions related to this concept. Okay. Hope you are in online. Right. Hmm. Okay. So look at this problem. Read the problem. A 3-phase 4-pole 50 Hz induction motor runs at a speed of 1440 rpm. Now 5 statements are given. We are asked to answer which statements are correct. The correct statements we have to answer. See, the first statement is about slip value. Okay, first calculate the slip value. Given NR is equal to 1440 rpm. Calculate NS. NS is always equal to 120 F by P. So 120 into what is the frequency? 50 by number of poles are 4. Therefore, it is 1500 RPM. So calculate the slip. Ns minus Nr by Ns, that is 1500 minus 1440 by 1500. So I think it is 0.04. Correct. First statement is correct. Slip is 0.04. Next, look at the second statement. Its rotor field rotates at 60 RPM with respect to rotor. See, rotor field with respect to rotor. We just seen the field diagram, right? What is the speed of rotor field with respect to rotor? Is it not Ns minus Nr? Rotor field with respect to rotor, Ns minus Nr. What is Ns in the given question? 1500, Nr 1440, therefore 60 RPM. Second statement is correct. Rotor field rotating at 60 RPM with respect to rotor. Look at the third statement. Rotor field with respect to stator field. What is the with respect to? See, the word called with respect to means relative speed indirectly. Rotor field with respect to stator field, is it not 0? Because both are lying on the same line. The relative speed between stator field and rotor field is equal to 0. Therefore, 60 RPM is a wrong answer. Correct? Next, its rotor runs at a speed of 60 RPM with respect to stator field. See, rotor with respect to stator field. So, if you draw the field diagram, this is a stator, guys. Stator conductors. Stator field will rotate at synchronous speed. This is the position of stator field. Okay. Now, rotor will rotate at a speed near to synchronous value. This is the rotor position, Nr. Now, rotor field will rotate at how much speed? Ns minus Nr. This is the position of rotor field. Now, what is the fourth statement? Rotor stator field. This is the position of rotor, guys. This is the position of stator field. So, what is the gap between these two? Is it not Ns minus Nr again? What is Ns minus Nr? 60. Therefore, this statement is correct. Okay. Look at the fifth statement. Rotor field rotates at a speed of 1500 RPM with respect to stator. See, rotor field with respect to stator. Stator means here. This is a stator. Rotor field is here. This is the rotor field. Rotor field, this is not rotor. This is rotor field. So, what is the relative speed between this rotor field and stator? Is it not Ns? What is Ns in the question? 1500 RPM. Therefore, the fifth statement is also correct. I think the only wrong statement was 3. So, 1, 2, 4, 5 are the correct statements. Am I clear? 1, 2, 4, 5 are the correct statements. So, if you remember the diagram, any question you can answer like that. Any question related to field theory you can answer. 1, 2, 4, 5 are the correct statements. Okay. Yes, option A is correct. Rahul. Yes, Rohan Singh, correct answer. Okay, right. Clear? Okay. This is the relation, field theory concepts in induction motor. Okay. Now, let me try one more question. Okay, that's all. One single question is sufficient. Okay. Next, we will move to the next topic, power flow diagram. Power flow diagram, an important topic where you can expect some questions. Okay, so it is very simple. We just wanted to know how the power was flowing from input side to output side of an induction motor. Okay, so coming to induction motor, there are two parts. One is going to be stator. This is the stator part of the machine. Another one is rotor part of the machine. Got it? Now, how the power is flowing? Induction motor means we will always give electrical power as input, right? We will give electrical power as input. Therefore, the input is electrical power. Okay. Will this entire electrical power will go to the rotor or losses will be there in stator? Definitely losses will be there. What are the common power losses you can expect at stator level? One is copper loss. there is a copper loss in stator, that will be loss. Another one is iron loss in stator. Iron loss means hysteresis loss, eddy current loss, like that. Do you find any rotational losses in stator? No, stator is a stationary body, that's why there are no rotational losses. Rotational losses will be there only when there is some rotating body. Okay. Now after these losses, whatever the remaining power is there, that will go to the rotor through which medium? Air gap medium. That's why we call it as air gap power. That is air gap power. Very important. Air gap power means it is the active power transferred from stator to rotor through air gap. We call it as air gap power. Now, out of this air gap power, will the entire power delivered to mechanical load, or again losses are there in rotor? Again, losses are there in rotor. What are the power losses you can expect in rotor? Obviously, copper loss will be there in rotor, because rotor winding will have some resistance. Whenever current is passing through resistance, loss will be there. But you don't find iron loss in rotor. Why iron loss is neglected in rotor? Because remember, iron losses are depends upon voltage and frequency. And what is the rotor frequency, guys? Rotor frequency is always equal to slip frequency. And generally slip is very, very small. We solved one problem also, right? Stator frequency is 50, but slip frequency is only 2 Hz. As rotor frequency is very small, iron losses are neglected in rotor. If iron losses are neglected, whatever the remaining power is there, that will be converted into mechanical power, because the output is mechanical, guys, right? So the remaining power will be converted to mechanical power. That is what we call it as mechanical power developed. This is known as mechanical power developed. Okay, mechanical power developed. But is there any guarantee that entire mechanical power developed will be delivered to mechanical load? No. Definitely mechanical losses will be there due to friction. Mainly because of friction, you will find mechanical losses also known as rotational loss. Mechanical loss or rotational loss or friction loss, anything is same. Anything is same. After the loss due to mechanical friction, whatever the remaining power is there, that is finally delivered to this mechanical load. That load may be a pump, that load may be a fan, that load may be a crane, train engine, it may be a rocket engine, anything it may be. And finally the power will be delivered to load. We call it as load power or output power or shaft power or net power delivered to load, any word you can use. And finally the ratio between that output power and input power is what we call it as efficiency of induction motor. Okay, so this is the power flow diagram of induction motor. One point is why iron losses are absent in rotor, because rotor frequency is very small, which is slip frequency. Okay, when the frequency is very, very small, iron losses are also very small, so we are neglecting it. Next, why rotational losses are absent in stator? Stator is a stationary part, so there are no mechanical losses or rotational losses. Okay, now how to find out efficiency? That is the ratio from output power to input power. Now, just by using a KCL equation, can you find out relation among these power values? Yes. You just like current going into the node is equal to currents going out of the node. Similarly, power going into the stator is equal to powers leaving the stator. So, what is the relation at the stator level? If you write input power is equal to air gap power plus stator loss, losses in stator. There are two losses in stator. Therefore, from this, air gap power is equal to input power minus losses in stator, stator loss. Okay, this is air gap power equation. Similarly, if you know air gap power equation, how could you write mechanical power developed equation? Can I write the next equation? Mechanical power developed. Okay, I better go to the next page. I don't want to complicate this. Okay. Right? So, mechanical power developed. Mechanical power developed is equal to air gap power minus copper loss in rotor. Copper loss in rotor. Okay. Mechanical power developed is equal to air gap power minus rotor copper loss. Next, if you know mechanical power developed, how do you calculate output power? Yes. Can I say output power is equal to mechanical power developed minus mechanical loss? Then the remaining power will be delivered to output. So output power or load power is equal to mechanical power developed minus mechanical loss. Okay, that is what the power that is delivered to load. Extremely important diagram. You may not remember the formulas, but you need to remember this power flow diagram so that any question you can answer related to power losses in induction motor. Clear? Okay. Now we will shift our focus to an important term here, that is air gap power. Let us shift our focus to air gap power here. Okay, very important term. What is mean by air gap power? Can I say air gap power is the active power transferred from stator to rotor through air gap? Also, can I say this is the active power taken by the rotor? That is the input active power to rotor part. So let us discuss more about air gap power. Okay. Air gap power. Okay. So this is the active power drawn by rotor. As it is the active power drawn by rotor, let us discuss with the help of rotor equivalent circuit. What are the parameters in the rotor equivalent circuit? I have to use a modified circuit, guys. Then only I can shift parameters from stator to rotor or rotor to stator. In the modified circuit, what is the rotor resistance? R2 by S, reactance X2, and what is the rotor voltage? E2, rotor current I2. Okay, now what is mean by air gap power? It is the active power drawn by rotor. You all know that active power formula is simply Vi cos phi. Correct? What is V here? E2. What is I? I2. Power factor cos phi 2. And remember, whatever the equivalent circuit I have drawn, it is a per phase equivalent circuit only. But our actual machine was a 3-phase machine. Therefore, to get 3-phase power value, I need to multiply this formula with 3. Then only I will be able to get 3-phase air gap power. Also, you try to understand one more formula you can write here. You see, there is a resistive element and there is an inductive reactance element. Which element will draw active power generally? Can I say only resistive part will draw active power? Therefore, whatever the power is drawn by this resistive element, that is nothing but air gap power. And what is the formula for power drawn by any resistor? Is it not I square into R? Therefore, one more formula for air gap power is simply I square, that is I2 square into R part is R2 by S. To get 3-phase power, you just multiply the formula with 3. This is one more formula I can use for air gap power. I can develop one more formula, see that. What is the formula for current I2 here? I can write current I2 is it not voltage by impedance? What is voltage? E2 by impedance square root of R2 square plus, sorry, not R2 square, R2 by S square, right? Okay, see this, square root of R2 by S whole square plus X2 square. Only magnitude I need, right? Voltage by impedance. Impedance is square root of real part square plus imaginary part square. Now substitute this current I2 here. But we have I2 or I2 square. So square it. If you square it, root will cancel. Then it will be 3 into E2 square divided by R2 by S whole square plus X2 square into R2 by S. Now out of these three, you can use any formula to represent air gap power of induction motor. Okay, and the unit for power is watt. And remember, this second formula is going to be more helpful for us. This is mostly we will use. Okay, so air gap power is equal to 3 times of I2 square into R2 by S. You try to understand, this is the power drawn by resistance R2 by S. Power drawn by resistance R2 by S. Okay, right. Once I know air gap power, now I can next develop the formula for rotor copper loss. Okay. Yes, copper loss in rotor. Rotor copper loss. PCU in rotor. See, copper loss means it is simply the loss that you will get due to the resistance offered by rotor winding. Therefore, a common equation, right? Rotor copper loss is equal to I square or formula 3 times of I2 square into rotor winding resistance R2. Rotor winding resistance is R2 guys, not R2 by S. R2 by S is the effective resistance of rotor. But R2 is winding resistance. Therefore, 3 I2, why I am multiplying every equation with 3? To get 3-phase power. Because all these quantities are per phase quantities. Therefore, to get 3-phase power, we are multiplying with 3. Okay. So, this is rotor copper loss equation. Yes, if I have air gap power equation and rotor copper loss equation, can I get mechanical power developed equation? Yes. What is the relation? Mechanical power developed is equal to air gap power minus rotor copper loss. Therefore, the next equation is mechanical power developed. Mechanical power developed. Yes, what is the formula? Mechanical power developed is equal to air gap power minus rotor copper loss. Rotor copper loss. What is the formula for air gap power? We developed already. 3I2 square into R2 by S. What is the rotor copper loss? 3I2 square into R2. I think you can take 3I2 square R2 common here. So if I take 3I2 square R2 common, the remaining thing will be 1 by S minus 1. Therefore, is it also looking like I square into R formula only? But what is the R value you are observing here? Yes, you can understand the R value is R2 into 1 by S minus 1. In place of resistance, you have R2 into 1 by S minus 1. Therefore, the power that is associated to this resistance R2 into 1 by S minus 1 is nothing but mechanical power developed by induction motor. You remember in the circuit diagrams that I have drawn earlier, okay, it was missing actually, it is in the previous slide. You remember this single resistance R2 by S is written as series combination of two resistances. What are those two? R2 and R2 into 1 by S minus 1. Okay. Then you can draw the circuit diagram like this. A single resistance R2 by S is written as series combination of R2 and R2 into 1 by S minus 1. Therefore, you tell me now, what is this resistance R2 into 1 by S minus 1 is representing? Yes, this is representing the mechanical power developed by induction motor. So, therefore, this is the mechanical power developed by induction motor. Okay, clear? So, what is the power drawn by R2 by S? That is air gap power. What is the power drawn by R2 into 1 by S minus 1? That is the mechanical power developed by induction motor. Okay, so when you see for induction motor, the load is mechanical load. How do you represent that mechanical load in the equivalent circuit with the help of this resistor? Okay, R2 into 1 by S minus 1. So we have three equations now. Air gap power equation, rotor copper loss equation, and mechanical power equation. Now what you do is that you take a ratio. You take a ratio from rotor copper loss to air gap power. Rotor copper loss is 3I2 square R2. Air gap power is 3I2 square R2 by S. Everything will cancel. You will get ratio S. You cross multiply, therefore rotor copper loss will be equal to S times of air gap power. Very important equation. Rotor copper loss is equal to S times of air gap power. We also call it a slip power indirectly. If you know rotor copper loss, then what is the mechanical power developed? Mechanical power developed is always equal to air gap power minus copper loss in rotor. Therefore, this is air gap power minus what is the copper loss in rotor? S times of air gap power. Therefore, you take air gap power common, it will be 1 minus S into air gap power. This is the mechanical power developed by induction motor. 1 minus S times of air gap power. Got it? Clear? So very important formulas. Now we will answer few questions related to power flow diagram. Before that, for 1 minute you need to observe these equations. Please look at this screen. Try to analyze what is the relation from one power to another power. Okay, just analyze these equations. I'll be back in 1 minute. Okay, meanwhile please go through this power flow diagram, analyze the equations. Okay, are you clear with these equations? So air gap power, it is the power drawn by R2 by S. Just a moment. Yes. Rotor copper loss, mechanical power developed, and the relation among these powers we just identified. Yes, copper loss is S times of air gap power. Mechanical power developed is 1 minus S times of air gap power. Okay. Now we will try to solve few numerical questions related to these power flow equations. Okay. Yes. Let us find out answers for few questions. Right. Fine. See this question. Power input to a three-phase induction motor is 60 kilowatt. Stator loss is 1 kilowatt. Motor is running with a slip of 3%. Calculate mechanical power developed under rotor copper loss. See, power input to induction motor is 60 kilowatt. So input power was given. Input power was 60 kilowatt. Next, if you know input power, how to find out air gap power? Air gap power is equal to input power minus stator loss. Correct? So input power was 60 and stator loss is 1 kilowatt. Therefore, air gap power was 59 kilowatt. Correct? Okay. Once I know air gap power, how to find out mechanical power developed? We have a direct formula. Mechanical power developed is equal to 1 minus S into air gap power. That is what we just developed. Mechanical power developed is equal to 1 minus S into air gap power. So therefore, 1 minus, what is a slip given? 3% means 0.03 into air gap power 59. Use calculator, you will get mechanical power developed. Also, second question is rotor copper loss. Yes, what is the formula for rotor copper loss? Rotor copper loss is equal to S times of air gap power. That is also the formula we derived. Okay. So, you know slip value 0.03, air gap power 59, you will get rotor copper loss also in kilowatt. Okay. You will get answers for both equations. Very simple formula. Yes, tell me the answers. What is the mechanical power developed? Yes, mechanical power developed is 1 minus 0.03 into 59, 57.23 kilowatt. Rotor copper loss also you find out. Okay, simple. I need not to proceed further. All right. Fine. Hope you can solve it, right? Next. Let us try to answer one more question. Okay, read the problem. The power input to the rotor of a 440 volt 50 hertz 6 pole 3 phase induction motor is 80 kilowatt. The rotor EMF is observed to make 100 complete oscillations per minute. Then calculate 5 questions are there. Any one question may come in exam. What is the slip of the machine? Rotor speed NR, mechanical power developed, rotor copper loss, rotor resistance per phase, and last line is assume the rotor is carrying 65 ampere in each phase. First of all, it is clearly given power input to rotor. Power input to rotor means is it not air gap power? Yes. Air gap power is directly given. How much? 80 kilowatt. Okay. And the next information is the rotor EMF is making 100 complete oscillations per minute. Remember, oscillation per minute is nothing but number of cycles per minute. One oscillation is nothing but one cycle. And that too, which EMF it is? Rotor EMF. As it is rotor EMF, indirectly rotor frequency information is given. But frequency means number of cycles per minute or number of cycles per second, number of cycles per second. They said 100 oscillations per minute. That means how many oscillations per second? So the rotor EMF details 100 oscillations per minute. That implies, can I say 100 by 60 oscillations per second? Okay, oscillations per second is nothing but frequency indirectly, cycles per second. Therefore, the rotor frequency is equal to 100 by 60 hertz. We know rotor frequency means slip frequency. And you send supply frequency to the left side, you will get slip now. 100 by 60 into 1 by, what is the supply frequency? 50 hertz. This is going to be the slip of the motor. Okay, calculate what is the slip, then we can solve the remaining problems. So it was 100 by 60 into 50. Is it not 0.033? This is the operating slip of the motor. Okay, that is the first question, right? I got the slip information. Once I know slip value, I can easily find out rotor speed. Second problem, what is the formula for rotor speed? Rotor speed is always equal to 1 minus S into synchronous speed. And S is 0.033. And what is the synchronous speed? It was a 50 hertz 6 pole. That means 1000 RPM. You can separately calculate it if you want. So 1000 RPM. Now you will get rotor speed. Okay, let me solve it. Yes, 966.66 RPM. This is the rotor speed of the machine. What is the next question? Mechanical power developed. What is the formula for mechanical power developed? We already answered one problem like that. mechanical power developed is equal to 1 minus S into air gap power. 1 minus S is 0.033. Air gap power is already given 80 kilowatt. So you will get mechanical power developed in kilowatt. Let's calculate. Yes, I'm getting 77.336. That is the mechanical power developed. One by one, you can answer. And rotor copper loss. What is the formula for rotor copper loss? Rotor copper loss is equal to S times of air gap power. Correct? S times of air gap power. Slip was already given 0.033. Air gap power was 80. You will get rotor copper loss in kilowatt. Now, what is the last equation? Rotor resistance per phase is asked. What is meant by rotor resistance per phase? R2. R2 is asked. To find out R2, one additional information is given. Rotor is carrying 65 ampere in each phase. That means, can I say rotor current I2 is given? Okay, this is given in the problem. Now you already calculated rotor copper loss here, right? What is the formula for rotor copper loss? 3I2 square into R2. Let me calculate. 0.033 into 80. That is 2.664 kilowatt. And use that rotor copper loss to find out rotor resistance. Rotor copper loss formula 3I2 square into R2. Now you know copper loss already. You know I2 value 65 ampere. So can you find out what is the rotor resistance R2? Yes, do it and find the answer. Rotor resistance R2 you can find out. Okay. Okay. Yes. Find out the rotor resistance also. Okay. Yes. Now let's try to answer one more question. See, very simple questions, right? These questions are very simple to answer. Okay. So let's answer one more question. I hope all of you got the rotor resistance per phase. This is the last problem in power flow equations. Solve it. I expect you can answer. I'll give you I'll just give you 1 minute time. Solve it. Come on. Yes, come on. Solve it. Yes, the time is up for 1 minute. Did anybody got the answer? Any answers? Okay. So see, stator loss is given, rotor loss is given, load power is given. See that load power. If this motor is driving a load of 50 kilowatt, load is nothing but output power. Output power was 50 kilowatt. Next, rotational losses are given. Rotational losses are 1 kilowatt. Therefore, you can get mechanical power developed now. Mechanical power developed is equal to output power plus mechanical loss. That is 50 plus 1, 51 kilowatt. Okay, that is the mechanical power developed. And rotor copper loss is given, right? Rotor copper loss is 2 kilowatt. Therefore, what is the air gap power? Air gap power is equal to rotor copper loss plus mechanical power developed. So rotor copper loss is 2, mechanical power developed is 51. So this is a 53 kilowatt. Now you have air gap power and rotor copper loss. What is the slip equal to? Am I audible now? Am I audible? Am I audible now? Okay, hope I am audible. So I would like to end the session here today, guys. It's already been more than 8 hours. Okay, so I will resume this session maybe 2 days later. Today is 22, right? 23 probably, 24 I think. Okay, so 26th or 27th I will take one more session. I will wind up the complete things. Okay, all right. So any questions? I'm ready to answer. Okay, please let me know in the chat box if you have any questions related to this. Yeah. Any questions? Please let me know. My aim was to complete induction machines also today, actually, in this 8 hours, but it wasn't happened. Okay, of course, uh, unless we teach these kind of sessions, we don't know how much time each session will take. For synchronous machines, I already ran one session called as Champions Series, right? I request you to watch the Champion Series. One session still left. Champion Series, 2 sessions already completed. I will take one more session, Champion Series, synchronous machines. Okay, so I don't discuss synchronous machines in this marathon. I request you to watch the Champion Series. If you want, I can give you the links. Okay, you just subscribe to our channel. Everything is available. Okay. Yes, Nagendra, I need to use PPT. Thanks. But preparing a PPT is more hectic in machines, right? Diagrams, equations, so many things. Okay, I don't want to use copy paste things from the material. Of course, in our material, everything is there. I always feel lively when I draw the diagram, when I wrote the formula. That looks very lively and also very interactive. Anyway, thanks for the suggestion. Okay, I will provide this PDF link for you, but that I will provide in my Telegram channel. I request you to join in my Telegram channel if you are okay with that. There is no compulsion. So I will paste the link in the chat box. Mm, EMF I don't. Yes, I gave the Telegram channel link in the chat box. Did you get that message? What happened, Vidyasagar? I didn't get your question. I mistakenly selected OBC MCL in my GATE application form, while I actually belong to OBC creamy layer category. Whether my all India rank will be considered for admission? Um, actually, actually speaking, I too don't have idea about your question. Okay, you better call directly IIT Roorkee, or you put a mail to IIT Roorkee. Okay, because I am not expert in this domain, recording admission process especially. Okay, just a moment. I'll give you the Telegram channel link I told you. Okay. I request Vidyasagar, you please try to approach directly IIT Roorkee management. You write a email stating your issue. Guys, I gave you my Telegram channel link. You can join in that Telegram channel. Okay, I use it to post so many questions also through the Telegram channel. I will also share this PDF, okay, through the Telegram channel. Okay. Yes, they will definitely consider your rank during your admission process. But that's why I'm saying, before the exam itself, if you send an email to them, then there won't be any mistake from your side. Okay. If you have already written the mail, no problem. During admission process, you can show that email. Sir, I already requested IIT Roorkee to consider my issue. Anything that should happen before the exam itself. That email will be a proof that you are from so and so category. I don't think it will be a problem for you if you already wrote the email. Clear? Okay. Any more questions? Yeah. It was really difficult for me because it was a 40 hours subject, discussing within 5 6 hours. It's very stressful actually. What to discuss, what not to discuss. Okay, I tried my best. Hope it was useful for you for your coming exam. Okay, guys. So shall we end the session here? All right. Fine. So thanks for your patience. All right, guys. So we will meet in one more session again. Okay. Thank you.